1.1 says the impulse delivered by a net force acting on an object is equals to the. So let's talk about impulse. We know fully well that impulse is the change in momentum, right? So the question is saying the impulse delivered by a net force acting on the object will be equals to what? A says the initial momentum of the object, B says the final, C says the change in the momentum of the object. We don't have to go any further. We know that the answer is C, right? Impulse is the change in the momentum of an object. And then D says the rate of change in momentum of the object. That is the net force itself, right? The rate of the change in the momentum. Here we're only interested in the impulse, which is the change in the momentum of an object. And 1.2 says the graph below represents the relationship between the net force exerted on an object and the displacement it undergoes, right? The net force and the displacement are in the same direction. And then we have a graph there. And then which one of the following statements can be deduced from the graph? A says the area between the graph and the displacement axis represents the net work done by the force. Let's look at it and see if it's true, right? We know that work is equals to force multiplied by the displacement and cos of the angle between the direction of the displacement and the force that is acting. We are told here on this question that the force and the direction are the same, right? They're going in the same direction. So the angle will be 0, and cos of 0 we know that it's 1. So the work done will be equal to the force multiplied by the displacement. The area of this graph will clearly be equals to the force, right, on the y-axis. So we have force and then the displacement on the x-axis, right, which is delta x. Is a rectangle, so the area is length times breadth, right? And this is clearly equals to the work done by the force on that object. So we go in with option A. Let's see if option B, C, D makes any sense. Option B says the area between the graph and the displacement axis represents the power. F multiplied by delta x is not the power, so there's no way that can be true. And then C says the gradient of the graph represents the change in kinetic of the object. That is not true. And then they say the gradient of the graph represents the work done by the force. It's also not true. So A is definitely our option here, right? We already know. We just disproving all the other options. And then 1.3 says the diagram below shows all the forces acting on an object being pulled to the right by a force F acting at an angle theta to the horizontal. Which of the following expressions can be used to determine the magnitude of the kinetic frictional force acting on the object? This is one of the equations I really like, right? Because most people get them wrong. So we know fully well that the kinetic frictional force will be equals to the coefficient of the friction multiplied by the normal force. Nothing is said here about the coefficient of the static friction, right? So it will just remain as it is. So what we essentially doing in this question, we finding the normal force. Can you find the normal force when the diagram is like this? So physics 101, free body diagram, right? So let's have a free body diagram of all the forces acting on the vertical axis so that we can determine the normal force. So which forces are acting? We know that the normal force is pointing up, and then we know that the weight is going down, right? But then not only is the normal force acting up, there is a force F that is acting at an angle, right? But then, lucky for us, we can resolve this force F and find the vertical component and the x component. So we're going to have the x component going like that, and then the vertical component going up, right? So now you can see that the normal force plus the vertical component of the applied force is equal to the weight, right? So now the normal force becomes the weight minus the vertical component of the applied force. But then how do we find that vertical component of the applied force? We say the force multiplied by sine of theta, right? And which option is that in our options? So we have the work, so we have the weight minus the force. So that is clearly option B, right? So the answer for 1.3 is definitely B, right? But then what happens if the force is acting down and not acting up? Story for another day. And then 1.4 says the position time graph below represents the motion of a ball from the instant it is released from rest from a certain height above the floor and bounces off the floor a number of times. Ignore the effects of air friction, right? So our ball is released from some height, right? And then we hit the ground. So here we definitely take in down as positive, right? And then it bounces off, reaches maximum height, goes down again, hits the ground, and then goes up, and then it goes down to the ground again. And then the question is saying which point PQRS on the graph represents the position time coordinates of the maximum height reached by the ball after the second bounce, right? So here, this is where it's released, and then it hits the ground and bounces off for the first time, right? And then maximum height goes down again, hits the ground and bounces off for the second time, right? So the maximum height reached after the second bounce is at point S, right? And that is option D. So for 1.4, our answer is D, right? If the question was saying after the first bounce, then our answer would be Q, which is option B. But then here we are interested on the second bounce, which is option S, right? And then that is D on our multiple choice. And then 1.5 is saying the kinetic energy of a car moving at velocity v is k, right? The velocity of the car changes to 2v. What is the new kinetic energy of the car? So here I usually advise people to give these variables values, right? Because if you work in variables, most people can't do it, but I can, and I'm gonna show you how. So for the first instance, we have our velocity being equals to v, right? And then if we calculate the kinetic energy there, we're gonna get 1 over 2 the mass v squared, right? But then now the velocity has changed, and then it's now 2v. So what will be the kinetic energy? 1 over 2 m, and in place of v, now we don't have v anymore, but we have 2v, right? So we have 2v squared. So we're gonna get a half the mass. What is 2v squared? 2 squared is 4, right? And then a v squared is v squared. So now we have a half multiplied by 4. So we're going to get 2mv squared, right? So from a half mv squared to 2mv squared, right? How is the kinetic energy of the new car different from the first car, right? It's 4 times greater, because you can easily say 2mv squared divided by a half mv squared. This should be equals to 4. mv squared and mv squared cancel out. We have 2 divided by half, which is equals to 4. So the kinetic energy is 4 times greater, right? And that is option D. And then now let's do 1.6. 1.6 says that a sound source approaches a stationary observer at constant velocity. Which one of the following describes how the observed frequency and the wavelength differ from that of the source? Before we even look at the options, let's look at the concepts first. We know fully well that if a sound source is moving, it's approaching a stationary listener, right? Then the listener will experience a higher frequency, right? And then what is the consequence of a higher frequency? The consequence of a higher frequency is less wavelength, because they are inversely proportional to each other. So we're looking for an option that says higher frequency and less wavelength, right? Option A says the observed wavelength will be greater than. So that cannot be true. We know that it's supposed to be less than, right? And then B says the observed frequency is less than, so that is true. And then it also says the frequency is less than. That is wrong, right? C says the observed wavelength is less than, and the observed frequency is greater than. And that's exactly what we're saying, right? So for 1.6 we can go with C. And then 1.7 says the electric field pattern between two charged spheres A and B is shown below, right? We have the electric field pointing towards A and moving out of B, right? So before we go any further, if the electric field lines are pointing towards, then that sphere is negatively charged. And then if the electric field lines are pointing outwards, then that sphere is positively charged, right? Which one of the following statements regarding the charge of spheres A and B is correct? Sphere A is negatively charged, right? We know fully well that that is true. And then sphere B is positively charged. Yeah, that is true because the electric field lines are radiating outwards, right? So before we go any further here, our answer for 1.7 is A. And then 1.8 says the SI unit of the rate of flow of charge in a conductor is. So yeah, back to the concepts. The rate of flow of charge. What is the rate of flow of charge? We know that I is equals to Q divided by delta T, right? So current is the rate of flow of charge. And what is the SI unit of current? Ampere, right? And then which option is that? It's clearly option C, right? So 1.8, our answer is C. Yeah, it's pretty much easy, not so complicated. And then 1.9 is saying which one of the following changes to the design of an AC generator will increase its maximum EMF output. This is actually a grade 11 work, right? When you're talking about electromagnetism, you know that if you want to increase the maximum EMF, then you have to increase the number of turns on the coil, right? And then for 1.9, that is clearly option D. Another way you can do, you can increase the strength of the magnets, right? Not change the polarity, but increase the strength of the magnets. There's other ways too, but stories. 1.10 says a line emission spectrum is formed when, okay, back to the basics again. So emission spectrum, right? So an emission spectrum is formed when we go from higher energy levels to lower energy levels, right? And then an absorption spectrum is formed when we go from lower energy levels to higher, right? Here we're talking about a line emission spectrum, right? So we're looking for higher to lower. Option A says electrons in the ground state moves to a higher energy state. No, that's absorption, right? Lower to higher. Now we want higher to lower. And then B says electrons in the higher energy state move to a lower state. We don't have to go any further. That's what we're looking for. So we have two blocks here. One of mass 2 kg and the other one of mass 5 kg. And then there's a force applied on the 5 kg block at an angle of 20 degrees. And then we are told that the 2 kg and the 5 kg blocks, they both experience kinetic frictional forces, right? Of 10 Newton and 15 Newton respectively, right? So the 2 kg block experiences a kinetic frictional force of 10 Newtons, and then the 5 kg a kinetic frictional force of 15 Newton. That's what respectively is basically telling us. And then the first question, 2.1.1, it says, let's state Newton's second law of motion. Again, Newton's second law of motion in words, it just states that when a non-zero resulting force is applied on an object, the object will accelerate in the direction of the non-zero resulting force with an acceleration directly proportional to the F net and inversely proportional to the mass, right? So we know fully well that F net is equals to ma, and then in this equation, if you make acceleration the subject of the formula, you basically get the definition, right? Acceleration will be equals to F net divided by the mass. Clearly in this case, the acceleration is directly proportional to the F net and inversely proportional to the mass, right? And then 2.1.2 says, let's draw a labeled free body diagram for the 5 kg block. So here's our 5 kg block here, right? So free body diagram, we denote the body with a dot, right? So there we have our dot. We are told that there's a force applied, right, at an angle of 20 degrees relative to the horizontal. So let's have that force that is applied, right? So we have FA, A denoting applied. And then no questions asked. Any object on Earth will always experience FG, right? The force of gravity. So we have Fg. And then if that body rests on a surface, then the surface will exert a normal force on the body, right? So there we go, normal force. And then apart from the normal force, the 2 kg and the 5 kg block are connected by a string, right? So we must have tension, right? So we have tension there. We are also told that there's a kinetic frictional force acting on the blocks, right? So we can have Fr also acting to the left. So let's, do 2.1.3, which says that let's calculate the magnitude of force F. Force F is the applied force, right? That must be applied at an angle of 20 degrees to the horizontal to make the 2 blocks accelerate at 2 meters per second to the right. So in this situation, we need the acceleration to be equals to 2 meters per second. So here, we're trying to find the magnitude of force F that must be applied at an angle 20 degrees to the horizontal, right? So the force F that is applied, it's applied on the 5 kg block. So we're going to go to the 5 kg block and try see if we can get the magnitude of force F. So what are we essentially saying? We're saying that for the 5 kg block, right, F net is equals to ma, right? So now in place of F net, we can add the forces that are acting, and in place of ma, we have the mass and we know the acceleration. So which forces are acting? We know that along the horizontal, we are going to have Fa x, right? We're going to resolve the force applied along the x, right? And then now we're going to minus all the forces that are opposing the motion. Which forces are opposing the motion? Obviously, frictional force will be opposing the motion, and then the tension force will also be opposing the motion. And this will all be equals to ma. So what is Fax? Fax will be the force applied multiplied by cos of 20 degrees. We know fully well that if you want to find the x component, you take cos of the angle, and then if you want to find the y component, you take sine of the angle, assuming that you are on a flat surface, right? And then minus frictional force. The frictional force, it is said to be equals to 15 Newton, right? So minus 15 and then minus the tension. We don't know what the tension is, so we're just gonna leave it like that for the moment. And then that is all equals to ma, right? We know the mass fully well. The mass is 5, and the acceleration, we're assuming that it is 2, right? The equation says, let's find the magnitude of the force F that must be applied if the blocks will accelerate at 2 meters per second. So now, let's go ahead and solve for Fa cos of 20 degrees, right? So we have Fa cos of 20 degrees being equals to, so we're taking minus 15 to the right hand side and minus tension, right? But then on the right hand side, we have 5 multiplied by 2, which is just 10. So we're going to have 10 plus 15 plus tension, right? So now we can divide both sides by cos of 20. So we're going to get force applied being equals to 25 plus the tension divided by cos of 20. So it's easy to see now that we just need the tension. If we get the tension, then we basically have the force applied, right? So we have already used the 5 kg block. What we can do now is to use the 2 kg block and see if we can get the tension from the 2 kg block. So from the 2 kg block, there is the tension that is pulling it to the right and the frictional force that is pulling it to the left, right? So we're gonna have something of this manner. So we have 2 kg, and then in place of 2 kg, we know fully well that F net is always equals to ma. So now the force that is greater than the other is the tension, and then we're going to subtract the force that is opposing, which is the frictional force, and this will be equals to ma. But we know fully well what the frictional force is, right? It's given to us. It is said to be equals to 10 Newton, right? So we have frictional, which is 10 Newton. The mass is 2 kgs, the acceleration is 2. So the tension is basically equals to 4 plus 10, which is equals to 14 newtons, right? So here in place of T, we can substitute 14 newtons. So we're going to have 25 plus 14 divided by cos of 20 degrees. And if you put that in your calculator, you're going to get the force applied being equals to 41.50 newtons, right? And we basically done with that equation. Let's move to 2.2. 2.2 is into us. The Earth exerts a force of 1842.5 newtons to keep a satellite of mass 200 kg in orbit around the Earth, as shown in the diagram below. We have a very fancy sketch there. And then the question says, let's calculate the distance above the Earth's surface at which the satellite orbits the Earth. So let's look at the information we have, right? We have the force that is acting between the Earth and the satellite. And then we have the mass of the satellite, right? Apart from the mass of the satellite, we have the mass of the Earth, because the mass of the Earth is a constant, right? So we have the mass of the Earth. And then now, what we're looking for is the distance between the Earth and the satellite, right? So we can use Newton's law of gravitational acceleration, right? Every body attracts every other body with a force that is directly proportional to their masses and inversely proportional to the square distance between them, right? So we're saying that F is equals to G, that G being a constant, right? And then mass of the satellite, mass of the Earth, and then divided by the distance between them. The distance between them will be equals to the radius of the Earth plus the actual distance between the Earth and the satellite, right? So we're saying that F is given to us, right? 1842. So we have 1842.5 being equals to that capital letter G, right? Which is a constant. It's 6.67 times 10 to the minus 11. So now the mass of the satellite, is said to be 200 kgs. And then the mass of the Earth, right? 5.98 times 10 to the minus 24 divided by the distance between them, right? So we have distance squared, right? So now we're solving for the distance squared. It's easy to see. We know fully well that if we have A is equals to B divided by X, and you want to find X, you're going to cross multiply, right? You're going to get AX is equals to B multiplied by 1. So X will be equals to B divided by A, right? So we're going to apply the same idea in this situation. Our X is D squared, right? So we're going to have something like this. So we're going to have D squared being equals to this entire expression here, right? So let me just duplicate it for the sake of time, and then we dividing that by 1842.5. And then after you do that, you definitely take square roots on both sides, right? So you take a square root on this side, and then you take a square root on the right hand side too, and then you're gonna get a distance of 6,579,982.8 meters, right? So this is the distance between the Earth and our satellite. But then we don't want the distance between the Earth and the satellite. We want the distance above the Earth's surface at which the satellite orbits, right? Even if you look in the question here, it's in bold, right? The distance above the Earth's surface. So that distance will be equals to the distance we just calculated right now minus the radius of the Earth. This question has 5 marks, right? So if you stop here, you only have 3 marks. The other 2 marks is for you to subtract the Earth's radius from this value that we have. So if we do that, we can now say the distance above will be equals to 6,529,982.8 meters minus the radius of the Earth, right? The radius of the Earth is a constant, so we know fully well that that is 6.38 times 10 to the 6 meters, right? So your answer is going to be equals to 1.9998 times 10 to the 5 meters. So what we have below is a velocity time graph that shows the motion of a ball thrown vertically downwards, right, from the top of a building and bouncing off the floor as it hits the ground. And then we can ignore the effects of air friction, and then it's a must that we take upward as positive. And then the first question, 3.1.1, says using equations of motion only, let's calculate the height from which the ball is thrown, right? So we are looking for delta y, the height at which the ball is thrown. Problem solving 101. We look at the information we have, right? And try use that information to find out what we don't have, right? So what information do we have here? At t is equals to 0, we have a velocity here of which the ball is thrown at, right? So the velocity that we have here, which will be our VI, right, is given as minus 20 meters per second. And then when the ball hits the ground, it has a velocity of minus 25 meters per second, right? So we can say our VF in this instance would be minus 25 meters per second, right? We know acceleration. We always know it's a constant, right? If we take in upward as positive, then our acceleration should be minus 9.8 meters per second squared. So we have VI, we have VF, we have our acceleration, and we'll need delta y, right? So which equation of motion has these 4 variables that we can use? We know fully well that that equation is VF squared is equals to VI squared plus 2a delta y. We have the acceleration, we have VI, we have VF. We're looking for delta y, right? So what is VF? VF is minus 25, right? That's the velocity at which our object strikes the ground. And then VI is minus 20, the velocity at which it is thrown off the building, right? Plus 2 multiplied by A. A is our gravitational acceleration, minus 9.8, right? And then we're looking for delta y. So basically, the physics is done now. We are just solving the math. So we're going to have minus 25 squared minus 20 squared being equals to 2 multiplied by minus 9.8 delta y. We just took minus 20 squared to the left hand side, right? So now it will be obvious what we're going to do. We're going to divide both sides by 2 multiplied by minus 9.8. So if we do that, we're going to get delta y being equals to minus 25 squared minus 20 squared, everything divided by 2 multiplied by minus 9.8, and then our delta y is equals to minus 11.48, right? Which is just 11.48 meters. So the height above the ground is 11.48 meters. Now we can do 3.1.2. 3.1.2 says let's find the time t on the graph. So time t on the graph is here, right? So let's analyze our motion. Here at this point, the object is thrown downwards, right? And then at minus 25, it hits the ground. When it hits the ground, it bounces off with a velocity of 12 meters per second, right? Until it reaches its maximum height. So what we do here, we calculate the time for this part of the motion from the moment it is thrown downwards to the moment it hits the ground. And after we're done with that, we calculate the time from the moment it leaves the ground to the maximum height which it reaches, right, when its velocity is equal to 0. So for that part of the motion, we have Vf, obviously, right? And then we have Vi, we have A, but then now we don't need delta y. We already have it. We're looking for delta t, right? We want that time, because that time, delta t in our graph here, is the time from the instance the ball or the object is thrown downwards, right? So here for that first part of the motion, we're gonna get Vf is equals to Vi plus A multiplied by delta t. What is Vf? Minus 25. And what is Vi? Minus 20. We know fully well what our acceleration is, minus 9.8, and then multiplied by delta t. So we're gonna have minus 25 minus 20 being equals to minus 9.8 multiplied by delta t. So we divide both sides by 9.8, right? If you do that, you get delta t being equals to 0.5102 second, right? And then we are done with that part of the motion. Now we need the part of the motion from the time it leaves the ground to the time it reaches its maximum height, right? So what do we have there? We have Vi for that part of the motion, and then we have Vf, right? Maximum height. We know the velocity is equals to 0. And then we have the acceleration, and we're looking for the time. So what is Vf in that instance? We're still using the same formula. Vf is equals to Vi plus A delta t. So Vf is 0, right? Maximum height. And then Vi will be 12. Here it is, right? 12 meters per second. And it's positive because the object has left the ground. It is now moving up. Plus the acceleration, which is minus 9.8 multiplied by delta t. So you can see what we're going to do here. We're going to take 12 to the left hand side and divide both sides by 9.8. So delta t is going to be equals to minus 12 divided by minus 9.8, right? And that will be equals to 1.2245 seconds, right? So now that time on our graph will be equals to the time from here to here, right? Which is 0.51, and the time from here to here, which is 1.2245. So we add in the 2, we have 0.51 plus 1.2245, right? And that should be equals to 1.7345 seconds. 3.1.3, which says that let's determine using equations of motion the magnitude of the displacement of the ball from the moment it is thrown until time t. So the ball is at some height, right? And then it is thrown downwards and then it hits the ground. After it hits the ground, obviously it's gonna move up, right? And then it moves up to some maximum height. At the maximum height, that's our time t. At this instance, we know the height the ball was thrown above the ground, but we're looking for the displacement of the ball, the change in position from the time it is thrown until it reaches maximum height. This is the object's maximum height after it bounces off the ground, right? So we're basically looking for this part here. This is the part we're looking for. So if we find this height from the ground to its maximum height, then we're going to be able to calculate that displacement that we are looking for. So what are we saying? We know the height, right? We know fully well that the height is at 11.48 meters above the ground, right? Now let's find the maximum height it reaches after the bounce, right? So we know fully well that the VI that it leaves the ground with is 12 meters per second, and then the VF, because it's at maximum height, it's 0, right? And then we know the acceleration, but now we're looking for delta y and not delta t. So which equation of motion can we use? We're gonna use VF squared is equals to VI squared plus 2a delta y. So VF squared, we have 0 squared, which is equals to VI squared, so that's 12 squared plus 2 multiplied by minus 9.8 delta y. It should be obvious. We're going to take 12 squared to the left hand side and divide both sides by this coefficient here. If we do that, we're going to get delta y being equals to minus 12 squared divided by 2 multiplied by 9.8. This here is supposed to be a minus, and then the answer we get in is 7.346 meters, right? So now our displacement will be equals to 11.48 minus 7.3469, which is equals to 4.1331 meters, right? Now we can move to 3.2. So 3.2 says, can you sketch a position versus time graph for the motion of the ball from the moment it is thrown until it reaches its maximum height from the bounce? Use the ground as the 0 position, right? And then we must indicate the height of which the ball is thrown and the time t, right? Which is things we have calculated. So let me just sketch our Cartesian plane. So on the x-axis we have the time in second. So on the y-axis we need delta y in meters, right? So let's start by indicating the maximum height which it is thrown, right? So the maximum height we say is 11.48. Yeah, like we've been saying, we're moving from maximum height and then it is thrown downwards, right? And then it hits the ground, and then it bounces until it reaches its new maximum height, right? This height here, we know fully well what it is, 7.3469, and then the time here, which is the time t that we're supposed to indicate, we just calculated it not too long ago, right? 1.73 second. The diagram below shows trolley A of mass 2 kg traveling at a velocity of v meters per second east on a straight horizontal surface, colliding head-on with trolley B of mass 4 kg traveling at a velocity of 5 meters per second west. And then after the collision, the two trolleys stick together and move at a constant velocity of 1.67 meters per second west. The collision only lasted for 0.01 second. Ignore the effects of friction. And then 4.1 says, state the principle of conservation of linear momentum inwards. We know fully well that it states that the total linear momentum in an isolated system is conserved. The total linear momentum in an isolated system is conserved. What does that mean? The sum of the momentum before a collision will be equals to the sum of the momentum after the collision. And then 4.2 says, let's calculate the magnitude of the velocity v of the trolley A before it collided with trolley B. The magnitude of the velocity of trolley A before it collided with trolley B. In 4.1, we stated the principle of conservation of linear momentum in wires. And then in 4.2.1, we're going to use that definition to determine the velocity v of trolley A. So what does the definition essentially say? We've went through that, right? We're saying that the sum of the momentum before will be equals to the sum of the momentum after. Before the collision, we have the 2 kg trolley moving towards the east and the 4 kg trolley moving towards the west. So what we can do here, we can take one direction as positive, right? It only makes sense to take east as positive. Let's not forget that momentum is given by the momentum is equals to the mass multiplied by the velocity, right? So the momentum of the 2 kg trolley will be the mass of the 2 kg trolley multiplied by the velocity v, right? Plus the momentum of the 4 kg trolley. It will be the mass of that trolley multiplied by the velocity it possesses, right? And this will be equals to, we are told that after the collision they move together, right? They become one body, so we can add up the masses. So we have the mass of A plus the mass of B multiplied by VF that they move with together, right? So what is the mass of trolley A? The mass of trolley A is 2 kg. And then what is the velocity of trolley A before the collision? That's what we don't know, and we're looking for it, right? So we just have V plus the mass of trolley B, which is 4 kg. And then what is the velocity of that trolley? Is 5 meters per second, right? To the west, we must put a negative sign, right? And then this will be equals to, we're summing up their masses. So we have 2 kgs plus 4 kgs. And the velocity after, which velocity do they move with? 1.67 meters to the west, right? So if it's to the west, then we must put a negative sign. Minus 1.67, right? And then now the physics is essentially done, and we're just solving the math, right? We're looking for V. So 2 multiplied by V, that will be 2V, and then 4 multiplied by minus 5, that will be minus 20, and that will be equals to essentially 6 multiplied by minus 1.67, which is equals to minus 10.02. So now 2V will be equals to minus 10.02 plus 20, right? So V will be equals to minus 10.02 plus 20, everything divided by 2. And the answer is 4.99 meters per second. We know that positive is to the east, right? So we can write here and say to the east. If the value was negative, then we would know that that velocity is to the left. And now we can do 4.2.2. 4.2.2 says, let's calculate the force that trolley B exerts on trolley A, right? The force that B exerts on trolley A. Since this question is on momentum and impulse, let's use Newton's second law in terms of momentum, right? We know fully well that it says that F net is equals to the rate of change in momentum. So if we can calculate the rate of change in momentum of trolley A, then we will know the force that B exerts on A. So what is the change? We know that delta P is equals to momentum final minus momentum initial, right? So F of B on A will be equals to the change in the momentum of our trolley A, right? So the change in momentum, we're gonna have the mass which is 2 kg, right? multiplied by the velocity final. The velocity final is this 1.67 meters per second that they move with after they've joined each other, right? So we're gonna have, and that velocity is to the left, so let's put a minus sign when you substitute it, because we're taking east as positive, right? So we're gonna have minus 1.67, and then minus the momentum initial, right? So we have 2 kg again multiplied by the velocity initial. We just calculated it here, right? It's 4.99. So we have multiplied by 4.99, and then we divide everything by the time the collision takes, right? The collision lasted for 0.01 second. So everything divided by 0.01. And then the answer I'm getting here is minus 1,332 newtons. We've already established that the direction to the east is positive, right? So since we have a negative value, then we know that that force is exerted to the west, right? So we're gonna have 1,332 newtons to the west, right? And it makes sense. If trolley B is moving to the west and then trolley A is moving to the east, then when they collide, trolley B will exert a force on trolley A to the west. A force of 62.5 Newton is applied to a trolley of mass m kg parallel to the inclined surface as shown to keep it moving down an inclined surface at a constant velocity. The vertical height of the inclined surface is 12 meters, and then refer to the diagram below. A kinetic frictional force of 35.5 Newton acts on the trolley as it moves down the inclined surface. And then 5.1 says write down the name of the conservative force acting on the trolley. So in our context, in our curriculum, we only have 2 conservative force that we talk about, right? We talk about gravitational force and electrostatic force. Here in this instance, the only force that is acting on this trolley as it moves down the incline at a constant velocity is gravitational force, right? Gravitational force. And we can move to 5.2. 5.2 says let's calculate the work done by the friction on the trolley, right? So fine, we are given the frictional force. Here it is. Here it is said to be so we have frictional force which is equals to 35.5 newtons, right? And then apart from frictional force, we know the height, right? But then from the height we can find the length of the incline, right? How can we do that? We have the angle here, and then we have the height. We can use trig ratios, right? So what we can do, we can say that sine of theta is equals to y divided by hypotenuse, right? But then in this instance, we know the angle. We know that sine of 30 degrees is equals to our y is our height, right? Which is 12 meters. So we have 12 meters divided by the length of the incline. That's what we ultimately interested in. So we can label that as delta x. So it should become easy to see now that delta x will be equals to 12 divided by sine of 30. And then if we do that, we get 24 meters. So we have the frictional force, we have delta x, and then we have the angle between the frictional force and the direction of the motion. So now we can say that the work done by the frictional force will be equals to that force of friction multiplied by the displacement of the object multiplied by the angle, right? So what is the frictional force? We've already said that the frictional force is 35.5, right? We calculated the displacement, that's 24, and then the angle. All the time, frictional force opposes the motion, right? So the angle should be 180 degrees, right? So we have cos of 180 degrees. And then if you punch that in your calculator, you're gonna get minus 852 joules, right? So that is the amount of work the frictional force is doing on the trolley. And then now let's do 5.3. 5.3 says write down the change in kinetic energy when the trolley reaches the bottom of the inclined surface. Let's go back to our statement again. We have constant velocity here, right? We know that the change in the kinetic energy is equals to a half mass Vf squared minus a half mass Vi squared. If we are moving at constant velocity, then Vf squared is equals to Vi squared. So the change in kinetic energy should be equals to 0 joules, right? And then now we can do 5.4. 5.4 says use the work energy theorem to calculate the mass m of the trolley. The work energy theorem to calculate the mass m of the trolley. Here I'm going to use work net is equals to the change in kinetic energy. The other formula you can use, you can say that the work done by non-conservative forces is equals to the change in the potential energy plus the change in the kinetic energy, right? Maybe this is the formula you might want to try out and see if it also works. But then I'm going to use this first formula here, right? So what is the work net? The work net is the sum of all the works done by the individual forces, right? So we have the work done by Fg, and then we have the work done by friction, and we have the work done by the force applied, right? And this is equals to Ek. But we know what Ek is. Ek is 0, right? Apart from Ek, we know the work done by friction. We just calculated it in the 5.2, right? So what is the work done by Fg? The force of gravity multiplied by the height, and then cos of the angle, right? Plus the work done by friction. We know that that is minus 852, right? And then plus the work done by the force applied. We know that the force applied is 62.5, right? So we're gonna, let me just write it in the line below. So plus 62.5 multiplied by the displacement, and then cos of the angle, right? And this should be all equals to 0. So let's talk about this work done by gravity first. So there's two ways you can use to find the work done by gravity. You can use the gravity itself, right? And the height. Apart from that, you can find the parallel component of the gravity, and then you can use the displacement, right? The distance from A to B, which is 24 meters. If you also use that, we should get to the same answer, right? But then I'm just gonna use this in this question. So what is Fg? Fg is the mass multiplied by the gravity, right? Which is 9.8, and then the height is there on our sketch. We know that is 12 meters, and then what is the angle? The angle between Fg and the change in the object's position relative to the height, right? That angle is 0, so we have cos of 0, right? Because gravity is pulling the object down, and ultimately along the height the object is going down, right? So that angle is 0, and then minus 852 from gravity, and then now we'll have plus 62.5, and then the displacement we calculated it, we know that is 24, right? 24, and then multiply by cos of 180. Why am I saying cos of 180? Because this force applied is pulling the object up, but then the object keeps sliding down at constant velocity, right? So the angle between the force and the direction of the motion is 180, and that will all be equals to 0. So you can see here that the only variable we have that is left is the mass, right? So we have solved the conceptual physics problem. Now we're just solving the math. Before I put anything in the calculator, I'm just gonna take everything that belongs to the right hand side to the right hand side, right? So I'm gonna have the mass multiplied by 9.8 multiplied by 12. Cos of 0 is 1, right? So there's no need to include that. That will be equals to, now I'm taking this minus 852 to the right hand side, so it will be positive 852. And then this here, right, we know fully well that cos of 180 will be minus, right? So when I take 65 multiplied by 24 to the right hand side, it will be positive, because cos of 180 is minus. Now we're taking it to the other side, it will be positive, right? So here we're gonna have plus 62.5 multiplied by 24. So now it will be easy to see. We're dividing both sides by the coefficient of m, right, the mass. So we're gonna have the mass being equals to 852 plus 62.5 multiplied by 24 divided by that coefficient 9.8 multiplied by 12. And the mass is apparently 20 kgs. We have a sphere A here of charge minus 5 microcoulombs hanging from a ceiling, right, by means of a light inextensible string. And then 100 millimeters away we have a point charge P. And then the first question, 7.1.1 says, did charge the sphere A lose or gain electrons to acquire a charge of minus 5 microcoulombs, right? So if a sphere was neutral, right, and then now it has a charge of minus 5 microcoulombs, did it gain or did it lose electrons? We know fully well that electrons are negatively charged, right? So if it becomes more negatively charged, then it gained electrons, right? So for 7.1.1, this sphere definitely gained electrons. And then 7.1.2 says, calculate the number of electrons gained or lost by sphere A to acquire a charge of minus 5 microcoulombs. The number of electrons gained or lost, right, is equals to the change in the charge of the sphere divided by the charge of an electron, right? So this change is going to be the charge of the sphere final, which is minus 5 times 10 to the minus 6, right? And then initially our charge was neutral, so we have minus 0 here. And then we can divide all of these by the charge of an electron, right? We know fully well that the charge of an electron is minus 1.6 times 10 to the minus 19. So the answer we get in here will be 3.125 times 10 to the 13 electrons. I feel like I've solved this problem before somewhere. Just can't remember. But then anyway, stories in passing. And then 7.1.3 says, let's calculate the electric field at point P due to charge the sphere A. And then the mark allocation is 5, right? We're waiting for 5 marks, which doesn't make any sense because this question is very simple and straightforward. We don't deserve 5 marks. But then anyway, the examiners make the rules. So we have the electric field being equals to K multiplied by the charge of the sphere divided by the distance squared, right? We know fully well that K is a constant. That is 9 multiplied by 10 to the power of 9. And the charge on our sphere, right, is 5 times 10 to the minus 6. We've already established that the distance is 100 millimeters, right? So that 100 millimeters, to convert it to meters, we divide by 1000, right? So we're going to have 100 divided by 1000 squared. And then if you punch that in your calculator, you're going to get 4.5 times 10 to the 6 newtons per coulomb of charge. And just like that, you've earned yourself 5 marks, right? Which is, yeah, unheard of. And then 7.2 says an identical sphere B Here it is here. Carrying an unknown charge placed on an insulated stand is brought closer to sphere A. Yes, sphere A. And then charged sphere A shrinks to the right and comes to rest so that the string makes an angle of 30 degrees with the vertical. And the tension in the string is 25 newtons. The distance between the two charged spheres is 50 millimeters as shown in the diagram below, right? And then without wasting any time, 7.2, so 7.2.1 says, is the charge on sphere B positive or negative? Give a reason for your answer. So we have sphere B here, right? And then we have sphere A. And then when sphere B is moved closer to sphere A moves further away, right? So they should have like charges, right? That's why they're repelling each other, so to say. So now we can conclude that sphere B has a negative charge, right? Why are we saying it has a negative charge? Even the question says we should give a reason. It has a negative charge because it is repelling sphere A, and sphere A has a negative charge. So sphere B must have a negative charge consequently, right? Yeah. And then 7.2.2 says, let's calculate the magnitude of the charge on sphere B. Yeah, here that's, where it starts to get a bit complicated. Let's calculate the magnitude of the charge on sphere B. So problem solving 101. Let's look at the information we have, right? So with regards to sphere B, we know the distance r away from sphere A. We know k is a constant, right? We know the charge of sphere A, and then we don't know the charge of sphere B. That's what we're looking for, right? Another thing we don't know is the electrostatic force between A and B, right? If we can find the electrostatic force between A and B, then we can use F is equals to K Q1 Q2 divided by R squared, right? We have R squared already. We have Q1, we don't have Q2, we have K. So if we find F, then we can find the charge on sphere B, right? So how can we possibly find that F? We can use sphere A, right? Here in this question, you don't have any option. You have two spheres, A and B. We have exhausted all our options with regards to sphere B, and we can't find a way to go to the answer. We are definitely going to use sphere A. So sphere A is at rest there, right? If sphere A is at rest, then FB on A should be equals to the tension force, because the electrostatic force of B on A is moving A to the right, and the tension is holding A from moving to the right, and then A is at rest. So these two forces are balanced, right? And then if we can find the x component of the tension, then we can find FB on A, right? So let's see what happens. So FB on A will be equals to the x component of the tension, right? Because clearly the tension is acting at an angle. Let me make it a bit more clear. So we have sphere A here, right? And then FB on A is pushing to the right? And then the tension is acting at an angle. So if we resolve the tension, then we're gonna know the magnitude of FB on A, right? So now we can say that the tension is 25, right? Multiplied by, if you want to find the x component, you use cos on a flat surface, right? And then on an inclined, you use sine. And then the angle that you use is not these 30 degrees that we have here. You use the angle between the force and the x component. Since that angle, this angle here is 30, right? This angle here will be 90, and the angle we're supposed to use is this 60 degrees here, right? So now we can say cos of 60 degrees. So we have 25 multiplied by cos of 60. 25 multiplied by cos of 60 is 12 12.5 newtons, right? So now we know FB on A. We can use this formula here to find the magnitude of charge P. Right? A very interesting problem. So now we can say FB on A is equals to K, the charge of B, the charge of A divided by the distance between them squared, right? So what is FB on A? FB on A, we know fully well that that's 12.5, right? K is a constant, 9 times 10 to the 9, and then the charge on B is what we're looking for, and then the charge on A, that is 5 times 10 to the minus 6, right? Divided by the square distance between them, 50 millimeters. If it is millimeters, then we have to divide it by 1,000 so that we can convert it to meters. So we have 50 divided by 1,000, and then let's not forget to square, right? And then now you can see that we have solved the conceptual physics problem. We're just doing the math. We're solving for Q of B, right? So here what we're gonna do, we're gonna cross multiply. If we cross multiply, we're gonna get 12.5 multiplied by 50 divided by 1,000 squared, being equals to 9 times 10 to the 9 multiplied by 5 times 10 to the minus 6 multiplied by the charge on B, right? So now it should be easy to see now that if we divide both sides by this term, we should get the charge on B, right? So consequently, the charge on B will be equals to 12.5 multiplied by 50 divided by 1,000, without forgetting to square, right? Everything divided by 9 times 10 to the 9 multiplied by 5 times 10 to the minus 6, and then the charge on B will be equals to 6.9444 times 10 to the minus 7 coulomb. A group of grade 12 learners want to determine an efficient conductor which can be used as the heating coil for a kettle that they're constructing for their ESCOM Expo project, right? So let's underline something here. We want to use this conductor as the heating coil for a kettle. The heating coil for a kettle. So they connected each of the 3 conductors A, B, and C in a circuit and measured the current passing through the conductor and the potential difference across the conductors. And the results are shown on the graph below, right? Clearly on the y-axis we have the current, and then on the x-axis we have the potential difference. And the first question, 8.1.1, says, name any 2 variables that must be kept constant for a fair investigation, right? So the question really here is, which factors affect the resistance of a conductor, right? If we keep those factors constant, then we have a fair test, right? So those factors, one of them is temperature, right? You need to keep the temperature of all the conductors the same so that it can be a fair test. If you increase the temperature, it has an effect on the resistance, so the test won't be fair anymore. Another factor you need to keep constant is the length of the conductors. If the length is not kept constant, then it's not longer a fair test anymore, because the length of a conductor actually affects the resistance, right? And then another factor you want to keep constant is the thickness. And then 8.1.2 says write down the physical quantity represented by the gradient of each graph. The gospel I've been preaching lately: if you have a graph, you should be able to derive an equation for that graph. Failure to do so, then a lot of issues are going to arise, right? We know fully well that V is equals to I multiplied by R, right? Like we said, in our graph, we have the current as the Y. So let's make I the subject of the formula. So we're going to have the voltage divided by the resistance being equals to the current, right? But then we can rewrite V divided by R, right, as 1 divided by R multiplied by V being equals to I. Clearly, we're saying that I is our y, right? And then 1 divided by r will be our gradient, and then v will be our x, right? So now you can see that the gradient in this graph, it represents 1 divided by r, or you can simply write it in words, the inverse of the resistance. And then 8.1.3 says which one of the following conductors is efficient enough to be used as a heating coil in a kettle? Give a reason for your answer. So the key word here is heating coil, because generally we are looking for conductors that have a low resistance, right? So that we can save energy when we pass current through an appliance. But then in this case, we're looking for a conductor to use it as a heating coil in a kettle. So we need a conductor with the highest resistance, right? Because if it has the highest resistance, then it will convert more of its energy to heat, right? And then if you want a heating coil for a kettle, then that's the conductor you are looking for. So now we're gonna go to a graph and try identify a conductor that has the highest resistance, right? We know fully well that the gradient is equals to 1 divided by r, right? So the conductor that has the highest resistance will have the lowest gradient, right? Because clearly in this equation they're inversely proportional to each other. Between A, B, C, which one has the smallest gradient? Clearly C has the smallest gradient, right? So for 8.1.3, conductor C. And then the reason for our answer, we're saying that for a heating coil in a kettle, you want a conductor with very high resistance so that it can convert more energy to heat. Now let's do 8.2. So 8.2 says that the circuit diagram below represents a combination of resistors in series and parallel. The battery has an EMF of 12 volts and an unknown internal resistance R. And before 8.2.1, we are told that when switch S is open, right, here's switch S here, the reading on the ammeter, so we have some I, which is equals to 1.5 amps, right? And then 8.2.1 says let's calculate the total resistance of the circuit, right? We have internal resistance, so we cannot just use V is equals to I multiplied by R, right? We have to use EMF is equals to the current multiplied by the external resistance plus the internal resistance. The question says let's find the total resistance of the circuit. So we're looking for R external plus internal resistance, right? We have the EMF, it is given to us, and then we have the current, right? It should be obvious what we're gonna do now. So we're going to have 12 being equals to the current 1.5 multiplied by R external plus internal resistance. So we divide in both sides by 1.5, right? So we get R external plus internal resistance being equals to 12 divided by 1.5, which is equals to 8 ohms, right? So R external plus the internal resistance is equals to 8 ohms, and that's the total resistance of our circuit. And then 8.2.2 says let's determine the internal resistance of the battery, right? We know now that R external plus the internal resistance is equals to 8 ohms. So if we can determine R external, then we're going to be able to find R internal. But how can we determine R external? We know fully well that R external is equals to the resistance in series plus the resistance in parallel, right? So now let's actually analyze our circuit. So we have a positive terminal here and we have a negative terminal here, and then the current is flowing from the positive to the negative, right? And then at this point here, there won't be any current splitted, right? Because the switch is open. So the current just keeps on flowing, keeps on flowing, keeps on flowing, keeps on flowing. So basically what we have here is two resistors that are in series relative to the circuit, right? So R external will be equals to 3 plus 4, and then we're seeing that we don't have any resistors in parallel, right? So we're gonna have 0 here, and then that will just be equals to 7 ohms. So now we can say 7 plus the internal resistance is equals to 8. We're substituting R external into this equation here. So the internal resistance will be equals to 8 minus 7, which is 1 ohms, right? So the internal resistance is 1 ohms, and now we can do 8.2.3. 8.2.3 says let's determine the energy dissipated by the 3 ohm resistor in 3 minutes, right? So in order to determine the energy, so we know that the power is equals to the work divided by the change in time, right? So the work is equals to the power multiplied by the change in time. Every time when the question says let's find the energy dissipated, we're looking for the work, right? But then the power can take different forms. The power is equals to I squared multiplied by R. The power is equals to V squared divided by R. The power is equals to V multiplied by I. So depending on the variables you have, right, you use one of these equations to find the power. Clearly, for the 3 ohm resistor, we have the resistance, right, which is 3 ohm, and then we have the current, right? From the current we can calculate the voltage, right, and then use the other equations, but there's no need. So what we're gonna do here, we're gonna use this equation here because we have the variables that allows us to do so. So now the work is going to be equals to the power. In place of the power, we're going to have 1.5 for the current, right, squared multiplied by the resistance, which is 3 multiplied by the change in time, 3 minutes. But we know in physics we talk about seconds, right, not minutes. So we're going to have 3 multiplied by 60. There's 60 seconds in a minute, and then if you punch that in your calculator, you're gonna get 1215 joules, and that is the energy dissipated on that 3 ohm resistor. And now let's do 8.3. 8.3 says switch S is now closed, right? Let's go ahead and close switch S. So here's switch S here, right? And we're closing it. When we close switch S, now the current is going to split here, right, at this point. So we're going to have a proportion of the current going in this direction, and then another proportion of the current going in that direction, right? And then how will each of the following be affected? Write down only increase, decrease, or remain the same. 8.3.1, the total resistance of the circuit. The total resistance of the circuit will decrease, right? Why am I saying so? Because if the current splits here, right, then the 2 ohm resistor and the 3 ohm resistor are now in parallel with each other. So R external will actually be equals to R in series plus the resistance in parallel, right? So this is going to be 4 ohms plus, now the 3 and the 2 ohms are in parallel with each other. So we're going to have 2 multiplied by 3 divided by 2 plus 3, and that is equals to 5.2 ohms. Clearly this is less than the R external we had initially, right? That R external we had initially was 7 ohms. So if we close that switch, the total resistance of the circuit will go down. And 8.3.2 says how will the reading on ammeter A be affected? If V is equals to I multiplied by R, right, and we're saying that the resistance went down, then the current should go up, right? So the reading on the ammeter will increase. If you decrease the resistance, the current goes up. And now let's do last but not least 8.4. 8.4 is saying a conducting wire of negligible resistance is now connected between points X and Y. Before we read any further, let's just go ahead and connect X and Y. So here's X, and then let's connect X to Y, right? And then it goes on to say, as shown on the diagram above, what effect will this have on the temperature of the battery? Write down only increase, decrease, or they stay the same. What effect will this have on the temperature of the battery? So if we connect X and Y, right, we have reduced the resistance. Yeah, because now the only resistor that will be getting current is the 4 ohm, right? So we have reduced the resistance. What we can see first is that R external decreases, right? So R external will decrease. But then what is the consequence of R external decreasing? If R external decreases, then IT, the total current in the circuit, increases. If the total current increases, and we know that V internal is equals to IT multiplied by small r, right? We're saying that the current increases, the internal resistance is the same, so V internal increases, right? If V internal increases, the work done by the battery will increase, and as a consequence, the temperature will also increase. AC generators at coal-fired power stations supply most of the electrical energy needed in our country. True. And then 9.1 says, state the energy conversion that takes place when this generator is in operation. So we know fully well that we have AC generators and DC generators, right? So the way I'm going to answer this question, I'm going to answer the question for an AC generator, and then also answer the question for a DC generator. So for an AC generator, the energy conversion is mechanical energy to electrical energy. And the same is true for a DC generator, right? All generators, they convert mechanical energy to electrical energy. Then all motors, they convert electrical energy to mechanical energy, right? And then 9.2 says, state one structural difference between an AC generator and a DC generator. This one is very tricky. For an AC generator, we have slip rings, right? Let me write it down. Slip rings. And then for a DC generator, we have a split ring. And then for AC, like we're saying, we have slip rings, right? So make sure you find a way to differentiate between the two. AC, slip rings, and then DC, split ring. And then 9.3, draw a sketch graph of potential difference versus time for this AC generator. Clearly label the axis and indicate Vmax on the potential difference axis. So what is an AC generator? An AC generator produces alternating current, right? But then what do we mean by alternating current? The current changes direction every half cycle, right? So if you wanna plot a potential versus time graph, then after this half cycle, you have to change the direction, right? So we go down. And then after this half cycle, we change direction again, and then so on and so on. That's what we essentially mean when we say a generator is alternating the current, right? And then on the y-axis, we will have Vmax, and then here we'll have minus Vmax, right? So this is for an AC generator. It produces alternating current. But then, like I said, we're answering for both, right? So for a DC generator, we producing a direct current, right? So after half a cycle, the current must not change the direction, right? The current only changes the direction if we have an AC generator, right? So here, if I just put this axis here and then we sketch it, after this half cycle, right, we're not changing the direction for a DC generator. We're still keeping the same direction. So on, and so on. So on the x-axis, we still have the time, and then on the y, we have the potential difference, right? And so on. So that's what you sketch when we want the potential versus time for an AC and for a DC. Now let's do 9.4. So 9.4 stories, they're saying that an electric appliance is rated 2000 watts, right? So we know that we measure power in watts. So as soon as I see 2000 watts, I'm writing P is equals to 2000 watts. And then it goes on to say that, we also have another rating, which is 230 volts, right? And then it goes on to say that the appliance is connected to an alternating current power source. Okay, and then what we are asked to do is to calculate the maximum current. So we were looking for I max, right? So here in electric circuits, we know fully well that the power is equals to the voltage multiplied by the current. But then when we're dealing with an AC generator, we have power average being equals to I RMS multiplied by V RMS. In the information that we have the power average and we have the V RMS, right? So with these two, we can find I RMS, and then from I RMS, we can then look for a way to find I max, right? So let me show you what I'm talking about. So in place of power average, we're substituting 2000, right? And then in place of IRMX, that's what we're looking for. So it remains as it is, right? And then in place of VRMS, we have 230. The conceptual physics problem solving is done now. We're just solving the math, right? We're dividing both sides by 230. So IRMS will be equals to 2000 divided by 230, which is equals to 8.6957 amps, right? So now we have the IRMS. We can go ahead and try find the IMAX, right? So what is the relationship between IRMS and IMAX? We know fully well that IRMS is equals to IMAX divided by the square root of 2, right? So in place of IRMX, we have 8.6957, right? Being equals to IMAX divided by the square root of 2. Should be obvious what you're supposed to do now. Should be obvious. So IMAX will be equals to, we cross multiplying, right? So we have that multiplied by the square root of 2, which is equals to 12.30 amps. And then 9.5 says, let's find the peak voltage. So we're looking for Vmax for the output of the generator. So what's the relationship between VRMS and Vmax, right? Very similar to IRMS and IMAX, right? So we're saying that VRMS will be equals to Vmax divided by the square root of 2. We have VRMS, which is 230. Now we're looking for Vmax, right? So Vmax will be equals to 230 multiplied by the square root of 2. And then if you do that arithmetic, we get in 325.27 volts. A crate P of mass 1.25 kgs is connected to another crate Q of mass 2 kgs by a light string. The two crates are placed on a rough horizontal surface. So we know that there's some friction there. and then a constant force F of magnitude 7.5 newtons acting at an angle theta to the horizontal is applied on crate Q. Clearly, right? The sketch demonstrates that. And then the crates accelerate at 0.1 meters per second squared to the right, and then crate P experiences a constant frictional force of 1.8, and crate Q experiences a constant frictional force of 2.2 Newton. And then the first question, 2.1, state Newton's second law of motion in words, right? I'm definitely not going to do that. And then 2.2, let's draw a labeled free body diagram for crate P, right? So let's pay our attention to crate P now. So crate P is connected to crate Q by a string, right? So there must be tension on crate P moving to that direction, right? And then because crate P is lying on a surface, we must have a normal force, right? But then not only a normal force, but even the gravitational force, right? So we should have Fg and the normal force there. And then we are also told that there is frictional force. So let's have a force opposing the motion, right? So let's have F at there. Why is the vector for the frictional force shorter than the vector for the tension, right? It is shorter because the crates are accelerating to the right, right? So the tension, the force of the tension is overpowering that force of due to the friction, right? So we must show that on our length of the vectors. I don't know if I don't know if the examiners are gonna penalize you if your FR is not less than the tension force, but yeah, it's supposed to be less than the tension force because they are moving to the right. We know that they're moving to the right because of that acceleration of 0.1. Anyway, stories 2.1, 2.3, I meant 2.3.1. Let's calculate the magnitude of the tension in the string, right? So we want the magnitude of the tension in the string. In 2.2, we were asked to draw a labeled free body diagram for crate P, right? So let's try finding the tension in the string by using crate P. If we cannot use crate P alone, then we will resort to also using crate Q. So let's try here and see what happens. So we're gonna say for P, right? And we underline it. Why are we doing that, right? It's for the sake of clarity. We're not all over the show. We're showing the examiner that we know exactly what we're talking about. So yeah, let's see what happens. So obviously we have F net equals to MA, being the second law of motion, right? So we start with the bigger force and then we subtract all the opposing smaller forces, right? So here we've already established that the tension is greater than the friction, right? So we must have tension minus all the smaller forces. We only have friction opposing, right? So minus FR being equals to MA, right? We're only considering the forces along the horizontal and not the vertical, right? So we're gonna have tension minus, so the frictional force that acts on crate P is given to us is 1.8. So this will be equals to the mass, which is 1.25 multiplied by the acceleration, which is 0.1. So now the tension is going to be 1.25 multiplied by 0.1 plus 1.8, and that should be equals to 1.925 newtons, right? And just like that, we have the magnitude of the tension. And now let's calculate the magnitude of the angle theta. So the angle theta has to do with our crate Q, right? So now again, Q we underline for the sake of clarity, and we say that F net is equals to MA, right? We leave in the examiner with no doubt. So again, so for crate Q, we're gonna need a free body diagram first before we do this, right? So for crate Q, I'm just gonna draw it here, right? We have the force acting at an angle, right? And then we have the normal, obviously, and then we have Fg, and then we have tension acting, and then we also have frictional force, right? So if we compute that, we're gonna have so we on the horizontal axis, né? We're on the horizontal axis. Since it's on the horizontal axis, we're gonna resolve F along the horizontal. If we want to resolve f along the horizontal on a flat surface, we say f cos of theta, and then we subtract all the smaller forces. So minus tension minus friction shall be equals to ma. So what is f? We know fully well that f is 7.5, and then cos of theta. What is the tension? The tension, we calculated it in 2.3.1, right? So here we're gonna have 1.925, and then for the frictional force is given to us as 2.2. And this will be equals to the mass of 2 kgs multiplied by the acceleration, which is 0.1. So 7.5 cos of theta will be equals to 2 multiplied by 0.1 plus 1.925 plus 2.2, right? We're making cos of theta the subject to the formula. So now it should be easy to see that theta will be equals to cos arc of 2 multiplied by 0.1 plus 1.925 plus 2.2, everything divided by 7.5. Obviously this is more messy, right? It will be more clean if you put this in your calculator first, but yeah, I'm just gonna do what I feel like doing. So theta should be equals to 51.93 degrees, right? And that's how we solve that problem there. A ball is thrown vertically upwards from the top of a building of height 25 meters with a velocity of 12 meters per second. On its way down, the ball passes a door which has a height of 1.9 meters and then strikes the ground as shown in the diagram below. And just like we always do, we can ignore the effects of friction, right? So the first question here is 3.1, which is saying that let's define the term free fall, right? I'm just gonna leave that for you. And 3.2.1 is saying that let's calculate the time taken for the ball to reach its maximum height, right? So let's do a bit of conceptualizing here. So we at the top of the building here, and then the ball is thrown up with some vi, which is equals to 12 meters per second, right? And then the ball goes up until it reaches some maximum height. At the maximum height, we know that we will have a vf, which is equals to 0 meters per second, right? And then what else do we have? We know the acceleration fully well. The acceleration is equals to minus 9.8 meters per second, right, squared. So now we have to decide on the direction. We take in up as positive, right? Hence acceleration is minus 9.8. And what we're looking for, we're looking for delta t. So we have this variable here. We have vf, we have vi, we have a. We're looking for delta t. Which formula can we use? Should be easy to see now that we're gonna say vf is equals to vi plus a delta t. So what is vf? We're saying that vf is 0. What is vi? It's 12 meters per second, right? So we put it as it is without a negative sign because we're taking up as positive, and then plus a, which is minus 9.8, right? Minus 9.8 multiplied by delta t. So now it should be easy to see that delta t will be equals to minus 12 divided by minus 9.8, right? And yeah, if you put that in a calculator, you should get a time of 1.22 seconds, right? Now we can do 3.22. So 3.22 is saying that let's find the velocity with which the ball strikes the ground. So again, we're going to conceptualize and we're going to look at the information we have and see how we can solve the problem. So we're looking for what? We're looking for the velocity, right? So we're looking for some vf, right? We have acceleration, we always do, right? And then what else do we have? So it's coming from the top of a building and then it goes down to strike the ground. So we have a delta y, right? Our delta y will be equals to minus 25. Why minus? We have taken up as positive, so the direction down it must be minus, right? So we have that there, and then we also have the vi. Let's not forget we have Vi that is equals to 12 meters per second upright. So now we have these variables. We have Vf, Vi, A, and delta Y. Which formula can we use? So we're gonna have Vf squared being equals to Vi squared plus 2A delta Y. So Vf squared is exactly what we're looking for. Vi is 12, and then 2 multiplied by A minus 9.8 delta Y minus 25, right? So here, if we take square root on both sides, we should get Vf is equals to 25.1794 meters per second downwards, right? Downwards. Let's put the direction there. Now, the only question that is a bit tricky here, I think, is 3.23. 3.23, you have to be, yeah, you have to be extremely, sober to do this question. So we're looking for the time it took the ball to move from the top of the door to the ground. So let's come to a sketch. So the ball is coming from the top, right? And then we go to some maximum height, and then as we go down, we at the door at some point of time, and then we keep going down until we are on the ground, right? So we're looking for the time that it takes for the ball to move from the top of the door to the ground, right? From the top of the door to the ground. So now let's fill in the information we have and see how we can solve this problem, right? So here we have a Vf, which is equals to 25.1794, right? And then here we also know the acceleration. The acceleration is obviously minus 9.8 meters per second squared, right? And then we have delta Y. We know the height of the door is 1.9 meters. So we have delta Y, and then what are we looking for? We're looking for the time it takes. So we're looking for delta T. So what we can do here, we can calculate the velocity at this point, right? When it's at exactly the top of the door at this point. If we calculate the velocity at that point, we're going to use Vf is equals to Vi plus A delta T. My favorite formula, right? It's pretty much straightforward. So let's calculate the velocity at that point so that we can use that simple formula. So to calculate the velocity at that point, we're going to do exactly what we did at 3.2.2, right? But the only difference here is that delta Y is not 25, but it is 25 minus 1.9, right? Think about it. I'm sure you're going to get it. So we're saying that Vf is going to be equals to the square root of 12 squared, right? Plus 2 multiplied by minus 9.8. We're doing what we did in 3.2.2, right? But then instead of our height being minus 25, right? It's supposed to be 25 minus 1.9, right? But then because then we have a minus, we're just gonna add so that we can have a less delta Y, right? Think about it. I'm sure you're gonna get it. So plus 1.9 here, right? And if we compute that, we're gonna get Vf is equals to 24.4287 meters per second downwards, right? So this Vf that we have here is basically going to be our Vi, right? For the motion from the top of the door to the ground. So now our favorite formula, we can say Vf is equals to Vi plus A delta T, right? We're looking for delta T. So if we solve this and make delta T our subject of the formula, we're going to get delta T is equals to Vf minus Vi divided by acceleration, right? So Vf is the answer we calculated in 3.2.2, right? So that will be minus 25.1794 because we're taking downwards as negative and upwards as positive, and then minus 24.4287, everything divided by 9.8, right? So everything divided by 9.8. So we should get a delta T, which is equals to here we should have a minus. Let's not forget that. So our delta T is gonna be equals to 0.0. So yeah, I think we're supposed to round off to 2 decimal places, so that will be 0.08 seconds. And then yeah, that's how you solve that problem. Obviously there's other ways you can use to solve that problem, but yeah, I'm deciding to go with that one. 3.3, the last question. What does 3.3 say in here? So here we have let's draw a velocity time graph for the motion of the ball from the moment that the ball is thrown upwards until it strikes the ground. Use the ground as 0 reference. Clearly indicate the following on your graph. So let's just have our set of axes first. I'm just gonna do them with a free hand, right? So we just trying to get this over and done with. So we have v here in meters per second, and then we have the time in seconds, right? So we're taking the ground as our 0 reference. Okay, fine. And then we must indicate the velocity at which the ball is thrown upwards. The velocity at which the ball is thrown upwards. It's thrown upwards at 12 meters per second, right? Let's indicate here that we're taking up as positive still. So here at 12 meters per second, our ball is thrown upwards, right? And then it takes 1.22 seconds to reach the maximum height, of which the velocity is 0, right? So here we must have a time which is 1.22, and then from there on, what happens? It changes direction, right? And now we have a negative velocity, so our graph should keep on going down. That line must be straight. The line must be straight. Let me make sure that it's straight. So we have a straight line going there until we reach a velocity of 25.1794, right? With a negative value. So we have minus 25.1794, right? That is the velocity at which we strike the ground, right? And yeah, I think this should be it. Trolley X of mass 1.2 kgs travels at 8 meters per second east and collides with trolley Y of mass 0.5 kg, which is initially at rest. And then the velocity time graph below shows the velocity of the trolley X before, during, and after the collision with trolley Y. And then yeah, we have a fancy sketch there. And then the first question, 4.1, which is saying, let's state the principle of conservation of linear momentum. We'll leave that for you. And 4.2.1. So for 4.2.1, we're looking for the velocity of trolley Y immediately after the collision. So how can we possibly determine the velocity of trolley Y immediately after the collision? We are going to use the principle of conservation of linear momentum, because we know fully well that the sum of the momentum before a collision should be equal to the sum of the momentum after a collision, right? So what is the momentum before a collision? We're going to have the momentum of trolley X plus the momentum of trolley Y, and then after the collision we're gonna have the sum of momentum of trolley X plus the sum of the momentum of trolley Y, right? So if we calculate the sum of the momentum of trolley X, let's not forget that P is equals to M multiplied by V, right? We're gonna have 1.2 multiplied by 8. So now we can see that we need to decide on a direction. So let's take direction to the east as positive, right? And then the trolley, the momentum of trolley Y, it is at rest, right? So we have 0.5 multiplied by 0, right? This will be equals to the momentum after the collision of X. We have 1.2 multiplied by the velocity. The velocity is on the graph, right? Because here, this is the velocity before the collision, during the collision, and then immediately after the collision. So we have 4 then. And then plus 0.5 multiplied by the velocity of trolley Y, right? So without wasting any time here, we're gonna say that the velocity of trolley Y should be equals to, so we have this 1.2 multiplied by 8 there, so we're gonna have 1.2 multiplied by 8, and then this, because we're multiplying by 0, is gonna fall apart, right? And then minus this here, which is just 1.2 multiplied by 4, and then everything divided by the coefficient of Vy, which is 0.5. So if we put that in our calculators, we shall get Vy is equals to 9.6, right? We take in direction to the east is positive, so this will be 9.6 meters per second to the east, right? To the east. And now let's do 4.2.2. So 4.2.2 is saying that let's find the average net force that trolley X exerts on trolley Y during the collision. The average net force that trolley X exerts on trolley Y during the collision. We already know that after the collision, trolley Y is going to move to the east, right? So the direction of this net force should also be to the east, right? Irregardless of the sign we're going to get in our calculation, right? Because the sign is going to depend on which body you use, right? Are you using trolley X or are you using trolley Y? But then that shouldn't have an effect on the magnitude, right? So if we use trolley X, right? So we're going to say F net is equals to delta P divided by delta T. Let me explain why I'm using trolley X instead of trolley Y. The velocity of trolley Y, we calculated it ourselves, right? So what if that velocity is wrong and then we use it again, right? There's a good chance that that answer will also be wrong, assuming that there's no positive marking. So let's just stick to trolley X because we're going to be using the velocities that are given to us. So there's no way we can go wrong with the values, right? Momentum final will be 1.2 multiplied by 4. Minus momentum initial, which is 1.2 multiplied by 8, and then divided by the change in time, which I've indicated here in our graph, right? It happens from 20.1 to 20.2 seconds. So here we're gonna have 20.2 being the final minus 20.1 being the initial. So if I just put that in my calculator, let me see what I get here. I'm getting minus 48, right? But we've already said that we don't care about the sign, right? We know that it's supposed to be 48 newtons to the east, right? To the east. And yeah, I think that's it for 4.2.2. Let's see what we can do for 4.3. So 4.3 here is saying that let's determine if the collision is elastic or inelastic, right? And explain the answer by means of a suitable calculation. So what is the prerequisite for an elastic collision? So if a collision is elastic, then we need two things to be conserved, right? We need the momentum to be conserved and we need the kinetic energy to be conserved. So in 4.2.1, we calculated the value of Y, assuming that momentum is conserved. So it will make sense if we calculate the momentums again, right? Because that's what we're assuming. We're assuming that the momentum is already conserved. So we're just going to calculate the kinetic energy and see if it is conserved, right? Yeah, so let's go ahead and do that. So we're going to say EK before and then calculate that and see if it's equals to EK after. So EK before will be equals to just the kinetic energy of trolley X because trolley Y was stationary. So when I have 1.28 and squared, right? So if I just put that in my calculator, I have 1.2 multiplied by 8 squared. And that is 38.4 joules, right? And then EK after, now I have 1.2 multiplied by 4 squared. Plus, this is for our trolley X, right? Plus the EK for our trolley Y. We have the mass, which is, what is this? The mass again? The mass is 0.5, so we have 0.5 multiplied by the velocity, which we calculated, right? 9.6, and then we square that. So let me just put that in my calculator real quick and see what I get. So multiply by 0.5 multiplied by 9.6 squared, I'm getting 32.64 joules. So since EK before is not equals to EK after, then we deem this collision inelastic, right? Let me start by apologizing because the way I'm going to solve 5.4 is a bit gangster, but let's see what happens. So the question is saying that a 12 kg block is initially at rest at point A at the bottom of a rough inclined plane. So we know that we have frictional force. The block is pulled up the incline by constant force F acting parallel to the incline, so we don't have to resolve the force. The block reaches point B, which is at a vertical height of 4.5 meters above the horizontal, with a speed of 2.5 meters per second. See the diagram below. The first question, 5.1, says that let's define the term non-conservative force, and I'm just going to leave that for you. And then 5.2, we are asked to draw a free body diagram for the block when it is pulled up the incline, right? So let's go ahead and do that. So clearly there, when the block is being pulled up the incline, there's a force F, there's an applied force, right, which is acting parallel to the incline. But then because it's resting on a surface, we must have a normal force perpendicular to the surface, right? And then obviously we're gonna have gravity, right? So we're gonna have weight there, and then since the incline is a bit rough, then let's have frictional force. So we have FR there. Yeah, I think now we can solve 5.3. So 5.3 is saying that calculate the work done on the block by the non-conservative forces when the block moved from point A to B. So we know fully well that work net is equals to the change in EK, right? But then what is another way we can represent work net? Work net can be work done by non-conservative forces plus the work done by conservative forces, being equals to the change in EK, that is 1 over 2 VF squared minus VI squared, right? So we're looking for the work done by the non-conservative forces, right? So we're going to see so let's leave that as a variable. We're going to have the work done by the non-conservative forces plus the work done by the conservative forces, right? The conservative force that is acting there, which we are supposed to calculate the work for, is gravity, right? Since we don't have the length of AB, we're gonna use the height instead, right? So if we use the height, because gravity is gonna be pulling the object down as it is moving up, right, we're gonna put a minus sign there. So we're gonna have the force due to gravity, right? That is the mass multiplied by gravity, the weight, right? And then multiplied by delta x, the height, right? The height is 4.5, right? We've already put a minus sign here, so there's no need for us to say cos of 180, and this is going to be equals to a half. The mass is 12, and then VF is 2.25. we square that to minus 0 squared, right? So now we can say that the work done by non-conservative forces will be equals to, so we have a half 12 multiplied by 2.25 squared basically, plus 12 multiplied by 9.8 multiplied by 4.5, right? So now it's just a matter of putting this in the calculator, and I'm getting 559, I meant 0.575 joules. Let's go ahead and move to 5.4. So 5.4 is saying that the same constant force F now moves the block at a constant velocity. So constant velocity, we know fully well that the work net is going to be equal to 0, right? Because the change in kinetic energy is going to be 0 if we have constant velocity across a rough horizontal surface from point B to point C. So we have friction also, force Fx parallel to the horizontal surface. So force F is still intact, right? And then what else do we have? the magnitude of the constant frictional force acting on the block while moving from point B to C is 42 newtons. Is 42 newtons larger than the magnitude of the constant frictional force acting on the block when it is moved from point A to B. And then let's calculate the distance from A to B. We're going to say that work net is equals to EK, right? The change in EK. But we know that the change in EK is supposed to be equals to 0 because it is moving at a constant velocity. So here, the work net is going to be the work done by the force applied plus the work done by the friction, right? Which is equals to 0 basically. But then we can go ahead and, solve this way further, right? So if we do that, we're gonna get force applied minus the frictional force, right? Multiplied by the distance they're traveling. What is the distance they're traveling? It is BC, right? Multiplied by BC being equals to 0. But this is what I'm going to do here, right? This frictional force that is here, we know that it is 42 newtons larger than the frictional force in 5.3, right? So if we call the frictional force in 5.3 Fx, right? So if we let that frictional force in, so let's write it down. Let's say we let in the frictional force in 5.3 be equals to Fx, right? If we do that, then Fa minus Fx minus 42 will then be multiplied by BC will be equals to 0, right? Clearly from our sketch, BC is not equals to 0, right? But then we don't even have to make that assumption. We can just say BC is equals to 0, or Fa minus Fx minus 42 is equals to 0, right? So Fa, this is Fx, what am I writing? Let's be very precise. This is Fx. So Fa minus Fx is equals to 42 newtons, right? We know that for sure. So we're saying that the force applied minus the frictional force in 5.3 is equals to 42 newtons. Let's go to back to 5.3 so that I can show you something. Here in 5.3, we ended up saying that the work done by non-conservative forces is equals to 559.575 joules, right? But then which forces are we talking about when we say non-consecutive forces? We're talking about the frictional force, which is Fx, right? And the applied force, which is Fa. So here we can change that and instead write force applied minus Fx, right? Multiplied by delta x. Delta x is AB, right? Multiplied by AB is equals to 559.575 joules, right? But then here we say that Fa minus Fx is equals to 42. So we can just replace this 42. So we're gonna have 42 multiplied by AB being equals to 559.575. If we divide both sides by 42, we get AB is equals to 13.32 meters, right? Some learner decides to investigate the relationship between the observed frequency and the frequency of sound waves emitted by a stationary source. The learner moved towards the source at a constant velocity. So we have the velocity of the listener being constant, right? Let's call it x, and then the learner records the observed frequency FL for a given sound source frequency. This process is repeated for different frequencies of the source, with the learner moving at the same constant velocity for each time, right? The graph below shows how the observed frequency changes as the frequency of sound waves emitted by the source changes. And then we have a graph there which we're going to talk about in a moment. But the first question, 6.1. So 6.1 is saying that let's name the phenomenon illustrated by the graph. Question 6, grade 12 physical sciences. If the question says name the phenomenon, it's always Doppler effect, right? So that's the answer for 6.1. We have Doppler. effect, right? Let's move to 6.2. So 6.2 is saying that name one application in the medical field of the phenomenon in question 6.1. So that's we can write ultrasound, right? That's one of the applications of Doppler effect in the medical field. And then 6.3, write down the type of relationship that exists between FL and FS as illustrated by the graph. We can see that they are clearly directly proportional to each other, right? As FS increases, FL increases. So we can say here that they are directly proportional to each other. Right? If you want to go further, you can even say that as FS increases, FL increases, right? Yeah, but then yes, just 1 mark, so this will be sufficient. But then if for instance it was for 2 marks, then you would say that as FS increases, FL increases. Now let's solve the problem. 6.4. So 6.4 is saying that 6.4 in blue, not in purple. So 6.4 is saying that the gradient of the graph obtained is found to be 1.06, right? If the speed of sound in air is, so we have v of sound in air is 340 meters per second. Calculate the magnitude of the velocity at which the learner approaches the source. So we're given the gradient of the graph, right? And so what we're gonna do here, we're gonna look for the equation of the graph so that we can know what the gradient is and find a way to solve our problem, right? So we know fully well that in Doppler effect we have FL being equals to V plus or minus the velocity of listener divided by V plus or minus the velocity of the source, everything multiplied by the frequency of the source, right? In our graph we have FL being the Y, and then we have FS being the X. So this expression here will be our what? Yeah, just like you guessed, it will be our M, right? So if we can take that expression then, and then we can equate it to 1.06 because that's the gradient. So what are we saying? We're saying that V plus or minus VL divided by V plus or minus VS should be equals to 1.06, right? It's not me, it's the question. So now we can substitute our values and solve for VL, right? We're looking for the velocity of the listener. So that V, this V here is for the sound in air, right? So we're gonna have 340. So because we are told that the listener or the learner is moving towards the stationary source, right? Then you must have plus VL, right? And then divided by 340. The sound source is stationary. So we're just going to have plus or minus 0, which is just 0. And this will be equals to 1.06, right? 1.06 is the same as 1.06 divided by 1. So if we cross multiply here, we should get 340 plus VL being equals to 340 multiplied by 1.06. So here it should be easy to see that VL will be equals to 340 multiplied by 1.06 minus 340, right? So VL should be equals to 20.4 meters per second, right? And that's how we solve that problem basically. Now let's do the last problem, 6.5. 6.5 is saying that the investigation is now repeated with the learner moving at a higher constant velocity toward the sound source. Copy the graph above in your answer book and label it as A. On the same set of axes, sketch the graph that will be obtained when the learner is moving at a higher velocity. Label this graph B, right? So this one, they're saying we must label it A, right? And we must draw a graph for when the learner is moving at a higher constant velocity and label it B, right? So let's see what the consequences of a higher constant velocity will be. So we know that we have the gradient being equals to V plus VL divided by V plus or minus 0, basically, right? This is what the gradient of our graph is. But then now the learner is moving at a higher constant velocity, right? So it will be easy to see that if VL goes up, right, the gradient should also go up, right? So for your graph B, you have the same straight line, but then the gradient is just slightly steeper than that one when the learner is moving at a less velocity. So we're going to have our graph here, right? The gradient is just a bit steeper, right? Just steeper than A, and then we label it B. So let's see what the fuss is about. A charged sphere M is suspended from a ceiling by a light, inextensible insulated string. Another charged sphere N of mass 2.04 times 10 to the minus 3 kgs and carrying a charge of plus 8.6 times 10 minus 8 coulombs hangs stationary vertically below sphere M. The centers of the two spheres are 0.3 meters apart, as shown in the diagram below. And then, yeah, we have a fancy sketch there, as you can see. The first question, 7.1, Coulomb's law inverse. I'm just gonna leave that for you, right? We're going to start with 7.2. Let's state whether the charge on sphere M is positive or negative. Let's state whether the charge on sphere M is positive or negative, right? So let's look at what's happening here. We have sphere N, right? Sphere N, it's in the air, right? But we know fully well that there must be some gravitational force acting on sphere N, right? But why is sphere N not going down? That is because sphere N is being pulled up by sphere M, right? So if we say that sphere N has a positive charge of 8.6 times 10 to the minus 8 coulombs, right? Then sphere M here, which is pulling sphere N up, should have a negative charge, right? If sphere M had a positive charge, then sphere N should just easily fall off, right? What's happening here can only happen if sphere M has a negative charge, right? So 7.2, we're saying that sphere M has a negative charge. Then 7.3, we have to draw a labeled free body diagram for sphere N, right? We already have a body diagram. Now we need to just, make it free. So for sphere N, we're saying that we have FG, right? That is pulling it down. And then we have the electrostatic force due to sphere M pulling it up, right? They are balanced. So that is why sphere N is stationary. It's not moving up or moving down, right? It's just hanging in there. Now let's do 7.4. 7.4 is saying that let's calculate the magnitude of the charge on sphere M. Let's calculate the magnitude of the charge on sphere M. So in 7.3 we just drew a free body diagram. In 7.4 we have to determine the magnitude of something. Should be obvious by now, right? We're going to use that free body diagram we just drew in 7.3. From the free body diagram there, we can see that the electrostatic force Fm, right, should be equals to Fg, right? That is why that sphere there is neither moving up or down. So what is the electrostatic force? We know that we're gonna have K, Q1, Q2, everything divided by R squared being equals to Fg, right? So what is K? K is a constant, that is 9 times 10 to the 9. And then Q1, let's make Q1 the charge that we are given, right? So that will be 8.6 times 10 to the minus 8 multiplied by Q2, the charge we are looking for. So we have Q2 here, and then everything divided by R squared. Their centers are 0.3 meters apart from each other, right? So we're gonna have 0.3 meters squared being equals to Fg. Fg is the mass multiplied by the gravity, right? The mass is 2.04 times 10 minus 3 multiplied by 9.8, right? So here, what we're going to do, we're going to jump straight into the answer, right? We're going to say that Q2 is equals to this term here that I'm just, copying. This term here divided by the coefficient of Q2. So this entire term here, basically, right? But without Q2. Yeah, without Q2. So this is what we say in Q2 will be equals to basically, this is one term and the denominator is one term. So if you put that in your calculator, you shall get Q2 is equals to 2.3247 times 10 to the minus 6 coulombs, right? Now let's do 7.5. So we have 7.5, 7.5.1. How does the electrostatic force that sphere M exerts on sphere N compare to that exerted by sphere N on sphere M with respect to the magnitude? So the magnitude is the same, right? The magnitude is the same. The magnitude is the same. The magnitude is the same. The only thing that is different is the direction, right? So I don't know if for 7.5.2 we can just write opposite. I don't know if that will be enough, but I'm assuming it will be enough because there's just one mark there, and we just know that the only difference is that the direction is opposite. Yeah, last question, 7.6. So let's do 7.6 real quick. So 7.6 here is saying that point X is 0.1 meters vertically below the center of sphere N, and then we have a sketch there. You can just see it on the sketch. Let's just solve the problem. Let's calculate the net electric field at point X. So we're gonna say that E net electric field will be equals to the electric field due to charge M plus the electric field due to charge N, right? So now we can say that E net is equals to that will be KQ divided by R squared, right? Plus KQ divided by R squared for the faint-hearted ones. But now let's go ahead and substitute. K is a constant, that is 9 times 10 to the 9. So what is the magnitude of the charge on sphere M? The magnitude of the charge on sphere M is 2.32 times 2.32 times 10 to the minus 6 divided by the distance between M and X, that is 0.3 plus 0.1 squared, right? But then now we have to worry a bit about direction here, right? Because M is negative and N is positive. So let's substitute M with its negative value, right? So M here will be negative, and then we'll substitute N with its positive value. So if we go ahead with that idea, we're gonna have plus 9 times 10. Now we're talking about the electric field due to sphere N. 9 times 10 to the 9 multiplied by 8.6 times 10 to the minus 8. Everything divided by the distance between N and X, right? So that is 0.1. So we have 0.1 squared. And if you put this in your calculator, you should get minus 5.31 times 10 to the 4, right? Assuming that I'm not making any mistakes with putting that in the calculator. But then it says, let's calculate the net electric field, not only the magnitude, right? So now we have to worry a bit about the direction. We know that the SI unit is newtons per coulombs, right? So let's look at our sketch here and then worry about the direction. We know that M is negative, right? And then we know that N is positive. As our answer here is negative, we can see fully well that our sphere M is overpowering our sphere N, so to say, right? So the direction of the electric field produced as a consequence of those two charges there will be towards M, right? 8.2, we are told that the reading on the ammeter is 3.5 amps, right? So we have I being equals to 3.5 amps, right? And then 8.2.1 is saying that let's calculate the total external resistance of the circuit, right? So now let's go to our circuit and do some analysis and see what's happening here. So if we look at our cell here, you will see that we have the positive terminal here and the negative terminal here. So the current flows from positive to terminal, right? It cannot go it cannot bypass through the battery. It has to take the longer route. So the current is going to flow in this manner, right? Here we have a voltmeter, so it's not going to go there, right? And at this point here, right, at this point, the current divides, right? So when the current divides, a proportion of the current is going to keep going through this route here, and then another proportion is going to go down through this route. So because current has divided, we will know fully well that the total resistance in this path will be parallel to the total resistance in this path, right? And then here the current flows as one, so this 4 ohm resistor here is in series, right? So we are asked to calculate the total external resistance of the circuit, right? So that will be given by, so we have R external being equals to RP, the resistance in parallel, plus the resistance in series, right? Let's start with the resistance in series because it's pretty much straightforward. We're gonna have RS being equals to 4 ohms, right? And we're done with that. Now we can calculate the resistance in parallel. So this is how you calculate the resistance in parallel. We say 1 divided by RP is equals to 1 divided by R1 plus 1 divided by RQ, and so on, depending on the paths you have, right? But then this R1 here is not one resistor, it's the total resistance in one path. And then this R2 is not one resistor, it's the total resistance in a path, right? So here you can see fully well that we have two paths, the one with the 3 and the 2 ohm resistor, and the other one with the 1 ohm resistor. So 1 divided by RP is going to be equals to 1 divided by, so let's use this path here, right? So that will be 3 plus 2, the total resistance on one path, plus 1 divided by R2, the total resistance on the other path. What is the resistance on the other path? We only have 1, right? So now from here, we can just go ahead and say RP is equals to 1 divided by 3 plus 2 plus 1 divided by 1 to the minus 1, right? You don't have to think very hard when you get to that step. You can just do it like I'm doing it here, right? So RP will be equals to 0.83333 ohms, right? So now we can conclude and say R external is equals to 0.8333 plus 4 ohms, right? And this will be equals to 4.83 ohms. Yeah, and that's how we essentially solve the problem. Now let's do 8.2.2. So 8.2.2 is saying that let's calculate the reading on V1, right? So let me just remove these lines here. So it's saying that let's calculate the reading on V1. So if you don't know what V1 is going to read, then you're not going to be able to answer this question, right? So now you have to ask yourself, if the voltmeter is connected across the battery and current is flowing to the external resistance, what will V1 read? V1 will read V external, right? And V external is equals to IT multiplied by R external, right? That's how you find V external. If there was a switch somewhere and then that switch is open such that there's no current that is flowing to any external circuit, then V1 would be reading EMF. But then here clearly the current is flowing to the resistors in the external circuit, right? So V1 will read V external. So what is IT? We know that IT is 3.5. What is R external? We know that R external is 4.83, right? So I'm saying 3.5 multiplied by 4.83, and that's giving me 16.91 volts. Let's move forward and do 8.2.3. So we have 8.2.3. So 8.2.3 saying, how will the reading on voltmeter V2 compared to the reading on voltmeter V1? Choose from smaller than, equal to, or greater than. So we have V2, and how does it compare to V1? So let's go to our circuit. We've already established that V1 is going to read V external, right? And then let's look at V2. V2 is connected across this path that is in parallel, right? V2 is going to read VP, right? And V external will obviously be greater than VP, right? Unless if we didn't have this resistor here, then V external was going to be equals to Vp. But then in this case, we have that resistor there. So V external is definitely greater than Vp, right? So V2 is less than that reading on V1. So we can write smaller than here. And yeah, I think that's it. We can move to 8.3 now. So let's do 8.3. So 8.3 is saying that Elena concludes that the EMF of the battery is equal to the reading on voltmeter V1. 8.3.1 define the term EMF. I'm gonna let you do that one. And 8.3.2 is the Elena's conclusion correct? Choose from yes or no. So Elena concludes that the EMF of the battery is equal to the reading on voltmeter V1. That is not true, right? That is not true. So let's say no here, and then we're gonna do the explanation in 8.3.3, right? So define the term EMF, right? So EMF, right, is the reading across on a voltmeter across the terminal of the battery when there's no current flowing to the external circuit, right? Back to what I was saying, if there was no current flowing to these external resistors that we have here, then V1 would be reading EMF, right? But then in this case, current is flowing to those resistors, so V1 is not reading EMF, but it is reading V external, right? That's why 8.3.1 asks you to define EMF. If you know how, if you know the definition of EMF, then you're going to be able to answer 8.3.2 and 8.3.3 because they're just depending on whether you know the definition of EMF or not, right? Yeah, let's move to 8.4. So 8.4, there's already some lines there. So we have 8.4. Let me just erase those. 8.4 is saying switch S is now removed and replaced by voltmeter V2 as shown in the diagram below, right? So instead of switch S here, we have voltmeter V2. We had switch S here, right? But now we have voltmeter V2. How will each of the following change, right? So let's just analyze how the current will flow when we have a voltmeter there. So the current is still flowing from the positive to the negative, right? So it's flowing in this manner, right? But then here, the current is not going to divide because we have V2. We know that voltmeters have very high resistance such that negligible currents a negligible current flows to the voltmeter, right? So we just assume that all the current just ignores the path with the voltmeter, and we keep going. So here we're gonna keep going, and yeah, that's how the current is gonna flow essentially. So this 1 ohm resistor is not playing any part in this instance. So 8.4.1. 8.4.1 says, how will each of the following change the power dissipated by the 4 ohm resistor, right? So here you have to be very careful, right? Because there's 3 equations for power, right, in electric circuits. So I'm gonna use P is equals to I squared multiplied by R, because if I use a formula that has V, then I have to calculate V for when we had the switch S, and then calculate V for when we don't have a switch S, right? And that's just too much work. So I'm just gonna take power as I squared multiplied by R. This just makes our life extremely easy. So yeah, let's analyze what's happening here. So the resistance of the 4 ohm resistor will still be the same, right? Will still be R. So here we are only worrying about the current. If the current has increased, then the power dissipated would have also increased. If the current had went down, then the power dissipated will also go down, right? So let's analyze whether the current goes up or goes down when we have V2 there. The current is going to go down, right? Because let's not forget that I is equals to V divided by R, right? So clearly, when that 1 ohm resistor is no longer in play, the resistance is going to go up, because all those 3 resistors, they're now in series, right? Resistance was initially 4.833, but then now the resistance is 3 plus 2 plus 4, which is equals to 9. So we can see that the resistance has increased. If the resistance is increased, then the current has went down, right? So the power dissipated here should be less than, right? Should have decreased, because initially we had a greater current, but then now current has went down. So here let's have decreases, right? And then 8.4.2, the reading on V1. The reading on V1 is going to increase, right? And then we're going to explain that in 8.5, right? So yeah, so it's one of those questions, 4 marks, you know it's gonna be there, this question, and you must be prepared for it. So what's going on? We know fully well that in our electric circuit, EMF is equals to IR plus I multiplied by the small r, right? V external and V internal, right? So we're saying that R external increased, right, when we put a voltmeter there. When R external increases, what's going to happen? The current is going to decrease, right? We know that fully well. But what will be the consequence of the current decreasing, right? So we're gonna have EMF being equals to I multiplied by R plus I multiplied by the small r, right? When the current decreases, this V value here is going to also decrease, right? V internal is going to decrease when the current decreases, right? Because small r doesn't go up or go down, right? It's the consequence of the material used on the battery. So we're saying that V internal is going to decrease. But then at the same time, EMF cannot go up or down. It remains the same, right? So if we're saying that V internal decrease, then we need V external to increase, right? And then V in external is being read by voltmeter V1, right? So that is exactly why we're saying that the reading on voltmeter V1 is going to increase. You will have to excuse the way my question paper looks here, but yeah, it is what it is. So the first question, 9.1.1, is saying that let's name the component in this generator that ensures that the induced current in the external circuit is in one direction only. Name the component in this generator that ensures that the induced current in the external circuit is in one direction only. That is the split ring that we have here, right? So 9.1.1, we have split ring. Now let's do 9.2.2. 9.1.2. 9.1.2 is saying that is the direction of the induced current from X to Y or from Y to X, right? I will let one of you let me know in the comment, and then I will pin that comment, right? So please leave a comment there and let me know whether the induced current is flowing from X to Y or from Y to X, and why you are saying so, right? Now let's do 9.1.3. So now 9.1.3 is saying that a maximum voltage of 90 volts is generated when the coil is rotating at a frequency of 20 Hz. Let's write down the time taken for the coil to complete one rotation. So we have frequency being equals to 1 divided by the period, right? Grade 10. So if we rearrange this formula, we should get the period being equals to 1 divided by the frequency. So this should be 1 divided by 20. And if I put that in my calculator, I'm getting 0.05 seconds, right? So that is the time taken for the coil to complete one rotation. Let's move to the next question, 9.1.4. So 9.1.4 is saying that the coil starts rotating from the initial position as shown in the diagram above. Sketch a graph of output voltage, current versus time for one complete rotation of the coil. Indicate the maximum voltage and the relevant time values on the graph. So let's sketch our axis here and see what we have. So we have our Y and we have our X. So on the X we have time in seconds, and then on our Y we have voltage in volts, right? So we can just leave that like that then. So we only want one complete rotation. So this is DC, right? So we shouldn't see anything like this manner because it's DC. It should look like this, right? So we change direction, we go up again, and we have one complete circle. So this time here should be 0.05, right? Because in 9.1.3 we say that it takes 0.05 seconds to complete one rotation, right? What else do we have to indicate here? We must indicate the maximum voltage. We must indicate the maximum voltage. So on the y-axis here, we're gonna write the maximum voltage is 90 volts, right? So we're gonna have 90 volts here. So this 90 volts will be in line with that part there, just like I showed you with my line. You can see my graph is a bit, sloping up, but yeah, it should be a straight line. And then 9.2, the last question, the wall sockets supply RMS voltage and current. Okay, 220 volts AC voltage is applied from a wall socket to an electric kettle having a resistance of 32 ohms. Let's calculate the average energy dissipated by the kettle in 2 minutes. So we have the power being equal to the work divided by the time, right? If you want to find the energy dissipated, you say the work equals to the power multiplied by the time. So the power can take different forms, right? Depending on what you have. Here we have the voltage and the resistance. So the power will take the form P is equals to V squared divided by R, right? So the energy dissipated will be V squared divided by R multiplied by delta time. So what is V? V is 220 volts. So we square that. R is 32. And then the change in time is, what is the change in time? Change in time is 2 minutes. So we have 2 multiplied by 60. Now, if I put that in my calculator, so I have 220 squared divided by 32 multiplied by 120. And I'm getting 181,500 joules. Light is incident on the cathode of a photoelectric cell connected to a battery and a sensitive ammeter as shown below. And then 10.1, so we have 10.1 here saying that what conclusive evidence about the nature of light is provided by the photoelectric effect. The photoelectric effect proves that light can act as a particle, right? So that's 10.1. The photoelectric effect proves that light can act as a particle. Now let's do 10.2. So for 10.2 here, the first question is saying that let's define the work function, right? So I'm just going to leave that for you. You're going to define the work function, and I'm going to go ahead and do 10.3. So 10.3 is saying that light of frequency 5.96 times 10 to the 14 hertz. It's shown on the cathode. And then let's calculate the maximum kinetic energy of an electron ejected from the cathode. So we given the work function, we given the frequency incident. So if we have the frequency incident, then we can calculate the energy, right? What else do we have? That's all we have, and we need EK max, right? So we know the formula we're gonna use here. We're gonna say that the energy is equals to the work function plus EK max plus EK max. But what is the energy? The energy is given by H multiplied by F being equals to the work function plus EK max, right? So if we make EK max the subject of the formula from just the get-go, we're gonna get H multiplied by F minus the work function, right? So what is H? H is a constant, that is 6.63 times 10 to the minus 34, and H is also given to us, that is the frequency of the light, right? 5.96 times 10 to the 14 hertz minus the work function, which is 3.42 times 10 to the minus 19, and that should be equals to 5.3148 times 10 to the minus 20 joules, right? EK max is in joules. So let's do 10 point. So we're at 10.4 already. So let's do 10.4 here. So 10.4 is saying that the ammeter registers a constant current. So we have some I, which is equals to 0.012 amps, right? Calculate the minimum number of photons of light that strike the cathode in a 10 seconds period. So we have delta T being equals to 10 seconds. So we know fully well that the current is the rate of flow of charge per unit time. The rate of flow of charge per unit time through a point or a region, right? So what are we saying? We're saying that I is equals to the charge divided by delta T. But what is I is given to us is 0.12, and then what is the charge? Let's look for the charge. So it seems like what we have to start with here is looking for the charge, and then divided by, this is 0.012, not 0.12, so 0.012 divided by the time. The time is 10 seconds, right? So if we cross multiply here, we're gonna get Q being equals to 0.12 coulombs, right? So we have Q, which is 0.12 coulombs. Let's not forget our aim here. The question is saying, let's calculate the minimum number of photons of light that strike a cathode in a 10 seconds period, right? We know fully well that in photoelectric effect, one photon ejects one electron from the metal surface. So if we calculate the electrons here and we find that the electrons are, we have 100 electrons, then that means that the minimum number of photons is also 100, right? Because we need one photon to eject one electron. So let's calculate the number of electrons, aka the number of minimum photons required in this instance, right? So how do we calculate the number of electrons from the charge, right? You say that the number of electrons will be equals to the charge divided by the charge of an electron, right? So let's just put small letter q there. So if we do that computation, we're gonna get 0.12 divided by the charge of an electron. So what is the charge of an electron? The charge of an electron is 1.6 times 10 to the minus 19. So our answer here should be 7.5 times 10 to the 17 electrons, right? So the minimum number of photons is also equals to 7.5 times 10 to the 17. The last question, 7.5 is saying that the intensity of the incident light is now increased. How will this change affect the reading on the ammeter? Choose from increase, decrease, or remain the same. Explain the answer. So the reading on the ammeter will increase, right? The reading on the ammeter will increase if we increase the intensity. So let's say we had 3 photons that are going to be incident on the surface of the metal, right? If we increase the intensity, then we're increasing the number of photons that will be incident. So let's say, from instance, we had 3 photons initially, and now we have 6. And we know fully well that each of those photons will eject an electron from the surface of the metal, right? And when an electron is ejected from the surface of the metal, that is current. Current is gonna increase, right? I is equals to Q divided by T.
1.1 says that a car is moving at a constant velocity. Key phrase, constant velocity. Before we even go any further, what is the consequence of constant velocity? If we have constant velocity, the acceleration is 0, right? And then if we have 0, we know that F net is equals to ma, so the net force is also 0. Right. Which of the following statements about the forces acting on the car is always correct? A says there's a non-zero net force acting on the car. No, the force cannot be non-zero because the acceleration is 0. If the acceleration is 0, the force must also be 0. And then B says the normal force acting on the car is equals to the weight of the car. That is not always true. And then C says there are no forces acting on the car. and this is the net force acting on the car is 0, right? And that's exactly what we said, that when we have a constant velocity, A acceleration is 0, and we know fully well that F net is equals to ma. So we're going to have A multiplied by 0, so F net is 0, right? So our option here is D. 1.2 says the force diagram below shows the forces acting on a box. We have a force applied, we have the normal force pointing up, and then we have gravitational going down. And then it says which of the following equations for the magnitude of the normal force Fn is correct. Our force applied is acting down, right? So let me just have a free body here. So we have the normal, we have the Fg, and then we have the force applied, right? So you can write the force applied like that, or you can do it like this, right? So we have our F applied here, and then nothing is said about the object moving up or down, right? So that tells us that the forces acting on the object along the y-axis are balanced, right? So which forces are acting up? It's only the normal. So the normal is supposed to be equals to Fg plus the y component of F, so that the object is not moving up or down. So we're going to have the normal is equals to F applied, right? Multiplied by, how do we find the y component on a flat surface? We use sine. So sine of theta plus Fg. This is the normal force for this object, and that seems to be option B. So our answer for this question is option B. If the force was acting up, right, we're going to have normal plus F sine theta, right, is equals to Fg, and then the normal would be Fg minus F sine theta. Yeah, usually the question is either the force is acting down or going up, so it's better to know what to do on both cases. And then 1.3 says an object of mass m2 attracts another object mass m1 with the force F. So F is equals to m1 m2 divided by r squared, right? And then we have our gravitational constant. And then now we are told that if the mass m2 is doubled, the force m2 exerted on m1 will be. So we have to find the new force, right? So this is F old, and then now we want F new. And then when we're done with finding F new, how does F new compare with F old, right? So F new will be G, the mass of M2 is doubled, so it will be M1 multiplied by 2M2 divided by R squared, right? So this will be equals to 2 M1 M2 divided by R squared, right? So clearly this is F old. So we're saying that F new is equals to 2 F old, which is option number C. So let's go see that. And then 1.4 says that the velocity versus time graph below presents the movement of an object that is initially projected vertically upward. Ignore the effects of friction. The maximum height that the object reaches above the projection point, the projection point is given by, and then we have a few options. So this is our vi, right? And then our v final is 0, obviously, at maximum height, and the time there is time t. So if you want to find the maximum height, you're gonna use the height is equals to half base times height. You calculate the area of the VT graph, right, all the time. So that will be equals to a half. The breadth is the time, right? So t, and then the height we have v. The breadth is from 0 to t here, right? And then the height is from 0 to v. So we just have a half t multiplied by v, and then that seems to be option A. It says a half vt instead of tv, but then that is still perfectly fine. 1.5 says that a black and red snooker ball are stationary and in contact with each other on a smooth table. A white ball with the same mass m as the other two moves towards the black ball on the line of contact of the black and red balls with a velocity v. It collides elastically with the black ball and stops. So elastically, what does this tell us? This tells us that not only is momentum conserved, but kinetic energy is also conserved, right? So if kinetic energy is conserved, 1 over 2 mv squared before is supposed to be equals to 1 over 2 mv squared after, right? That's what we know about conservation of kinetic energy. So we are told that after the white ball strikes the black ball, it comes to a stop. Okay, let's just underline that. And then now the question is saying the velocity of the three balls directly after the collision will be. The white ball comes to a stop, so we're supposed to have a velocity of 0 for the white ball, right? That's not negotiable. So now the only options that can be true is B and C. A and D are ruled out because the white ball didn't stop for A and D, right? So after the white ball collides with the black ball collides with the red ball, right? And then for the velocities of the red ball, we have a half v here and v. But we know that the white ball was moving at a velocity v, right? So it had a kinetic energy of 1 over 2 mv squared. So we need the red ball to end up with a kinetic energy of 1 over 2 mv squared, right? If we take this value here of 1 over 2 v, we're gonna have, let me write it here, 1 over 2 the mass, and then in place of v we have 1 over 2 v squared, and this will give us 1 over 2 m multiplied by 1 divided by 4 v squared, which will be equals to 1 divided by 8 mv squared. So the kinetic energy will not be conserved anymore if the red ball moves with a velocity of 1 divided by 2v. But then if it moves with a velocity of v, then we'll still have 1 over 2 mv squared. And then EK before will be equals to EK after. So our answer for 1.5 is C. Let's move to 1.6. 1.6 is 2 boxes X and Y have the same mass. Box X is lifted through a vertical height by a force of magnitude F, and then box Y is pulled up a slope by a force of the same magnitude to reach the same vertical height as shown. And then which statement is correct? A says also we have changing gravitational potential energy of the boxes and the amount of work done by the boxes. So A says the change in the gravitational potential energy of the boxes is the same. So let's look and see if that is true. So for box X, the potential energy will be from 0 to mass multiplied by gravity multiplied by height. And then for box Y, we essentially have the same thing, right? The mass is the same, the gravity is the same, and the height is the same. So option A and B are still safe, but C and D cannot be correct because we have different gravitational potential energies for the boxes. Now we have to look at the work. Is the work for box Y more than that of box X, or are the works done the same? Let me erase this so that we can look at what's going on here. So let's calculate the work for box X. So the work for box X will be equals to the force multiplied by the change in position, right? So we just have F multiplied by height, and then let's go to box Y. The force is not the force, but the work. The work is equals to the force multiplied by the change in position. The force is applied are said to be the same, right? F. But then the change in position of box Y is the hypotenuse, right? Hypotenuse. And we know that the hypotenuse will always be greater than any of the other two sides of the triangle. So the work done on box Y is more than that done on box X. So 1.6, I'm going with A. And then 1.7 says two identical isolated insulated conducting spheres A and B carry equal charges. They are separated by a distance d and exert a force with magnitude F on each other as shown below. And then a third identical uncharged sphere touches A and is then removed. Okay, so we have F being equals to Q of A plus Q of B. Actually, that is wrong. So we have F being equals to Q1, Q2, and then divided by R squared. Here we have K, obviously. So this is our F old. Now we want an F new, right? Before we find our F new, it is said that sphere C, that is uncharged, touches A, right? So Q new of sphere A and sphere C after they touch will be Q of A plus Q of sphere C divided by 2. But we know that sphere C is uncharged, so it's just Q of A divided by 2. So what we're going to have here, we're going to have F new being equals to K. Let's say Q1 is QA, right? So we're going to have QA divided by 2 multiplied by Q2, everything divided by R squared. So let's write that nicely. So we basically have QA Q2 divided by R squared, everything divided by 2. So our option here for that would be A. Let's look at 1.8. In the circuit diagram below, X is a variable resistor or rheostat, and Y is a resistor with a fixed resistance. The internal resistance of the battery and the resistance of the wires are negligible, while the voltmeters have a very high resistance. As always, what happens to the readings on voltmeter Vx and Vy respectively if the resistance of resistor X, our rheostat, is increased? So V is equals to I multiplied by R. We are interested on Vx, right? And then we are saying that we increasing the resistance of Vx, right? So since Vx is directly proportional to R, if we increase R, Vx should go up, right? So A, B, C, D, Vx is increasing for option C and option D. So now we have to look at Vy. This one option is saying Vy decreases, and then the other option is saying Vy remains the same. But then it cannot remain the same. That is because Vt is equals to V1 plus V2 and so on, right? So if V is 6 and V1, let's say Vx plus Vy. If Vx goes up, Vy has to go down so that Vt can remain 6, right? If Vy goes up and then if Vx goes up and then Vy remains the same, then the voltage is no longer constant, and we know that the voltage remains constant on an electric circuit. So our option here for C is that it will decrease, right? If you want to go deeper and think about how it's actually going to decrease, that will be because when we increase the resistance on X, right, the current will go down because I is equals to V divided by R. The current went down for resistor Y, right? So Vy is of a less current but same resistance. So the value is supposed to ultimately go down. Let's move to 1.9. 1.9 says choose the option that correctly differentiates between an AC generator and a DC motor. So AC, we talk about slip rings, and then DC, we talk about split rings, and then AC, we talk about mechanical to electrical, and then DC, we talk about DC motor, we talk about electrical to mechanical. Every motor, we talk about electrical to mechanical. Even in AC motor, we're talking about an electrical to mechanical. So A says AC generator converts mechanical to electrical. That is true. And then with the aid of slip rings, that is true. And then for the DC motor, it says electrical to mechanical, which is true. And then it says with the aid of slip rings, which is wrong. So A cannot be the answer. And then B, the AC generator is converting electrical to mechanical. This is wrong. We don't have to look at anything else. And then option C says is converting electrical energy to mechanical. This is also wrong. So we cannot look at it. And then option D says it converts mechanical to electrical with the aid of slip rings. Correct. And then for the DC, it says it converts electrical to mechanical with the aid of split ring commutator. So our option here for 1.9 is D. Let's look at 1.10. The following graph shows 4 different results, W, X, Y, and Z, from an experiment involving the photoelectric effect. And then we have a graph there. So in photoelectric effect, if you have a graph, before you do anything else, derive an equation for that graph, right? So clearly here we have EK max, the maximum kinetic energy, on the Y, and the frequency on the x-axis, right? So that frequency on the x-axis, is it the applied frequency or is it the threshold frequency? Let's derive an equation. We know fully well that the energy is equals to Planck's constant multiplied by the frequency, right? Another way, you can have Planck constant multiplied by the threshold frequency plus EK max, right? So these two here are equal to each other, and that's how we can derive our equation. So we know that EK max is supposed to be our Y, right? So if we rearrange this equation, we're gonna get EK max is equals to H Planck's constant multiplied by the applied frequency minus Planck constant multiplied by the threshold frequency. So if you look at this equation, the applied frequency can be the X and the threshold frequency can be the X. But clearly, if you make the threshold frequency the X minus H, Planck's constant here will be M, right? So your graph is supposed to slope down, have a negative gradient. But then clearly here the graph is sloping up. So F is what's on the X, and then the gradient is Planck's constant. Now we have an equation in the form Y is equals to mx plus c, right? So when x is 0, we're gonna be left with minus fo, which is our work function, right? So if we extend this graph here, w will go and pass through the graph, and then x will pass through the graph, and y will do the same. So w, x, y, z, we have different work functions, right? We can only have different work functions if we have different materials. Now let's look at our equation. Which one of the following best describes the 4 lines on the graph? The lines are for the same material. If you have the same material, you should have the same work function. So same material is not true because we have already established that we have different work functions. And then B is also not true. C and D are the only possible candidates, right? Because it says different materials. all with different threshold frequencies. This is true. If the materials are different, they are most likely to have different threshold frequencies, right? But then, as you can see here, the y-intercepts of W, X, Y, Z is not the same, right? So they have different frequencies, and that they are different materials. A block of mass 24 kg is on a rough horizontal table. As soon as I read rough horizontal table, I know that there's some frictional force acting on the block, right? And then it goes on to say a force F is applied to the 24 kg block at an angle of 35 degrees to the horizontal. The 24 kg block experiences a force of friction of 7 Newton as it moves. We are even given the frictional force, right? It goes on to say that the block is connected by a light inextensible rope which passes over a light frictionless pulley to another block of mass 12 kg, clearly indicated on the sketch, which hangs vertically as shown in the diagram below. And we are told to ignore the effects of air friction, as we always do. And then it goes on to say that the 24 kg block moves to the left at a constant velocity. So the 24 kg block is moving to the left. Let's just indicate that. And then now 2.1 says, state Newton's second law of motion. We know that F net is equals to ma, and if we make a the subject of the formula, we get a is equals to F net divided by m. So clearly here, if you apply a F net on an object, the object will accelerate in the direction of the net force with an acceleration that is directly proportional to the applied force and inversely proportional to the mass of an object, clearly. And then you can also say that F net is equals to delta P divided by delta T. That is Newton's second law in terms of momentum. And it will say that the net force acting on an object is equals to the rate of change of momentum of the object. And then now we can move to 2.2. 2.2 says, what is the resultant force acting on the system? If you pay attention to this statement here, it says that the 24 kg block moves to the left at constant velocity. Constant velocity implies that our acceleration is equals to 0. If acceleration is equals to 0 and F net is equals to ma, then F net is equals to 0 newtons. So 2.2, we have 0 Newton. And then now we can move to 2.3. 2.3 says, draw a fully labeled free body diagram to all the horizontal forces acting on the 24 kg body, right? So that's our free body diagram there. And then we have the tension as a consequence of the string attached to the 20 kg block, right? And then we also have friction that is going to the right because our object is said to be moving to the left, right? And then our force applied is supposed to be moving to the left, right? So we have force applied here. I'm trying to make the error of the force applied to be equals to the tension plus the friction, right? Because these forces are balancing out. As a consequence, our object is moving at constant velocity or with an acceleration of 0. So now we can go to 2.4. Before we go to 2.4, if you want to support the channel, please check the link on the description there. And then 2.4 is saying calculate the tension in the rope, right? For our 24 kg block, we don't know what the tension is. We know what the friction is, but we also don't know what the force applied is, right? But for our 12 kg block, let's have a free body diagram for our 12 kg block. We have the tension that is pushing up, and then we have the weight that is pushing down, right? And then we know the weight, obviously, because we have the mass. The only unknown variable is the tension. So here, clearly, it will be easier for us to use the 12 kg block to find the tension versus the 24 kg block, right? Because on the 24 kg block, at this point, we have two unknown variables. So for the 2 kg block, so I'm writing 2 kg, we have F net equals to the mass multiplied by the acceleration. So it's just two forces, the weight minus the tension is equals to ma. These two forces are said to be equal, right? So the order really doesn't matter, but usually I start with the bigger force and subtract all the other forces. So what is the weight? The weight is 12 minus 9.8 minus tension being equals to this is 12 kg, not 2, being equals to 12 multiplied by 0, because we know that it's moving at a constant velocity. So we're going to have minus tension being equals to minus, let me just put that in my calculator real quick. I don't want to embarrass myself, right? So we have 12 multiplied by 9.8, that is 117.6. So our tension is basically 117.6 newtons. It says let's calculate the tension, right? So we can put a direction here. So for the 12 kg block, it will be to the left, right? And then for the 24 kg block, it will be to the right. Yeah. So let's do 2.5. 2.5 says let's calculate the magnitude of force F. So now if we come back to our free body diagram for the 24 kg block, now this unknown variable of tension, we now have it, right? So we have tension, we have friction, we just need Fa. So again, we're gonna say 24 kg, and then we have F net equals to ma, and then force applied, we're saying that it's supposed to be equal to the tension plus the friction, right? So it's bigger than those individual forces. So we're gonna have F applied cos of 35 plus minus tension minus friction is equals to ma. Now let's talk about this cos 35. So the force applied is at an angle of 35 degrees to the horizontal, right? We want to resolve it to the x along the x-axis. On a flat surface we use cos, and then on an incline we use sine. Clearly we on a flat surface here, so that's why we're saying Fa cos of 35. So it will be Fa cos of 35 minus 117.6 our tension, and then minus 7 is equals to 24 multiplied by 0. Why am I saying minus 7? Look here, we are told that the frictional force is 7 Newton, right? So from here, what are we gonna have? We're gonna have Fa cos of 35 equals to 24 multiplied by 0 is 0, right? And then we take in minus 117.6 and minus 7 to the right hand side. We're gonna get 124.6. We divide both sides by cos of 35. So 124.6 divided by cos of 35. So I'm getting a force applied here of 146.1343 newtons to the left. We are only actually it's not to the left, it's at an angle of 35 degrees, right? Yeah. Plus even the question only needs us to find the magnitude of force F. So 2.6 says force F is now removed. Does the magnitude of the normal force increase, decrease, or remain the same? So let's find a formula for the normal force so that we can see what happens. So here on our object, when we're talking about the normal force, we now pay attention to the forces acting on the vertical, right? The normal force is pointing up, obviously, and then we have the weight going down, and we have F applied to the Y, right? So clearly from these forces, the normal force is supposed to be equal to the weight plus FAY. So if you remove this force, the normal force goes down. Clearly, the normal force will go down. So here we're gonna have decrease. So let me show you something. It will not always go down when you remove a force. Let's say this force, the force applied was acting up, right? Then we're gonna have the normal force, and then F applied Y, and then down we still have weight. So from this sketch here, we're gonna have the normal plus FAY equals to the weight. So the normal is equals to the weight minus FAY. Clearly in this case, if you remove FAY, the normal would go up. Moons. Neptune's largest moon, Triton, circles his planet in a direction opposite to the planet's rotation. The mass of Triton is 2.139 times 10 to the 22 kgs, and it has a diameter of 2,706 kilometers. And then 3.1 says state Newton's universal gravitational law in words. We know that by formula F is equals to G m1 multiplied by m2 divided by r squared. We can see from the formula here that every body in the universe will attract every other body with a force that is directly proportional to the product of their masses and inversely proportional to the square distance between them. And then now we can go to 3.2. 3.2 says calculate the gravitational acceleration an object will experience on the surface of Triton. So we want the gravitational acceleration. What is the formula of the gravitational acceleration? This is one of those formulas that you will most likely forget, right? But then it is said to be the gravitational acceleration will be equals to G m divided by r squared. This capital letter G being the gravitational constant, and then the mass is the mass of the object of interest, and then r is the radius of that object. In this instance, we're talking about Triton, a moon that is rotating around Neptune. So what do we have here? This will be equals to 6.67 times 10 to the minus 11. That is the value of G. And then the mass of Triton is said to be 2.1390 times 10 to the 22 kg. Now we have to pay our attention to the radius, right? We are told that the diameter of Triton is 2,706 kilometers, but then radius is only half of the diameter, right? So we're gonna have 2,706 divided by 2. We want the radius and not the diameter. But then hold on, the diameter is given to us in kilometers, so it's our job to convert it to meters. So we're gonna multiply this by 1,000. That is because in 1 kilometer we have 1,000 meters. So we're gonna square that, and then let me punch that in my calculator. So we have 6.67 to the minus 11 multiplied by 2.139 to the 22 divided by 2,706 divided by 2 multiplied by 1,000 squared, and that is 0.7794 meters per second squared, right? And then that's about it. we can move forward and go to 3.3. 3.3 says, if the space agency sends a robotic spacecraft of mass 15,000 kg to Triton, calculate the force of attraction when the robotic spacecraft is at a height of 50 kilometers above the surface of Triton. So we know fully well that F, like we have already said, is equals to G m1 m2 divided by r squared. So F will be equals to G is our universal gravitational constant, right? Which is 6.67 times 10 to the minus 11. And then we want the force of attraction between Triton and the robotic spacecraft, right? So let's say M1 is the mass of the spacecraft, which is 15,000. And then M2 is the mass of Triton, which let's do question 4. Question 4 says that a ball of mass 50 gram is thrown vertically downwards with a kinetic energy of 2,704 joules from a point P above the ground as shown below. At the same instant, a second identical ball Y is dropped from a point Q, which is located below point P. Ball Y strikes the ground with a velocity of 19.6 meters per second. Both balls hit the ground at the same time. Ignore the effects of friction and take downward direction as positive. Okay, fine. 4.1 says define the term free fall. Free fall is the motion of an object when the only force acting is gravitational force. The motion of an object when the only force acting is gravitational force. And now we can move to 4.2. So we're taking down as positive, right? We are instructed to do so. Usually take up as positive, but hey. 4.2 says calculate the time taken for ball Y to reach the ground. So let's pay our attention to ball Y. We are told that at the same instant, a second identical ball Y is dropped from a point Q. So if it's dropped, we know fully well that VI is equals to 0 meters per second. And then it goes on to say ball Y strikes the ground with a velocity of 19.6 meters per second. So VF is equals to 19.6 meter per second, right? So we have VF, we have VI, we always have acceleration, and we need delta T, right? The time taken to reach the ground. Now the question you ask yourself, which formula has all these four variables? Clearly, that is VF is equals to VI plus a delta T. What is VF? VF is 19.6. The velocity at which it strikes the ground. What is VI? It was dropped. Every time when a ball is dropped, its velocity initial will be 0, and then plus 9.8 because we're taking downward as positive, multiplied by delta T. So basically, we divided both sides by 9.8. 9.8. So 19.6 divided by 9.8, that is 2. So we have delta T being equals to 2 seconds, right? And then that's it for 4.2. Now 4.3 says calculate the speed with which ball X strikes the ground. So let's take our attention to ball X. For ball X, we are asked to find VF, right? The speed at which it strikes the ground. So that's what we're looking for. We can find VI because we are given the kinetic energy, right? So we are told that EK is equals to 2.704 joules. And then VF is our unknown. We have the acceleration, obviously, because we always do. And then we are told that the ball hits the ground, the two balls hit the ground at the same time, right? So we also have delta T. So obviously here we're going to say VF is equals to VI plus a delta T. But before that, we need to determine VI, right? So how are we gonna determine VI? We're gonna say that EK is equals to half mv squared, and then we know that EK is 2.704, which is equals to half the mass is 50 divided by 1000, right? V squared. So dividing both sides by this expression here, we're gonna get 2.704 divided by half 50 divided by 1000, and then now we can take the square root on both sides, right? So there we take a square root, here we take a square root, and you will end up getting a velocity of 10.4 meter per second. And then we know that it's supposed to be going down, right? And then so now we have our VI, and we can go on and determine VF. So VF is equals to VI plus A delta T. What is VF? It's our unknown, right? But we know now that VI is 10.4. Acceleration is 9.8 because we're taking down is positive, and the time is 2 seconds. So we basically have 10.4 plus 19.6, which is gonna give you 30 meters per second. So where do we go from here? 30 meters per second down what? We are only interested in the speed, so we don't have to give the direction, but it doesn't hurt doing so. 4.4 says on the same set of axes, sketch the velocity time graph for the entire motion of balls x and y. So we need velocity time graph. So our velocity is on the y, and then our time, as usual, it's on our x. So we have velocity here in meters per second, and then we have the time in seconds. Let's pay our attention to ball y first. Ball y starts at 0 meters per second when it gets dropped, right? And it goes up to 19.6. So for ball y, how much time does it take? It takes 2 seconds, right? So we can put 2 here. So ball y ends up here. So now we can have our VT graph for ball y. The line is supposed to be straight. And then now let's put our attention to ball x. Ball x starts at 10.4, so somewhere here, right? So it's starting at 10.4, that's the VI, and then it goes up to 30 meters per second, so it's ending up somewhere here. So if we would sketch a graph for ball y, we'd have something like this. The two lines have to be parallel, right? And then yeah, they have to be they have to all be at 2, right? With regards to the time. So that's the VT graph you would get. You would label that this is your x and this is your y. A box is pushed from rest with a constant applied force of 30 Newton over a horizontal surface which has 3 different regions. Each region is 5 meters long and exerts a different frictional force on the box as it moves through. And then we have a diagram there that clearly demonstrates what the statement is saying. It goes on to say that the graph below shows the kinetic energy of the object as a function of the distance from the starting point as the object experiences the constant applied force of 30 Newton. The first region is from 0 to 5 meters, the second region is from 5 to 10, and the third is from 10 to 15. 5.1 says state the work energy theorem in words. The work energy theorem essentially says that work net is equals to change in EK. So what this is telling us is that the work net done on an object is equals to the object's change in kinetic energy. The work done on an object is equals to the object's change in kinetic energy. And then now we can move to 5.2. 5.2 says, use the work energy theorem to show that the gradient or slope of the graph represents the net force experienced by the object. I don't really like these questions that have to deal with graphs. But if you're doing physics, they're gonna come and you will need to know them. On the y-axis, we have EK, right? And then on the x-axis, we have the distance. So in work, energy, and power, we have delta EK and we have delta x. So we need to find a relationship where on the y we have delta EK and then on the x we have delta x. From the work energy theorem, right, 5.1 is hinting us on what we need to use. From the work energy theorem, we know that work net is equals to EK, but we also know that the work net is equals to F net multiplied by delta x multiplied by cos of theta, right? So EK is equals to F net multiplied by delta x multiplied by cos of theta. In our situation here, cos of theta, theta will be 0, right? Because you can see the force that is being applied, that is horizontal. So we're going to have delta EK being equals to F net multiplied by delta x. Cos of theta, if theta is 0, that will be 1, right? Because cos of 0 is 1. So we just have delta EK being equals to F net multiplied by delta x. So now we have EK on our y, and then we have F net as our m, right? Our gradient, and then we have the distance as our x. So here clearly the gradient or the slope will be giving us F net. So here you come and say F net will be our gradient, which you're gonna find by saying the change in EK divided by the change in distance or the change in x. Yeah, this is honestly a very strange question. I've never came across anything like this before I came across this question. Anyway, let's move to 5.3. 5.3 says, calculate the net force experienced by the object in the third region between 10 meters and 10 meters. So F net, we know that we're supposed to find delta EK and delta x, right? So we have F net being equals to EK final minus EK initial divided by, so that's divided by x final minus x initial. So that will be equals to, so we want the net force experienced between the region 10 to 15, right? So for x final, we're gonna have 15 minus 10 because that's our initial, right? Now let's find the corresponding EK values at 10. So if this is 2, if this is 4 here, then this is 2, and then this is 6, and this is 8. So 10 is here. So let's go up and see where 10 is. So 10 is somewhere here, and then now let's look at the y-axis and see how the boxes and the numbers are pairing up. So if we have 40 and here we have 80, so here we have 60, here we have 20, here we have 100, right? So between we are between 80 and 100. So for EK 1 or EK initial, we have 90, right? Now let's come to EK final. So this is 10, 12, 14, so 15 is somewhere here. So let's go up and then let's see where we end up. We end up at around, so this is 160. So this is 180 here. So we have 180. So 180 minus 90, that is 90, right? And then 15 minus 10, that is equals to 5. So 90 divided by 5 is equals to 18, right? So F net between 10 and 15 is 18 newtons. Now let's move forward and do 5.4. 5.4 says, hence determine the magnitude of the force of friction experienced by the block as it moves over the third region. So force of friction. So we know that F net is equals to F1 plus F2 to some Fn, depending on the number of forces you have, right? So on that region, 10 to 15, we know that the F net is 18 Newton, right? So we have force applied minus friction. We're saying minus friction because it opposes the motion, right? So we're going to have 18 being equals to what's F applied? We are told that F applied is 30 Newton. So we have 18 equals to 30 minus Fr. So if we take 30 to the other side, we get minus 12 is equals to minus friction. So this will give us a frictional value of 12 Newton. Then that's 5.4. Let's move to 5.5. 5.5 is saying which region, first, second, or third, offers the largest frictional force. So again, we know that F net is equals to F applied minus Fr, right? One thing, the steeper the slope, the greater the value of F net, right? And then F applied is kept constant. So basically, friction is the one that is determining the steepness of the slope. So where the slope is the steepest, then we have less friction, right? So let's look at our graph here. From 0 to 5, it's pretty much steep, but then from 5 to 10, it's a bit gentle, right? And then 10 to 15 is also very steep. So 5 to 10 is gentle compared to the other parts, right? So there we have the largest friction. So here we're gonna say the second region has the largest friction. I hope you can understand that. And then 5.6 says explain your answer in question 5.5 without any calculation. That's basically what we just did, right? But then another way of doing, we can actually do the calculations, and you're supposed to get a frictional force that is less than that of the region 0 to 5 and the region 10 to 15.
In the diagram below, a small metal sphere A on an insulating rod has a charge of minus 80 times 10 to the power minus 9 coulombs. And then 7.1 says describe the term electric field in words, right? An electric field is a region of space in which an electric charge experiences a force. A region in space in which an electric charge experiences a force. Basically, we're saying that E is equals to F divided by Q, right? That's the formula for electric field. A region in space where an electric charge will experience a force. And then 7.2 says, calculate the number of electrons sphere A has in excess, right? So the number of electrons a sphere will have in excess will be equals to its charge divided by the charge of an electron, assuming it has a negative charge, right? Because if it has a positive charge, then it doesn't have any electrons in excess. In this instance, we're going to have minus 80 multiplied by 10 to the minus 9 divided by the charge of an electron, which is minus 1.6 times 10 to the minus 19. So I'm getting 5 times 10 to the 11 electrons. So this sphere has 5 times 10 to the 11 electrons in excess. And then we are told now that sphere A is now kept vertically above another sphere B of mass 0.01 kg lying on a horizontal insulated surface. The charge on sphere B is plus 120 times 10 to the minus 9. Sphere A is closely brought closer to sphere B in order to pick it up. Ignore the effects of friction. Okay, and then 7.3 says that draw a diagram that shows the electric field pattern between spheres A and B. So sphere A is negative, let's put it here, and then down here let's have sphere B, which is positive. So the electric field on sphere B, which is positive, will be pointing out, while the electric field on sphere A, which is negative, will be pointing towards
itself, right? So let's have something like that. So for sphere A, the electric fields are pointing towards it, and then for sphere B, the electric fields are pointing out, right? And sphere A and B will attract each other. So let's demonstrate that using our electric field lines, right? Yeah, so at the end of the day, you're going to get something like this. If you want to be more precise, sphere B has a greater magnitude compared to sphere A. So you can put more electric field lines pointing out of sphere B, since it has a greater magnitude. And then 7.4 says at a certain height h, sphere B is just lifted off the surface due to its attraction to sphere A. Just lifted off, right? Let's note that, just lifted off. And then draw a free body diagram showing all the forces acting on sphere B at this instance. So let's talk about the keyword just in this statement line. So if it is just lifted off, then that tells us that the force that is lifting it off and the force that are keeping it down, they are very, 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 very close to each other. They are approximately equal. So that's why it is just lifted off for a split of a second, right? So let's look at sphere B and do some analysis. So if sphere B is being lifted off, it's going to be lifted off by the attraction from sphere A, right? So let's have an arrow pointing up here and demonstrate that this is FA on B, and then what's keeping it down is gravity, right? Because it is said to have a mass of 0.01 kg. So let's have FG here. So we need these two lines to be approximately equal to each other because the sphere was just lifted off. And then 7.5 says calculate the height h in the diagram at this instance, right? So we definitely gonna use the free body diagram of sphere B, right? Because that's the only information we have. So we're gonna say that FA on B is equal to FG. So FA on B will be K Q1 Q2 divided by R squared, and Fg will be the mass multiplied by the gravity. So what is the value of K? We know fully well that K is 9 times 10 to the 9. The charge on Q1, let's say Q1 is A, that will be 80 multiplied by 10 to the minus 9. Don't forget, we are only interested on the magnitude of the charges and not the direction. And then for B, we're going to have 120 times 10 to the minus 9. And then we divide everything by R squared. So R in this instance is H, right? So we're going to have H squared, which is equals to the mass 0.01. Gravity is 9,8. Right? So now we're basically solving for H squared. So if we cross multiply, H squared is going to be multiplied with 0.01 multiplied by 9,8, right? And then we're going to end up dividing both sides by 0.01 multiplied by 9,8. So we're going to have H squared being equals to 9 times 10 to the 9 multiplied by 80 times 10 to the minus 9 multiplied by 120 times 10 to the minus 9. And then this, we are going to divide it by 0.01 multiplied by 9,8. So now we can take square roots on both sides, right? So we will say h squared to the power 1 divided by 2 is equals to this entire expression to the power 1 divided by 2. So h will be equals to 0.0297 meters, right? And then let's move to 7.6. And now we are told that sphere A is now placed on the horizontal insulated surface a distance x from sphere B as shown in the diagram below. P is a point between A and B, which is 0.05 meters from B. The magnitude of the net electric field intensity at point P as a result of the presence of sphere A and B is 54.45 times 10 to the 4 nano per coulomb. And then 7.6 say draw a labeled vector diagram indicating the directions of the electric field at point P as a result of spheres A and B. So point P is a point charge, right? So we always assume that it's positive. And then sphere B is positive, right? And then sphere A is negative. So how do point P and sphere B interact? They repel each other, right? That means that the vector of charge B on P will point in that direction. And then how does sphere A and sphere P and point charge P interact? They attract each other. So A on P will be in that direction also. This will be electric field due to B, and this will be the electric field due to A. And let's move to 7.7. 7.7 says calculate the distance x between spheres A and B. So we are given the net electric field and the magnitude of the charges, right? And the distance between the point charge and one charge. So it should be obvious to see that we're going to use E net is equals to EB plus EA, right? So E net is 54.45 times 10 to the power of 4. And then the electric field due to B will be K. I won't substitute anything for K for the sake of space, right? And then the magnitude of B is 120 times 10 to the minus 9 divided by R squared, the distance between P and B, which is 0.05 squared. And then plus K again for the sake of space, the magnitude of A, 80 multiplied by 10 to the minus 9 divided by R squared. So R squared here will be the distance between A and P, right? Let's just put Y there. So let's put Y squared, right? So we are looking for X. You can see that X will be Y plus 0.05, right? So after we found Y, we basically have X. So if we do that, we can take this expression here to the left hand side, right? So we're gonna have 54.45 multiplied by 10 to the power 4 minus 9 times 10 to the power 9. I'm substituting K now, multiplied by 120 times 10 to the minus 9 divided by 0.05 squared. And then this will be equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by Y squared, right? So now I can rearrange this equation in attempt to find Y squared. So basically, if you have A is equals to B divided by Y and you want to find Y, you're going to cross multiply, get AY is equals to B, so Y will be B divided by C. You can see that B on our equation is this expression here, and then A on our equation is this entire expression, right? So let's rearrange it so that we can find Y ultimately. So we're gonna have Y squared is equals to 9 times 10 to the power of 9 multiplied by 80 times 10 to the minus 9 divided by this entire expression. So that's essentially what we're doing there. And then after this, we will take square roots on both sides. So we have Y squared to the power half, and then this entire expression to the power half. Then if you do that, you're gonna get y is equals to 0.08 meters, right? So x will be 0.08 plus 0.05, which is 0.13 meters. 8.1 says define the term EM of a battery. That is maximum energy provided by a battery per unit charge passing through it. Maximum energy provided by a battery per unit charge passing through it, right? And then now we can go to 8.2. 8.2 says calculate the reading on ammeter A1. So now what we have to do, we have to analyze our circuit before we answer any questions. Clearly, this is the positive terminal and this is the negative terminal. Current flows from the positive to the negative, but then it cannot bypass here. It has to take the long road, right? So our current is flowing just like how I'm indicating on our sketch, right? Here at this point it spills because we have resistors in parallel. So here on this question we are told that switch S is now closed, right? Which is situated here, and then the ammeter reading on A2 is 0.3 amps, right? So here on A2 we have 0.3 A, and then it goes on to say that the reading on V2 is 6.8 volts. Now we can attempt to answer our question. You will realize that A1 is in series relative to the second, right? So A1 is going to read I total. So what this question is asking us is basically to find I total, the total current. On this path here, after the current split, right, we have a current of 0.3 A, right? And then what we can do is to find the current that this 20 ohm resistor is going to experience, right? Then the sum of those two will be equals to I total, because the current is only splitting here. A portion will go up and then another portion will go to the 30 ohm resistor. From our definitions, we know that in parallel, the current is different, but the voltage is the same, right? So we can say VP is equals to I multiplied by R. So we're going to calculate VP using the 30 ohm resistor, right? That is because we have the current and the value of that resistor. So that will be 0.3 multiplied by 30, which is going to be 9 volts. So now we know that the voltage that the 20 ohm resistor is going to experience will be 9 volts, right? And then the value of the resistance is 20 ohms. So now we can calculate the current on that line, right? So here what I wrote here is for the 30 ohm resistor. Now we take our attention to the 20 ohm resistor. So we're gonna say again VP is equals to I multiplied by R. We already know VP from the 30 ohm resistor, right? So that will be 9 being equals to I multiplied by 20. So the current will be equals to 9 divided by 20, which is equals to 0.45. Now we know that I total will be equals to 0.3 plus 0.45, which is equals to 0.75 amps. And then now we can move to 8.3. So for 8.3, we are asked to calculate the total external resistance of the circuit, right? Resistance total is always equals to the resistance in series plus the resistance in parallel. So which resistors are in series and which resistors are in parallel? The 30 ohm resistor is in parallel with the 20 ohm resistor, right? And then X is the resistor that is in series relative to the circuit, right? So let's start with the resistors in parallel. So we're gonna say RP is equals to R1 multiplied by R2 divided by R1
plus R2, right? This formula works. You can also do it using 1 divided by Rp is equals to 1 divided by R1 plus 1 divided by R2 and so on. That formula will perfectly work. So here for R1, let's take 20 ohm as R1. So we're going to have 20 multiplied by 30 divided by 20 plus 30. And then if you put that in your calculator, you are going to get 12 ohms, right? So we are done with our resistance in parallel. Now we have to move our attention to our resistance in series. So let's come to resistor X. For resistor X, we know that, so let me just denote here that we're talking about X. We know that it's going to experience IT because it is in series relative to the circuit, and that will be 0.75A is what we calculated in 8.2. And then we know that the voltage is said to be 6.8 volts. So now calculating that resistance becomes pretty much straightforward. So we're gonna have V equals to I multiplied by R. So the resistance will be equals to the voltage divided by the current, right? What's the voltage? The voltage is 6.8 and the current is 0.75. And then when you put that in your calculator, you get 9.06 ohm. So that will be our RS, right? So now we can say R total is equals to RS, which is 9.06 plus RP, which is 12. So 9.06 plus 12 will give you 21.06 ohm. So our resistance total is 21.06 ohm. And then from there we have 8.4, which says calculate the internal resistance R of the circuit, right? The current is the same everywhere in the circuit, right? On the resistors, on the external resistors, and even on the internal resistors, in the internal resistor. So that is why EMF is equals to I, which is the current, multiplied by the external resistance plus the internal resistance. What's the value of the EMF? Is given to us as 18 volts. And then what's the current? We know fully well that the current is 0.75. And then what's the external resistance? That is 21.06 plus R, right? So now what we can do, we can divide both sides by 0.75. So 0.75 and 0.75 cancel out. Now we are left with 21.06 is equals to 18 divided by 0.75. This we have plus R here, we have plus R, I'm making a mistake. So that is 21.06 plus R is equals to 18 divided by 0.75. Now we can make R the subject of the formula, right? We're gonna get the internal resistance being equals to 18 divided by 0.75 minus 21.06. And then if I put that in my calculator, I'm getting the internal resistance to be 2.93 ohms. And then we can move ahead to 8.5. 8.5 is saying resistor X is now replaced with another resistor with a lower resistance. How will the reading on voltmeter V1 be affected by this change, right? So let's go look at V1. V1 is connected across the battery, right? If the current is flowing to external resistors and we have a voltmeter connected across the battery, that voltmeter will read V external. If there's no current flowing to external resistors, then it will read EMF. But then here clearly we have the 20 ohm, the 30 ohm, and resistor X when switch S is closed, right? So our voltmeter V1 will definitely read V external. But we know fully well that V external is equals to current total
multiplied by resistance external. So now resistor X is replaced with another resistor of lower resistance, right? So what's going to happen to resistance external? Resistance external will go down, right? It will go down. So clearly here, when resistance total goes down, V external will also go down. And then we are asked what the reading of the voltmeter will be, right? The change will be decreased, because clearly when resistance external go down, voltage external goes down. And then 8.6 says we should explain our answer in question 8.5 without any calculation. There's something I didn't say when I was explaining the decrease, right? But then now I'm going to touch on it. Maybe the question you're asking yourself is that when the resistance decrease, don't the current increase? That V external will stay the same, right? Because we know that the current is equals to V divided by R. So if we say in R decrease, then why shouldn't the current increase? And then nothing happens to V external. But then the thing is, EMF is constant, right? And then EMF is equals to IR plus I multiplied by internal resistance. So we're saying the external resistance will go down, right? When the external resistance go down, the current will definitely go up, right? But then let's look at this part of the equation here. R stayed the same, and now the current went up, and we need EMF to be constant. So there's no way for V external to increase or stay the same. It has to decrease so that the EMF remains a constant. So even though the external resistance is decreasing, the current will not go up such that V external stays the same or goes up. A simple sketch of a generator is shown below, and then 9.1 says the north and south poles of the magnet remains unchanged. If the coil is rotated in the direction S shown in the sketch, will the induced current flow in the direction as indicated? Answer yes or no. So basically what they're asking us is asking us to determine the direction of the induced current, right? First of all, let's note how the coil is being rotated. The coil is being rotated anti-clockwise, right? And then here is our north pole and here is our south. So with our index finger, we're going to point from the north to the south. Here we are applying Fleming's right hand rule, right? And then after you do that, you're going to pick one side of the coil. Either you're going to pick AB or you're going to pick CD, right? When you're rotating the coil anti-clockwise, CD is going up, right? And then AB is going down. So with your thumb, you decide which side you are taking. If you take CD, then your thumb must face up and your index finger should go from north to south. Let's take CD. So if you take CD, here you're going to have your thumb pointing up. If your index is going from north to south and your thumb is pointing up, and then you turn your middle finger 90 degrees relative to your index, then your middle finger will be pointing from C to D. Let me just use a better pen there. It will be pointing from C to D, right? So the induced current that is given to us on this sketch, right, is not true. So the answer here should be no. It's very difficult to indicate the right hand rule or the left hand rule when I'm making videos like this, but I'll put some notes on the description so that you can see how it works and see why I'm saying the answer is no. And then let's move to 9.2. 9.2 says, is the output voltage AC or DC? The output voltage will definitely be AC. Now, why do we say that? We say that because of the presence of slip rings and not split rings, right? We're saying that because of the presence of slip rings and carbon brushes, right? So it's AC because we have slip rings. And then let's go to 9.3. 9.3 says, what will happen to the output voltage if the coil is rotated faster? So the output voltage when the coil is rotated faster is going to go up, right? So the answer here would be increase. And then another way you can use if you wanna increase the output voltage is to use magnets that are more powerful, right? Or basically increase the strength of the magnetic field, right? And then now we can go to 9.4. 9.4 says, what is the position of the coil relative to the magnetic field when the output voltage is a maximum? That position would be parallel, right? Because when it's perpendicular, that's when voltage is 0, and then when it's parallel, the voltage is maximum. And then we can go to 9.5, which I've been waiting for this entire time. We sort of are using electrodynamics and electrostatics at the same time, right? So here we're told that lights in a household are connected in parallel as shown in the simplified circuit below. So lights or any other appliances, they work as resistors, right? That's just something I want you to note. So we are told that we have two light bulbs rated 100 watts and 220 volts, and then we have another one 60 watts 220 volt 2 respectively connected to an AC source of RMS 220 volts, and then the fuse in the circuit can only allow a maximum of 10 amps, right? And then let's ignore the resistance of the conducting wires. 9.5.1. So 9.5.1 says, calculate the peak voltage of the source. So what is peak voltage of the source? Peak voltage of the source is V max, right? And then this 220 volts that we have here is our VRMS, right? Root mean square voltage. So we're gonna have VRMS equals to V max divided by square root of 2. So what is our VRMS? Our VRMS is 220, which is equals to V max divided by square root of 2. So our V max will be equals to, we multiply in 220 by the square root of 2. So if you do that, I'm getting 311.13 volts, right? I hope you're getting the same thing. And then for 9.5.2, it says calculate the resistance of the 100 watt light bulb when operating at optimal conditions. So let's go to the 100 watt bulb and look at the information we have so that we can answer our question, right? It's rated 100 watt. So we already know that the power average will be equals to 100 watts. What else do we know? We know that it needs 220 volts, right? Because that's given on the rating. So here we're gonna have VRMS being equals to 220 volts. And now what are we looking for? We're looking for the resistance, right? So what is the resistance? When you're working with electrodynamics, instead of having let's say V equals to I multiplied by R, you instead have V RMS and IRMS, and you're gonna use VRMS and IRMS when you calculate in power 2. Right, let me just erase this and we carry on. So now we're gonna have power average equals to VRMS multiplied by resistance squared, right? The only difference is that now we have VRMS instead of just V that we were already using. So now we're gonna have the power average being equals to VRMS squared divided by R, which we're already using in electric circuits, but then instead of VRMS we just had V. So what is the power average? The power average is 100, and then the VRMS is 220, and then we square it and we divide by the resistance. So the resistance will be 220 squared divided by 100. So let me just punch that in my calculator real quick and see what I get. So that is 220 squared divided by 100 is giving me a value of 484 ohms, right? And yeah, I think that's all. We can move to 9.5.35 marks. So we're bound to do some work here, but is it really? Let's see what happens. So 9.5.3 is saying the 60 watt light bulb is now removed and replaced by an electric ion. Okay. An ion generally consumes more power than a bulb, right? Yeah, and then it goes on to say with a power rating of 2220 watts. Makes sense, it's an ion. We are replacing a bulb. Explain with the aid of a calculation why this is not advisable. Yeah, so now what I'm thinking is this ion has a power rating of 220. So for ion, let's just jot down some information for the ion. For the ion, we have a power of 2200 watts, right? And then the ion will experience a voltage of 220 volts, right? Because it will be parallel to the 100 watt bulb, which is receiving 220 volts, because our power source can only give us 220 volts, right? So we have the power, we have the voltage, we can determine the resistance, right? The resistance, and then we can determine the current. What would the resistance help us with? If we determine the resistance, then we can calculate IT, right? The total current. But then another way of which you can calculate the total current is if we just use the power and the voltage, right? So let's say that the power is equals to VRMS multiplied by IRMS. So our IRMS will be equals to the power, which is 2200 divided by 220, and this will be equals to 10 amps. So on this line here that I'm circling now in yellow, let me just make that more appealing. So on that line there, we're going to have 10 amps, right? But then we also have this line here, which will have its own current. We can actually calculate that current actually, because we know the power there and we know the voltage. So okay, fine. Current of the 60 watt battery will be equals to the power divided by 220. So let me just put that in my calculator real quick and see what we get. Where's my calculator? Okay. So we have 60 divided by 220, which is equals to 0.27. So 0.27. And then the fuse can only allow a current of 10 amps. But now we are requiring a current of 10.27. So what's going to happen? The fuse is going to burn out because the current that is required is greater than that which the fuse will let pass through, right? So it will not be advisable at all to have this electric ion on this circuit of ours. An experiment is conducted to investigate the relationship between the wavelength of light incident on a metal and the maximum kinetic energy of the emitted electrons from the surface of the metal. This experiment is conducted for 3 different metals, namely iron, copper, and gold. And then 10.1 says state in words what the photoelectric effect is for 2 marks. That's just basically the definition of photoelectric effect, right? Which says that it is the process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on the metal surface. It's a process whereby electrons are ejected from a metal surface when light of a suitable frequency is incident on the metal surface. And then 10.2 says, write down the name of the physical quantity or quantities represented by the gradient of the graphs, right? So now what we have to do here is to find an equation for this graph, right? We know that the energy is equals to the Planck constant multiplied by the frequency. But we also know that this energy can be equals to the work function plus EK, right? So these 2 things that I'm circling are equals to each other. So in our graph here, we have 1 divided by wavelength as our X and the maximum kinetic energy as our Y. So in this formula that we have here, we have to make the maximum kinetic energy the subject of the formula. So we're gonna have EK, this is EK max, right? EK max being equals to H multiplied by F minus the work function. But we know fully well that on our graph, we have 1 divided by wavelength, right? We can say that the frequency is equals to the speed of light divided by the wavelength, right? So that is equals to C multiplied by 1 divided by wavelength. So in our equation, we can now say that EK max is equals to H multiplied by C multiplied by 1 divided by wavelength minus the work function. So now you can see that this will be your Y, and then this here is going to be your M, and 1 divided by wavelength is going to be your X, and then minus work function is going to be your C. So we have Y equals to mx plus C. We are interested on the gradient of the graph, right? So we can now tell that the gradient of the graph is the Planck's constant and the speed of light, right? So you can see H and C, and then you get your 2 marks. And now we can go to 10.3. 10.3 says that which of the 3 metals needs incident light with the largest frequency for photoelectrons to be emitted? Give a reason for the answer. We have already said that the frequency is equals to the speed of light divided by the wavelength, which you can also write as the frequency being equals to the speed of light multiplied by 1 divided by wavelength. So we basically multiplying these 2 numbers, right? So the bigger 1 divided by wavelength, then the more frequency is required. So when we go to our graph here, which one is the bigger value for 1 divided by wavelength? Clearly is gold, because it's here, right? It has a value of between 2 and 1.5. So here the metal that will require the largest frequency for photoelectrons to be emitted is going to be gold, right? Why are we saying gold? We're saying gold because the frequency is equals to the speed of light divided by the wavelength. And clearly gold has
the highest value of 1 divided by wavelength, right? And then now we can move to 10.4. 10.4 says the symbol X in the above graph represents the work function of ion. They don't even have to tell us, right? We can already tell because we have this equation here. And then it goes on to say that if the work function for ion is 9.945 times 10 to the minus 34 joules, calculate the maximum velocity of an emitted electron from the surface of ion if the wavelength of the incident light is 9 times 10 to the minus 11 meters. So again, we have the energy being equals to H multiplied by F being equals to the work function plus EK max. So here we are asked to find the velocity of an emitted electron, right? So EK max will be equals to 1 divided by 2 mv squared, because that's the equation for kinetic energy, right? So now we have H multiplied by F being equals to the work function plus 1 divided by 2 mv squared. So what we're looking for here is this V, right? So let's try and make V the subject of the formula. So we can take this term here to the left hand side. If we do that, we're gonna get H multiplied by F minus the work function is equals to half mv squared. So now we can divide everything by half m and take the square root, right? So we're gonna find that our V is supposed to be H multiplied by F minus the work function divided by half m, and then everything to the power 1 divided by 2. So now it's just a matter of substituting our values in V equals to this expression here, and then we get the maximum velocity of the emitted electron. So let's go ahead and do that. So here we're going to have the value of H is a constant, that is 6.67 times 10 to the minus 34, and then what is the frequency? Let me look here. We don't have the frequency, right? But we have 1 divided by wavelength, which is somewhere around here, just before 0.5, right? So let's estimate that value to be 0.4 because we're not really sure what it is. So here we can have multiplied by the speed of light, which is 3 multiplied by 10 to the power 8 divided by 0.4 times 10 to the minus 8. Where is the minus 8 coming from? Look here where I'm circling in yellow, right? Is multiplied by 10 to the minus 8 meters to the minus 1. So now we have that. So let's go ahead and subtract the work function, right? We are told that the work function is 9.945 times 10 to the minus 34. And then there we have it. Now we're supposed to divide everything by half m, right? So let me just, so we're gonna have half the mass of an electron, which is 9.11 times 10 to the minus 31. Yeah, I think that is correct. And then everything to the power of 1 divided by 2. So V is going to be equals to, let me just put that in my calculator real quick. So I'm getting 10.48 times 10 to the 7 meter per second, right? If the net force is constant, the acceleration is constant, okay? The first option says constant velocity. If it is constant velocity, the acceleration will be 0. So this is not true. Constant acceleration is option B. So that is our answer. The answer to 1.1 is B. Constant force, constant acceleration, not constant velocity. Constant velocity implies that the acceleration is 0, which is not correct. 1.2,
A crate of mass m is stationary on a plane inclined at an angle theta with a horizontal. Which one of the following statements regarding the magnitude of the frictional force acting on the object is correct? So the crate is stationary, right? If we draw a free body diagram for m, we're going to have the frictional force, not the frictional force, but Fg parallel. When I have Fg parallel pushing down the object, but it is stationary, that means that frictional force is pushing it up the incline. We have the normal force and we have Fg perpendicular. Okay, so clearly you can see that Fg parallel is equals to the frictional force. That is why our object is stationary. Let's hear the stories. The magnitude of the frictional force acting on the crate is, the first option, equal to the component of the weight of the crate which is parallel to the plane. We don't have to go any further. That is what we are saying. So the answer to 1.2 is A. Okay. 1.3. 1.3 says a ball is projected vertically upwards from the top edge of a building. Points P, Q, R, and S represent different positions during the motion of the ball, as shown in the diagram below. Ignore the effects of air resistance. Between which 2 points will the ball undergo the greatest change in kinetic energy? So the change in kinetic energy, EK final minus EK initial. Let's take a look at our situations. Okay, we have P and S as one of the possible options. Okay, at S we have some Vx. Okay, let's say Vs. Yeah, let's say Vs and not Vx. Okay, so at S we have some Vs. At P we have some Vp. Okay, and then let's take a look at P and R. At P we have Vp. At R we also have Vp. Okay, it's just that with a negative sign or a positive sign, depending on which direction you take a switch. But the magnitude of the velocity at P is equal to the magnitude of the velocity at R. Okay, so P and R, the change in kinetic energy there is actually 0 between P and R. So this cannot be the correct option. The answer, P and R, the change in kinetic energy is 0. Let's move to R and S. Okay, the change in kinetic energy between P and S is the same as the change in kinetic energy between R and S, because Vp, the velocity of at P, is equal to the velocity of at R, right? So A and C cannot be the correct answers at the same time, right? We cannot have A being correct and C being correct. So clearly they all have to be wrong. The correct answer is actually D, okay? But we can make sense of that. We can justify why D is the correct answer. At Q, that is the maximum height. So the kinetic energy at Q is 0. But at S, we have some Vs, okay? So Vs minus 0 will be greater than Vs minus Vp, okay? That makes sense. Right, so the answer to 1.3 is actually D. 1.4, let's hear the stories. I think I've seen this before. A ball is dropped from height h and strikes the floor with momentum p. The ball is then dropped from a height a half h. Ignore the effects of air friction. Which one of the following represents the momentum of the ball when it strikes the floor after being dropped from height a half h? Okay, so we know that P, we need M and V. M is not changing. What is changing is V. So we need to figure out how V is changing as a function of h. In order to do that, we can say that Vf squared is equal to Vi squared plus 2a delta y. All right. This is our formula of choice because it's been dropped, so Vi is 0. The only thing that is affecting Vf is delta y. Okay. So Vf will be equal to the square root of 2a delta y, right? Vi is 0. So let's look at our case where the height is h. In our case where the height is h, we're going to have P being equals to M multiplied by 2AH, right? Looking at the case where the height is a half h, we're going to have P being equals to M multiplied by 2a multiplied by h divided by 2. 2 and 2 cancels out, so we have M multiplied by the square root of AH, Okay, let's look at the case where the height is h. We're going to have p being equals to the square root of 2 multiplied by m multiplied by ah. Okay, so as you can see, the momentum when the object is being dropped from a height h, let's call this momentum px, will be equals to px divided by square root of 2. If you divide this by square root of 2, you get the momentum when the ball is dropped from a height of h divided by 2. So the answer to 1.4 is B because of that. Okay, 1.5. 1.5, a box moves on a horizontal surface. The diagram below shows all the forces acting on the box. Which of the following combinations of forces do work on the box? Okay, so obviously P is not doing any work because the object is moving horizontally. The angle between P and the movement of the box is gonna be 90 degrees. If it is 90 degrees, cos of 90 is 0, so it's not doing any work. Same is true with R. The angle is going to be 90 or 270 depending on whether you move clockwise or anti, right? But the work done by P and R is 0. So the only forces that are doing work is S and Q. Okay, so which option says S and Q? That is B. So the answer to 1.5 is B. 1.6, a train moving at a constant velocity towards a stationary listener emits sound waves at constant frequency. Which one of the following statements about the sound waves observed by the listener is correct? So the train is moving towards, if the train is moving towards higher frequency, lower wavelength. Let's look at A. Frequency is higher than the emitted frequency. We don't have to go any further. The answer is A here. Okay, 1.7. Yeah, that is conceptual. We should be getting that one. 1.7, Q and R are small spheres suspended by light insulated strings. When a negatively charged rod is brought close to sphere Q is repelled. Okay, when the negatively charged rod is brought close to sphere R is attracted. Which one of the following combinations below can be possible for the nature of the charges on sphere Q and R? Okay, if you look at option A, we have negative and negative. So Q and R cannot be negative, and then they act differently when they are brought close to the rod, right? They should act in the same way. So this is not correct. A cannot be correct, right? They cannot be all negative and act differently around the same charge. B says Q is positive. If Q is positive, it should not move away. It should move close. Opposite charges attract. So this cannot be correct. Let's take a look at C. C says neutral. C cannot be correct. Why? Because if you have a negative and a neutral, they attract. If you have a negative and a positive, they attract. So the mere fact that it is moving away, it means that it is not neutral. If it was neutral, it was going to move towards the rod. So C is not correct. Obviously, D should be correct. Okay, so let's look at the other side. The other side, it says R is neutral and is being attracted by the rod. So that makes sense. 1.7, the answer is D. 1.8, in 1.8, 4 voltmeters V1 and V2, V2, V3, and V4 are connected in a circuit, as shown in the diagram below. Which voltmeter will have the same reading as voltmeter V1 when the switch is open? Let's take a look at V1. V1 is reading the EMF, right? When the switch is open. It's connected across the ends of the battery because there's no current flow in here when that switch is open. Okay, the current is going to try going through the voltmeter, but it can't because it has very high resistance. So V1 is reading the EMF. Okay, can V2 read the EMF? No, it cannot. It is not connected across the ends of the battery. The same is true with V4, right? But V3 is reading the EMF. So the answer to 1.8 is B. Okay, if you cannot see how this comes about, you can actually open a simulation online and set up this circuit and look at the reading on V1, V2, V3, and V4. The reading on V1 and V2 will be, V1 and V3 will be the same. So the answer to 1.8 is actually B. 1.9. A split ring connects the coil of a generator to an external circuit. Which one of the following combinations below is correct for the magnitude and direction of the induced current in the external circuit? Magnitude of the induced current. Okay, the magnitude of the induced current changes. So we're looking at C and D. Okay, you know that we draw a graph where we have I on one side and time on the other side, and then it is going up until I max and goes down. So clearly the current that is induced changes. Okay, now let's talk about the direction of induced current in the external circuit. The direction of the induced current in the external circuit when you have a split ring is constant, right? In the external circuit. That is a key word. In the external circuit, it is constant. So which option satisfies those two conditions? I think it is option C and not D. So the answer to 1.9 is C. 1.10 on the other hand, let's take a look. Where's 1.10? Oh, okay, here it is. I was surprised. Light of visible frequency is shown on the surface of a metal and electrons are ejected from the metal. Which one of the following is equal to the ratio of the work function to the threshold frequency of the metal? Okay, so what is work function divided by threshold frequency equals to? Is equals to Planck's constant, because if you cross multiply, work function is equals to Planck's constant multiplied by threshold frequency. Okay, so that is option A. The answer to 1.10 is A. State Newton's second law of motion inwards. So when a non-zero resultant force is applied on an object, the object will accelerate in the direction of the non-zero resultant force, with an acceleration that is directly proportional to the non-zero resultant force and inversely proportional to the mass of the object. That is Newton's second law, 2.1. Let's take a look at 2.2. Okay, so in 2.2, the kinetic frictional forces acting on block A and B are 5.88 newtons and 13.23 newtons respectively. Okay, so that of A is 5.88 and that of B is 13.23. And then the equation 2.2, we're supposed to draw a labeled free body diagram showing all the forces acting on block A. So let's go ahead and take a look at block A. Before we start thinking about anything, we have the weight, obviously. So there goes the weight. Block A is resting on a surface, so the surface will apply a normal force on the object. So we have the normal force in that direction. Okay, A and B are connected by a string, so there's a tension pointing in that direction, up the incline. But there's kinetic frictional force, which will be opposing the motion. So there we go. We have our kinetic frictional force. Okay, that is 2.2. The Muggle equation is 4, and we have 4 forces on our free body diagram. So we are quite convinced that we have done the correct thing. If the Muggle allocation is 4 and you have 3 forces on your free body diagram, you're probably doing something wrong. Okay, let's move to 2.3 and 2.3.1. In 2.3.1, we want to calculate the tension in the string. In 2.2, we have the free body diagram of object A, block A, right? So let me use block A again in 2.3.1. We want to find the tension force. As I always say, we start by saying F net is equals to MA all the time in question 2. This is Newton's second law. How you want to follow up this equation is by doing the following. Which force is pulling your object? It is the tension. So you want to say tension minus all the forces that are opposing. Okay, we have frictional force. So tension minus frictional force because it is opposing. Right? So we're going to have tension minus frictional force. But I want you to take a look at something. We have the weight, of which we can resolve into FG parallel and FG perpendicular. So we have FG parallel that is also opposing the motion. So minus FG parallel. This is equals to MA. So what is the tension? The tension is what we are interested in. What is the kinetic frictional force of block A? It is given to us as 5.88 newtons. So we're going to have 5.88 minus FG parallel. FG parallel is just mg sine of theta, okay? Of which theta is 35 degrees. So we're going to have the mass of block A, 4 kgs, the gravitational acceleration, 9.8, cos, not cos, but sine. The parallel component on an inclined surface is sine. So we have sine of 35 being equals to ma. The mass is 4. Are we given the acceleration? If you take a look at your question statement, you should realize that the blocks now accelerate up the incline at 2 meters per second. So we have an acceleration of 2. Okay, so we're going to have the tension minus. So we have minus 5.88 minus 4 multiplied by 9.8 multiplied by sine of 35. If you put that in your calculator, you're going to get minus 28.3642 being equals to 4 multiplied by 2, which is 8. So the tension is just equals to 8 plus minus 28.3642, right? When minus 28 goes to the other side, it is going to be plus. So it's just 8 plus 28.3642. The tension is going to be 36.36 newtons. That is the tension on the rope, okay? 2.3.1. Let's take a look at 2.3.2. In 2.3.2, we're looking for the force F. The force F is applied on block B. So we cannot use block A to find the force F. We have to use block B, okay? Obviously, we can go ahead and say F net is equals to MA, go ahead and substitute. But let's draw the free body diagram first. I cannot do it without a free body diagram. I always have to draw a free body diagram first. Okay, how will that look like? We have the force which is applied. But on block B, the tension is opposing. So we have tension down the incline. We have the weight and we have the normal force. So that is the free body diagram for block B. There is no mark for this free body diagram, but I need it in order to answer the question. I cannot answer it without the free body diagram. Okay? If I use the same idea I used in 2.3.1, I'm going to say that F net is equals to MA. Which force is pulling our object? F. Which force is opposing? I'm missing something. There's a frictional force. Let's not forget that. Right. So the forces that are opposing, it is frictional force, it is tension, and it is FG parallel being equals to MA. Okay. So we're gonna have F, the frictional force, not the frictional force, but the applied force, minus the kinetic frictional force, which is 13.23, minus the tension, which is 36.36. So we have 36.36 minus FG parallel. FG parallel will be the mass, which is 9. So we have 9 multiplied by 9.8 multiplied by sine of 35. So that sine of 35. This is equals to MA. The mass is 9 and the acceleration is 2. Okay? So we're going to have the force minus 13.23 minus 36.36 minus 9 multiplied by 9.8 multiplied by sine of 35. I'm getting 100.1794 being equals to 18. So the force applied will be equals to 18 plus 100.1794. Okay, this is 118.1794 newtons. Right, that is the magnitude of force F 2.3.2.
2.4, let's hear the stories. In 2.4, the angle that the plane makes with the horizontal is now decreased. Okay, this angle is decreased now. What is the question saying? How will this change the kinetic frictional force acting on block A? Choose from increase, decrease, or remain the same. And then in the question that follows, we're supposed to explain our answer. Okay, so let's take a look at 2.4.2 first. Okay, so we want to figure out whether the kinetic frictional force is going to increase or decrease. Okay, so Fr is given by the coefficient multiplied by the normal force. The coefficient is dependent on the material, so it's not going to change. What about the normal force? The normal force is the mass multiplied by gravity multiplied by cos of theta. Okay, the coefficient is not changing, the mass is not changing, the gravitational acceleration is not changing. So what we're interested in here is the effect of cos of theta on the frictional force. The angle is decreasing, right? So let's see how that affects cos of theta if the angle is decreasing. We know that cos of 0 is equals to 1. Cos of 0 is equals to 1. What about cos of 20? Okay, let me put that in my calculator. Cos of 20 degrees, that is 0.94. Let me say cos of 35. Cos of 35 is equals to 0.82. So you can clearly see that when we decrease the size of the angle, when we decrease theta, cos of theta increases. So the frictional force is going to increase if we are decreasing the angle, right? As you can clearly see, as the angle decreases, cos of theta increases. Define the term free fall. So free fall is the motion of an object under the influence of gravity only, right? That is free fall. You start by saying the motion. If it was projectile, you would start by saying it is an object, so on and so on. That is the difference between free fall and projectile. Free fall is the motion of an object in which the only force acting is gravity, it's gravitational force. That is free fall. 3.1. Let's take a look at 3.2. We have to go through our question statement. So a ball of mass 0.5 kg is thrown vertically upwards from the top edge of a building which is 15.3 meters high. The ball reaches a maximum height of 5.89 meters above the top of the building. The ball strikes the ground and bounces vertically upwards, reaching a maximum height at point P, as we can clearly see. Okay. 3.2. Using only equations of motions, calculate the speed at which the ball was projected upwards. So we will consider the motion of the object from the time it is projected until the maximum height. If we only consider that part of the motion, then VI is what we would be interested in. VF will be equals to 0 meters per second, maximum height. Our acceleration, if we take up as positive, it will be negative. So we're going to have minus 9.8 meters per second squared. Do we have delta t? We don't, but we have delta y, which is equals to 5.89 meters. That is the displacement of the object from the time it is projected until maximum height. 5.89, not 5.89 plus 15.3. No, but 5.89. We're only considering the part of the motion from the time it is projected until maximum height. If we look at these equations and you want to find VI, not these equations, but if you look at these variables and you want to find VI, the equation to use is VF squared is equals to VI squared plus 2A delta Y. Okay, VF, that is 0 squared, being equals to VI. VI is what we're interested in, multiplied by plus 2 multiplied by A, which is minus 9.8. Delta Y is 5.89. 0 squared is just 0, obviously. If we take VI squared to the left-hand side, we're going to get minus VI squared being equals to. So now I have 2 multiplied by 9.8 minus 9.8 multiplied by 5.89. That is minus 115.444. If I divide both sides by minus 1, I'm going to have VI squared being equals to 115.344. Now I need to take square roots on both sides. If I do that, let me just go ahead and do that. I'm going to have 10.74 meters per second. I was looking for the magnitude or the velocity. Let me take a look. The speed, okay, speed, we only need the magnitude. So that is the speed at which the object is projected upwards, 3.2, 3.3, 3.3.1. After the collision with the ground, the ball leaves the ground with a speed of 11.92 meters per second. Okay, let's hear the stories. The question: calculate the amount of energy lost by the ball during the collision with the ground. That is for 5 marks. Let's make sense of that. We want to find the amount of energy, of kinetic energy lost by the ball during the collision with the ground. Okay, so as the ball strikes the ground, it is striking the ground with some EK, right? Because it has a velocity. Its velocity is not zero. And then as it leaves the ground, it is also leaving the ground with some EK. So we want to find how much kinetic energy the object loses, the ball loses, when it is in contact with the ground. So we need to find EK as it strikes the ground, and we need to find EK as it leaves the ground. We need to find those two kinetic energies and find the difference between the two. The difference will be the kinetic energy that the object lost as it was in contact with the ground. So let's concentrate first on the kinetic energy as it strikes the ground. So we're looking at the kinetic energy as it strikes the ground. E is equals to EK, not just E, right? Because E can be inert. So EK is equals to a half mv squared. I need to write down this formula first before anything else. Now let's take a look. Do I have the velocity as the object strikes the ground? I don't. I only have the velocity as the object leaves the ground, but not as it strikes the ground. So I need to find the velocity as the object strikes the ground. Okay, let's go back to our sketch. Now we are considering the entire motion from the time it is projected until it strikes the ground. Okay, that is the motion we are considering now. Delta y for that motion is minus 15.3. The displacement is downwards. Okay, A obviously will be minus 9.8 meters per second squared. If we take upwards as positive, that is. What else do we have? We have VI from the equation above. VI is 10.74 upwards, so that is positive. Okay, I want to find VF, or the velocity as it strikes the ground. With these 4 variables, which equation can I use? Is VF squared is equals to VI squared plus 2A delta y gonna work? Yeah, I think that can work. So let's go ahead and find the velocity as it strikes the ground using that equation. VF squared is equals to VI squared plus 2A delta y. VF squared is what we're interested in. VF, not VF squared, but you know what I mean. And then VI, that is 10.74 squared plus 2 multiplied by A minus 9.8 multiplied by delta y minus 15.3. So VF squared is equals to, okay, let me just go ahead and put that in my calculator. Plus 2 multiplied by minus 9.8 multiplied by minus 15.3. I'm getting 415.2276. So VF is equals to. Now I just need to take square roots on both sides. If I do that, I'm getting 20. So I have 20.3771 meters per second downwards, right? This is downwards. Okay, so now that I have, this is the velocity as the object strikes the ground. Now that I have the velocity as the object strikes the ground, I can go ahead and substitute it on EK. So EK will be equals to a half m. The m, the mass of the object, that is 0.5. So I'm going to have 0.5 multiplied by the force. Not the force, but the velocity. What am I saying? The velocity is 20.3771 squared. Okay? This will be equals to. So let me go ahead and put that in my calculator. 0.5 multiplied by 20.3771 squared. Okay, I'm getting 103.8066 joules. This is the kinetic energy as the object strikes the ground. Okay, now let's look at the kinetic energy as it leaves the ground. As it leaves the ground, we're going to have EK being equals to a half. The mass is 0.5. The velocity as it leaves the ground, it is given to us 11.92. So that's what we need to substitute. 11.92 squared. Okay, now I just need to put that in my calculator. Okay, so 11.92, I'm getting 35.5216 joules. So this is the kinetic energy of the object as it leaves the ground. I want to find the amount of kinetic energy that is lost. So the amount of kinetic energy, so I can just say EK lost. EK lost. There is no formal way of writing this. EK loss will be EK that we started with as we are striking the ground. We have 103.8066 minus the kinetic energy as we are leaving the ground. Okay, so minus 35.5216. Is it 5216? Okay, I think it is 5216. Let me just go ahead and put that in my calculator. 103.8361 minus 35.5216. I'm getting 68.31 joules as the amount of kinetic energy that is lost. So this kinetic energy is converted to heat, is converted to sound and other form of energies, right? It is not disappearing. We know that it cannot disappear. It's just being converted from one form to another. That is 3.3.1. Quite an interesting question. It's the first time I see a question like this. Honestly, I've solved a lot of questions. It's the first time I'm seeing a question like this. But still, that doesn't mean you should get the question wrong because it's quite basic. You just needed to realize that, okay, I can find the kinetic energy as we strike the ground, the kinetic energy as we leave the ground, and then the difference will be the kinetic energy lost in contact with the ground. Anyway, 3.3.2. Let's take a look. 3.3.2. Time taken for the ball to reach point P after leaving the ground. Okay, we leave the ground with a velocity of 11.92 meters per second upwards. And then at point P, that is our maximum height after striking the ground. So VF shall be equals to 0. Acceleration minus 9.8. If we're taking up as positive, we're interested in delta T. So I think this is quite easy to compute. VF is equals to VI plus a delta T. VF is 0, VI is 11.92 plus the acceleration minus 9.8 multiplied by delta T. So I have delta T being equals to minus 11.92 divided by minus 9.8. So, okay, let me go ahead and put that in my calculator. So minus 11.92 divided by minus 9.8, 1.22. So delta t is equals to 1.22 seconds. That is 3.3.2. Yeah, let me just verify that point P is our maximum height. I don't want to miss anything. So yeah, point P, it is indeed our maximum height. Let's move to 3.4. 3.4 is a breath of fresh air, if I can say so. Yeah, I was not looking forward to having to sketch a graph. I was not looking forward to that. So now that I have a graph and I just have to identify the points, I'm quite a fan. I didn't want to sketch a graph. Let me hear the stories, okay? The velocity time graph for the motion of the ball from the instant it is projected upwards from the top edge of the building until the time it reaches point P is shown below. Write down the numerical values indicated by each of the following. So 3.4.1, we have, let me just write that down. 3.4.1, we have K. So what is K? So let's take a look at L first. L is at t is equals to 0. So this is the velocity at which our object is projected upwards. We have the value of that. So let's just go ahead and write that first. So this is 3.4.1 we're looking for K. In 3.4.2 we're looking for L. L is 10.74. That is the velocity at which the object is projected upwards. Okay, and then here we have V is equals to 0, maximum height. We strike the ground at this velocity, and this is the velocity at which we leave the ground. So K is the velocity at which we leave the ground. It is given to us as 11.92. So the answer to 3.4.1 is 11.92. Okay, we are only interested on the numerical value. We don't have to put the SI unit. Right, and then T2 minus T1. Let's take a look. So T2 is our total time, the time at point P. And then let's take a look at T1. T1 is the time at which we are striking the ground. So T2 minus T1 should be the time from the ground to the maximum height, which is 1.22 seconds, like we calculated in the question above. Okay, this is quite not accurate. This is quite not accurate. I don't know if you're able to see why I'm saying that. This is the correct answer. It is the answer in the memo. I know that 100%, but it is not quite accurate. Think about it. If you get what I'm saying, if you can comprehend the idea, let me know in the comments. Let me know in the comments if you get it. What do I mean when I say this 1.22 is not quite accurate? Right, that is question 3. Let me know in the comment section which question you want me to do next. A wooden trolley of mass 2.7 kg moves to the left with a constant velocity of 3 meters per second. A bullet of mass 0.03 kg is fired horizontally from the left towards the trolley. See diagram A. Okay, we can see in the diagram that the trolley is moving to the west and the bullet is moving to the east. Let's carry on and hear the stories. The bullet strikes the trolley and comes to rest inside the trolley in 0.02 seconds. Okay, the average net force exerted by the trolley on the bullet during this time is 591 newtons. So the net force exerted by the trolley on the bullet is 591 newtons. Right. The bullet trolley combination now moves to the right. See diagram 2, as we can clearly see in diagram 2. Let's go ahead and answer the questions. The first question, 4.1, we are told that we can ignore all frictional and rotational effects. Okay. Write down the magnitude and direction of the average net force that the bullet exerts on the trolley. 4.1. We are given the average net force that the trolley exerts on the bullet. Now we want the average net force that the bullet exerts on the trolley. Newton's third law. So they should have the same magnitude, but in opposite directions. Okay, so the magnitude of the net force that the bullet exerts on the trolley will be 591 newtons. That is 4.1. Let's take a look at 4.2. Calculate the magnitude of the velocity with which the bullet strikes the trolley. Calculate the magnitude of the velocity with which the bullet strikes the trolley. Let's jot down the information we have. The information we have is going to guide us to the formula we need to use. So we have F, which is equals to 591 newtons. Okay, we're interested on the bullet because we want the magnitude of the velocity with which the bullet strikes the trolley. Okay, so this will be 591 newtons to the left. This is to the left. Okay, because the trolley is moving to the left. When it hits the bullet, it will apply a force to the left. So that is one thing we know. Another piece of information we have is the mass of the bullet. It is 0.03 kgs. Right. What are we looking for? The question says we must find the magnitude of the velocity with which the bullet strikes the trolley. The bullet comes to rest inside the trolley in 0.02 seconds. So we have a delta t, which is equals to 0.02 seconds, and a VF, which is equals to 0. This is when the bullet rests inside the trolley. What we are interested in is VI, the velocity at which the bullet strikes the trolley. If you take a look at our variables, you can see that they are taking us to F net is equals to the change in momentum divided by the change in time, where F net will be equals to minus 591 being equals to the mass multiplied by VF minus VI. The mass of the bullet, that is 0.03, multiplied by VF. VF is 0. What is VI? What we are interested in. Everything divided by the change in time. The change in time is 0.02. So we are going to cross multiply. If we cross multiply, we're going to have minus 591 multiplied by 0.02, which will give us minus 11.82 being equals to, okay, 0.03 multiplied by 0, that is 0. And then 0.03 multiplied by minus VI is going to be minus 0.03 VI. If we divide both sides by minus 0.03, so let me just go ahead and do that. I'm getting 394. So VI is equals to 394 meters per second, which is a realistic speed for a bullet. It makes sense. If we were getting 20 meters per second, it wouldn't make sense. But a velocity of 394 meters per second for a bullet makes sense. Okay, it's traveling just above the speed of sound in air. Let's carry on. That is 4.2. 4.3. State the principle of conservation of linear momentum in words. Well, the total linear momentum in an isolated system remains constant or is conserved. Okay, that is 4.3. Not trickery there whatsoever. It should be max we are getting. 4.3. What about 4.4? 4.4, calculate the magnitude of the velocity of the bullet trolley combination after the collision. So in 4.3, I defined the linear momentum in words. In 4.4, I'm most likely to use it. So I'm going to start by saying that the sum of the momentum before is equals to the sum of the momentum after. This formula will earn you a mark. Even if you don't say M1, V1, even if you don't do that, this formula is going to earn you a mark. Just the way it is. The sum of momentum before is equals to the sum of momentum after. So you must start with this formula. Because if you start with that one that says M1, V1, you might get it wrong. But there's no way you will get this formula wrong. It is always like this. There is no, there's nothing you need to change. It's just always like this. Okay? Now we can go ahead and take a look at our situation. We want the magnitude of the velocity of the bullet trolley combination after the collision. So initially, we have the bullet. So we're going to calculate the momentum of the bullet plus the momentum of the trolley. So let me use T. And then now we're going to have the momentum of the bullet and the trolley. Okay, the momentum of the bullet before the collision is 0.03 multiplied by VI, which we just calculated above, which is 394, plus the momentum of the trolley. So the mass is 3, and no, the mass is not 3, the mass is 2.7, and the velocity is 3, but to the west or to the left. So this is going to be minus 3, being equals to the momentum of the bullet trolley system. So now we have M1 plus M2. So that is 2.7 plus 0.03 multiplied by VF, which is what you're interested in. So let me just put together all those numbers on the left-hand side and see what I get. I'm getting 3.72. So I have 3.72 being equals to 2.73 VF. Now I just need to divide both sides by 2.73. So 3.72 divided by 2.73, that is 1.36. So I have 1.36 meters per second to the right. Am I only looking for the magnitude? Right, I'm looking for the magnitude, so I don't have to write to the right or to the left. So yes, that is question 4. I've already done question 5. If you have not watched it, then click on the channel and go ahead and watch it. Tell me which question you want me to do next. Just leave a comment. I'm going to check it out. Let's take a look. Let us conduct an experiment to determine how the initial kinetic energy given to a trolley affects the distance the trolley moves on a rough horizontal surface. A learner pushes a trolley of unknown mass until it reaches point A with kinetic energy EKA. The horizontal distance traveled by the trolley before it comes to rest is then measured. See the diagram below, okay? So the learner is pushing the trolley until it reaches point A. After the trolley reaches point A, the learner lets go, and then the trolley moves until it comes to a stop. So the learner is taking note of the initial kinetic energy of the trolley and then measuring the distance, okay? Let's see what the first question says. 5.1. Draw a labeled free body diagram showing all the forces acting on the trolley during its motion after passing point A. You can clearly see that point A is in bold, right? So we need to take note of that. So let's take a look. It is resting on a surface. So obviously, I'm going to start with normal force. After normal force, I have the weight, okay? If it is resting on a surface, I'm going to have the normal force and I'm going to have the weight. Well, the weight is always there, regardless of whether it's hanging or it is resting on a surface. Let's look at the mark allocation. The mark allocation is 3 and not 4. So we have only one other force we are looking for, which is frictional force, okay? The object is coming to a stop because there's frictional force. In the absence of frictional force, the object is supposed to keep going until forever. The object only stops because of frictional force. So we have frictional force. That is the third force. There's no force applied after passing point A. So if you actually include force applied, then this is wrong. If you put force applied, this is wrong. You're going to get the mark for the normal, the weight, but not for the friction because you also have force applied. You're going to forfeit 1 mark if you put force applied. So just know, if you wrote force applied on the free body diagram, it is wrong. I'm sorry, but it is how it is. Let's move to 5.2. So 5.2, name the independent variable in this experiment. So the independent variable is the variable you're willingly changing, and the dependent variable is the variable you are measuring after you've made that change. In our case, we are changing the initial kinetic energy of the trolley, and then we are measuring the distance it traveled. So the independent is the initial kinetic energy. That is our independent variable. So initial kinetic energy is our independent variable. Let's go ahead and do 5.3. 5.3 says the work energy theorem in words. State the work energy theorem in words. Well, it says that work net is equals to the change in EK. In words, the net work done on an object is equals to the object's change in kinetic energy. Okay, sometimes I see people losing a mark because they just say the net work on an object is equals to the object's change in kinetic energy, but that's not how you're supposed to say it. The net work done on an object it is the net work done on the object. It is not just the network. No, it is the net work done on the object. Okay, so that is 5.3. Let's do 5.4. Calculate the mass of the trolley if the coefficient of kinetic friction between the wheels of the trolley and the rough horizontal surface is 0.18. Okay, in a case like this, in 5.3, I defined the work energy theorem. In 5.4, I'm going to use the work energy theorem, right? That is the first thing I'm going to try out. I'm not saying that it will always work, but if you define something in the question above, you should be expecting that you will need to use it in the question that follows. So let me go ahead and see if I can use the work energy theorem. Okay, so work net is equals to change in EK. Let me take a look at the information I have. I have the coefficient of kinetic friction. If I have the coefficient, obviously I can find the friction. So I have FR, of which my FR is the F net, because frictional force is the only force that is doing work on the object. Normal force and weight, they're not doing any work, right? We're going to have cos of 90 and cos of 270, which will give us 0. So the normal force and the weight, they're not doing any work on our object. So I have the frictional force. Okay. Let's see. Do I have delta X? This is what the problem solving is. Do we have delta X? That's what the problem solving is. If you come here to your diagram, you should be able to see that you are given initial kinetic energy and its corresponding distance traveled. So let me take 12 and 3, okay, because this is the point. That point we have 12 for the kinetic energy and 3 for the distance traveled. So you can take that point. You can also take 18 and 4.5. You can take 6 and 1.5. Whichever point you take, it doesn't matter. But this is where the problem solving starts. This is the difficulty of the question. That's what you had to realize. Okay, so let me carry on. I can say that when my EK initial is equals to 12 joules, my delta X is equals to 3 meters. Yeah, that is correct. When my initial kinetic energy is 12 joules, my delta X is equals to 3 meters. But I also know, there's something that I know. I also know the kinetic energy final, because this is the distance the object travels until it comes to rest. So the kinetic energy final is equals to 0 joules because our object is coming to rest. So let me take a look. I have the frictional force, I have EK initial, I have EK final, and delta X. I think I can go ahead and substitute. Okay. When I substitute, I'm going to have FR, which is my F net, multiplied by delta X, multiplied by cos of 180, being equals to EK final minus EK initial. Okay, so what is frictional force? Frictional force is equals to, not coefficient, but frictional force is equals to the coefficient multiplied by the normal force. What is the coefficient? Let me take a look. The coefficient is 0.18. So we have 0.18 multiplied by normal force on a horizontal surface with no force acting at an angle is going to be the mass multiplied by 9.8. So this is the frictional force. Let me just put that in my calculator real quick. When I do that, I get 1.764 m. Okay, so in place of the frictional force, I'm going to have 1.764 m multiplied by delta X, which is 3, cos of 180. So this is minus 1. Being equals to EK final, that is 0, minus EK initial, which is 12. Okay. So now I have 1.764 multiplied by 3 multiplied by minus 1. So let me put that in my calculator real quick and see what I have. I'm getting minus 5.292 m is equals to minus 12. I need to divide both sides by the coefficient of m. So when I do that, let me go ahead and do that. I'm getting 2.27 kgs. Our mass is kgs as the mass of our trolley. That is 5.4. Tell me, which question do you want me to do next? Drop a comment. Let me know in the comments. I'm already done with solving all the questions. I just want you to tell me which question I need to do next. I need to record and upload. Let me know in the comments. Is it question 10? Because I think the last question 10, was quite interesting. Let me know. 6.1.1, state the Doppler effect in words. I'm just going to leave that for you. Let's take a look at 6.1.2. Use the given information to calculate the speed of sound in air. So let's take a look at the information we have. So an ambulance is moving away from a stationary listener. So if the listener is stationary, then we have VL, the velocity of the listener, being equals to 0. Okay, the ambulance is moving away from the stationary listener with a constant velocity of 25. So we have VS, the velocity of the source, being equals to 25. Okay, the siren of the ambulance emits sound waves at a frequency of 550 Hz. So we have the frequency as emitted by the source being 550 Hz. The siren of the ambulance, okay, 550 Hz. Let's carry on. The listener detects the frequency of these sound waves to be 512.64 Hz. So the frequency as observed by the listener is 512.64 Hz. Okay. We are told that the ambulance is moving away. But even if the question didn't say that the ambulance is moving away, we would be able to deduce it from the mere fact that the frequency of the listener is less than that of the source. But anyway, stories. So V, which is the speed of sound in air, what we're interested in. We don't have that, okay? So that is our unknown variable. Sticking to the basics, we're going to have FL, the frequency observed by the listener, being equals to V plus or minus the velocity of the listener, V plus or minus the velocity of the source, multiplied by the frequency as emitted by the source. The frequency experienced by the listener is 512.64, being equals to speed of sound in air, what we're interested in, plus or minus the velocity of the listener. The listener is stationary, so VL is equals to 0. Everything divided by V. The ambulance is moving away, so that is supposed to be plus 25 in the denominator. If it was moving towards, it would be minus 25. Multiplied by the velocity, not the velocity, but the frequency of the source. That is 550. Okay, so a mark for the formula, a mark for the substitution. Usually it's 2 marks for the substitution. They find a way to somehow squeeze 2 marks for the substitution. But let's forget about that and focus on the problem solving. Okay, so there's a couple of different methods people will use in this position, but ultimately we must get to the same answer. So this is the method I'm going to use. I will divide both sides by 550. Okay, so 550 and 550 will cancel out on the right hand side, and then on the left hand side I'm gonna have 512.64 divided by 550, which is 0.9321. So I have 0.9321 being equals to V divided by V plus 25. I didn't do anything fancy here. I just divided both sides by 550. Okay, and now I want to go ahead and cross multiply. V multiplied by 0.9321 will be 0.9321 V. Okay, and now I have 0.9321 multiplied by 25. That is going to be plus 23.3018. Okay, I'm rounding off to 4 decimal places because I'm not at the final answer. At the final answer, I'm going to round off to 2 decimal places, not 1. Okay, and then V multiplied by 1, it is just a V. If I take 0.9321 V to the left hand side, to the right hand side, I mean, I'm going to have 1 minus 0.9321, which is 0.0679. So I have 23.3018 being equals to 0.0679 V. It is obvious what I'm going to do at this point. I'm going to divide both sides by the coefficient of V, which is 0.0679. Okay, if I do that, I'm getting 343.18 meters per second. I'm quite happy with this answer because this is the value we usually get. We have 343. It's always somewhere there. Okay, so it is not unusual. It is not odd. If I was getting 20 meters per second or 900 meters per second, I would be panicking. But now I have 343, which is almost the value I always get in other problems. Okay, that is 6.1.2. 6.1.3, a bit conceptual. The ambulance is now moving away from the listener with a velocity that is greater than 25. Okay, how will each of the following change? Choose from increase, decrease, or remain the same. Let's take a look. A, the speed of sound in air. The speed of sound in air will remain constant, right? The speed of sound in air is not a function of how fast the velocity of the source is, right? So this will remain the same, okay? And then B, the frequency of the sound waves emitted by the siren. If you are emitting sound waves with a frequency of 500, that is not dependent on how fast you're moving. The frequency that you're emitting is going to be 500, whether you're stationary, whether you're moving towards, whether you're moving away. So again, we have remained the same, right? So this is the remains the same. Now let's look at C, the frequency of the sound waves detected by the listener. Take a look at our equation. We had FL being equals to V divided by V plus Vs multiplied by the frequency of the source. Okay, as you can clearly see, if the velocity of the source increases, we're gonna have a way greater denominator. And then if you increase the denominator, the number as a whole is decreasing. So the frequency of the listener would decrease, right? So the answer to C is decreases. Yeah, we can clearly see that from our equation. And then 6.2.1, the spectrum of a distant star when viewed from the Earth is redshifted. Is the star moving away or towards the Earth? And 6.2.2 says that use the Doppler effect to explain the answer to question 6.2.1. Right, I'm interested on how you answered this question. So 6.2.1, is it moving away or is it moving towards? Let me know in the comment. And what reason did you give? Why are you saying it is moving away? If you said it is moving towards, why are you saying that is the case? Let me know in the comment section. Let's take a look. 7.1, describe an electric field. Well, it is the region in space, so on and so on. I know that is not the question we're interested in. We're interested in 7.3. Let's just do 7.2 first and move to 7.3. I know that is the question you're here for. Okay, so 7.2, draw the resultant electric field pattern due to charges A and B. Let's take a look at A. A is positive, B is positive, so they're going to repel. They have the same magnitude, So we're going to have something that looks like the following. They are going to repel because they are like charges. They are both positive, so the filled lines should be pointing away from the charge. This arrow should be pointing away from the charge and not towards, like we would see in a negatively charged sphere. Okay, so we are supposed to have something like this. Okay, two positive charges, they're going to repel. This is how the electric field pattern is going to look like. 7.2. Taking a look at 7.3. Okay, so in 7.3 we are told that the magnitude of the net electric field pattern at point P is 27. So we have E net being equals to 27 newtons per coulomb of charge. Let's calculate the value of R. Let's take a look at our situation. Okay, my grade 10 kids can solve this question. Let me just leave it like that. Let's carry on. Okay, so we have A, which is positive. We have B, which is positive. We are given the net electric field at point P. Okay, so let's have a vector for the electric field due to A and the electric field due to B at point P. Okay, the way we do this is we always assume that at point P we have a positively charged sphere. Okay, so let's take a look at A and P. If A is positive and P is positive, that is repulsion. So P is going to be pushed to the right by A. Okay, so this is the electric field as a consequence of A. Now let's take a look at P, which is positive, and B, which is positive. Okay, we have repulsion once again. So this will be the electric field as a consequence of B at point P. As you can see, we're going to have E net being equals to EA minus EB. But we have the value of E net. E net is 27. We're going to have 27 being equals to the electric field due to A. What you want to write first is the equation. You need to write E is equals to KQ divided by R squared. There's a formula for this, so make sure that you don't forget to write that somewhere, okay? If I go ahead and substitute on that formula, I'm going to have 9 times 10 to the power 9 multiplied by the magnitude of A, which is 3 times 10 to the power minus 9, divided by the distance between P and A. It is given to us as R. So we're going to have R squared, okay, minus 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by R. But R, the distance between P and B, is 2R. So we're going to have 2R squared, okay? This will be equals to, so we have 27 being equals to 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by R squared. Minus 9 times 10 to the 9 multiplied by 3 times 10 to the minus 9. Everything divided by 4R squared. Okay, so now it comes down to mathematics. Other people will use different methods, so on and so on. But ultimately, we must get to the same answer. So this is how I did it. I'm taking 1 divided by R squared as a common factor on the right-hand side. Let me show you what I'm going to have. I will have 27 being equals to, open bracket, 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by 1. Minus 9 times 10 to the minus 9 multiplied by, not to the minus 9, but to the plus 9, okay? I think I made the same mistake there. To the power 9 to the power 9 multiplied by 3 times 10 to the minus 9 divided by 4, okay? I'm taking 1 divided by R squared as a common factor. So I can go ahead and put this in my calculator, okay? So I will have 27 being equals to, So let me just go ahead and put that in my calculator once more. So I have 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by 1 minus 9 times 10 to the power 9 multiplied by 3 times 10 to the minus 9 divided by 4. Okay, if I put that in my calculator, I get 20.25 multiplied by 1 divided by r squared. Okay, so this is just 27 being equals to 20.25 divided by r squared. If I go ahead and cross multiply, I'm going to get 27 r squared being equals to 20.25. So r squared is equals to 20.25 divided by 27. That is 0.75. So I'm taking square roots on both sides. Okay, let me go ahead and do that. If I do that, I get 0.87 meters. And when I substitute it back into my equation for E net, I get 27. So I'm quite convinced that R is indeed equals to 0.87. So that is 7.3. That is 7.3. Let me know in the comments if you got a different answer. But it is probably wrong. Yeah, it is probably wrong. Maybe I'm wrong, but I don't know. It's probably wrong. I think R is 0.87 meters. Just let me know in the comments if you get the same thing. Oh, there's something I'm missing here. Okay. 7.4. Calculate the magnitude of the net electrostatic force that an electron will experience if placed at P. So we know that E is equals to F divided by Q. Okay. So if we want to find F and we have E, we just see F is equals to E multiplied by Q. The net electric field is 27. Okay, so we have 27 multiplied by Q. Q being the charge of an electron. So we are only interested in the magnitude. So we're going to have 1.6 times 10 to the minus 19. I think if you put that in your calculator, you should get 4.32 times 10 to the minus 18 newtons. Right, let me know in the comments if we got the same answer. I'm just putting it in my calculator once more to verify. 4.32 times 10 to the minus 18 newtons. So there we go. Question 7. Did we get the same answer? Let me know. I'm quite sure that a lot of people were not even able to calculate the total external resistance of the circuit. Let me show you why. We're going to skip 8.1, obviously. It is just Ohm's law. V is equals to I multiplied by R. Let's take a look at 8.2.1 instead. So we're looking for the total external resistance of the circuit. Okay. We know fully well that R external is equals to RP plus RS. Let's take a look at RS first because it is easier to calculate the resistance in series. You just add all those resistors up. If you take a look at our setup, you should realize fairly quick that we have no resistance in series. RS is equals to 0 ohms. In the grand scheme of things, you're gonna see why I'm saying in the grand scheme of things. Okay, if you are not very fluent with electric circuits, then we need to do this first. This is the negative terminal. This is the positive terminal. The current flows from positive to negative, so it is gonna flow in the following fashion. We're gonna have something like this, but at this point the current splits, right? A proportion of the current goes down this path while the other proportion of the current goes down this path. Okay, so the total resistance on this path is in parallel with the total resistance on this path. Okay, but it is a bit deeper than that because on the upper path we have R1 and R2, which are also in parallel. So we need to find the effective resistance of R1 and R2 first. Okay, so RP will be equals to R1 multiplied by R2 divided by R1 plus R2. Okay, so we have 10 multiplied by 10, 100 divided by 10 plus 10, 20. 100 divided by 20 is 5 ohms. Okay, So the effective resistance of these two resistors is actually 5 ohms, right? So that tells us that the total resistance on the upper path is 5 ohms plus 10 ohms, which is 15 ohms. Okay, so if we want to calculate RP for this path and this path together, we're going to have RP for the entire circuit. We're going to have RP being equals to R1 multiplied by R2. R1 is the total resistance on the upper path, which is 5 plus 10, multiplied by the total resistance on the lower path, which is 15 ohms. Okay, everything divided by R1 plus R2. So that is 5 plus 10 plus 15. On the numerator, we have 15 multiplied by 15. On the denominator, we have 15 plus 15. RP will be equals to 7.5 ohm. Okay, so this is the total external resistance of our circuit. It is 7.5 ohms. Let's move to 8.2.2. Yeah, this situation where you have parallel on a path that is parallel, it is not so common, but you need to know how to take care of that. You first have to calculate the effective resistance of R1 and R2. Let's go ahead and take a look at 8.2.2. In 8.2.2, we want the reading on the ammeter. As you can clearly see, the ammeter is experiencing current that is not divided. So basically, we're looking for I total. Okay, so I total is what we're interested in. We have R external, which is equals to 7.5 ohms. We have R internal, which is 0.5. We have EMF, which is equals to 12. It will be obvious the equation we need to use. Okay, EMF is equals to I total multiplied by R external plus R internal. EMF is 12. I total is what we're interested in. R external 7.5, R internal 0.5. Okay, so 12 is equals to IT multiplied by 8. So IT will be equals to 12 divided by 8. That should be 1 point something, 1.5 ampere. So there we go. We have our current. 8.2.3. What's the mark allocation? 4 marks. Okay. 8.2.3. We're interested in the power dissipated by R3. Okay. So R3, the potential difference across R3 is VP, because on that path we only have R3. If we calculate VP, then we can say that the power dissipated by resistor R3 will be equals to V squared divided by R. Okay, so let's go ahead and find VP. VP is IT multiplied by RT. IT, that is 1.5. RT, the total resistance in parallel, that is 7.5. We know fully well that RT is not RT but RP, right? That's supposed to be RP. VP is equals to IT multiplied by RP. Okay, so 1.5 multiplied by 7.5, that is 11.25 volts. So we have VP. We can go ahead and calculate the power. The power is going to be 11.25 squared divided by the resistance, which is 15. Okay, let me go ahead and put that in my calculator. So 11.25 squared divided by 15 is 8.44 watts. Right, so there we go. We have our power. The power is 8.44 watts. 8.3.1. Switch S is now opened. Okay, so let's go ahead and open switch S. If we open switch S, this resistor R3 is no longer taking part in our circuit. So that other path is non-existent basically. Okay, all the current is flowing through this path, right? It's not going to divide at this point anymore. Yeah, we're going to have something like that. What does our equation say? If the resistance of the light bulb remains constant, How will the brightness of the light bulb be affected? Choose from increase, decrease, or remain the same. Explain the answer to question 8.3.1. Is it increasing, decreasing, or remaining the same? Let me know in the comment section. I'm going to check the comments after an hour, and then I'm going to reply with the correct answer. So make sure that you come back here after an hour and check 8.3.2. This is 4 marks up for grabs. Did you get this 4 marks or did you lose it? Come back after an hour and find out. In the meanwhile, you can let me know what your answer is and why you think so. As you can clearly see, this is a split ring and not a slip ring. So the answer to 9.1.1, we have split ring. Okay, A is a split ring and not slip. Okay, 9.1.2, state the energy conversion that takes place in the motor. So for every motor, we have electrical energy to mechanical energy, right? We have a power source here that is providing us with electrical energy, and we converted that electrical to mechanical. Right? That's what you were supposed to write, electrical to mechanical, right? There's no other possible solution here. We have electrical energy to mechanical energy. I do see electrical to kinetic energy once in a while, but for the most part, electrical energy to mechanical energy. Okay, 9.1.3, in which direction will the coil rotate? Choose from clockwise or anti-clockwise. Okay, well, explaining this will be very difficult because you cannot see my hand, obviously. This is a motor. With a motor, we use the left hand, okay? So your index finger will point from north to south. Your middle finger is the direction of the current, and your thumb is the force or the rotation of the coil, okay? If you place your left hand on that part of the coil, and then with your index pointing from north to south, and with your middle finger showing the direction of the current, then your thumb is going to show you the direction of the coil at that part. Okay, so we have the positive terminal and the negative terminal. So the current is going to be flowing in this fashion. Okay, as you can clearly see on the part we're interested in, the current is going down. So you're supposed to twist your hand such that your index is pointing from north to south, and then your middle finger is following the current. If you do that, then this part is going to be going down, right? And if that part is going down, you can clearly see that we have a clockwise rotation. That is the answer to 9.1.3. It is unfortunate I cannot demonstrate it. Yeah, as you cannot see my hand, but practice that and wrap your head around it. 9.1.4. So 9.1.4, state 2 changes that can be made to the motor for the coil to rotate faster. Okay, I can increase the voltage, increase the voltage. If you increase the voltage, the coil will go faster. So that's one of the things you can do. I want you guys to tell me what reasons you gave. I'm saying I'm going to increase the voltage. What did you say in the exam? Let me know in the comments. I'll be checking it out. Okay, that is 9.1.4. Let's take a look at 9.2. VRMS, IRMS, so on and so on. We know what you expect. The second diagram below shows an electric kettle and a toaster connected to an AC source with an RMS voltage of 220 volts. Okay. The ammeter connecting wires and switches S1 and S2 have negligible resistance. Right. 9.2.1, we're supposed to define the term root mean square current. I'm going to leave that one for you. Let's do 9.2.2. 9.2.2, when switch S1 is closed and switch S2 is open, the maximum current, so I max, is equals to 3.6 ampere. calculate the root mean square current in the circuit. Okay, so we're gonna have IRMS being equals to I max divided by square root of 2. I max 3.6 divided by square root of 2. So what should we get? I'm getting 2.55 ampere as my answer to 9.2.2. 9.2.3 on the other hand, when switch S1 is open and switch S2 is closed, the root mean square current in the circuit is 2.62 ampere. So now we have IRMS, which is 2.62 ampere. Calculate the energy consumed by the toaster in 2 minutes. So we want the energy. The energy is equals to the power multiplied by the time. Okay, so the power can take different forms, right? We can have V squared divided by R, I squared multiplied by R. So let's decide on which formula we're going to use to calculate the power. Well, we have IRMS is equals to 2.62. So now we need V or R in order to calculate the power. We have the VRMS. We are given the VRMS of the source. Okay, it is said to be 220. So we can just go ahead and find the power by saying VRMS multiplied by IRMS. Okay, obviously you can find the resistance first, which is sort of wasting your time because you don't have to do that. But if you do it, there is no problem. Okay, so we can find the power using that. And then the time, we have 2 minutes, which is just 120 seconds. Okay, so the energy consumed will be equals to the power, which is 220, our VRMS, multiplied by the current, which is 2.62, multiplied by the time, which is 120. Okay, I have the answer, but I have to put it in my calculator again and make sure. Okay, this is 69,168 joules. Okay, energy is in joules and not watts. Let's take a look. We have two spheres, A and B. They're made of pure zinc and they are at rest 0.1 meters apart on a wooden table. Sphere A is negatively charged and is free to move on the table, while sphere B is uncharged and fixed to the table, as shown in the diagram below. Okay, let's hear the stories. High intensity ultraviolet light of frequency 2.8 times 10 to the power 16 Hz is now shown onto sphere B. The work function of zinc is 6.63 times 10 to the minus 19 joules. Okay, let's carry on. 10.1.1 define the term work function of a metal. That is the minimum amount of energy required by a certain metal for electrons to be ejected or to be emitted from its metal surface, okay, right? That is work function. 10.1.2 explain using a suitable calculation why the ultraviolet light shown on sphere B will eject electrons from its surface. So we are given the work function, right, and the frequency that is shown. There's two ways you can explain using a suitable calculation why the ultraviolet light is suitable. Okay, yeah, there's two ways you can do that. You can convert the work function to the threshold frequency, and then you can compare threshold frequency with the frequency that is shown. The other way of doing it, you can use this frequency that is shown to find the energy that will be incident on the metal surface and compare the energy to the work function. One between the two ways. So our work function is equals to 6.63 times 10 to the minus 19 joules. Let me calculate the energy of the frequency that is being shown on the metal. Okay, I'm choosing to take that route. You can take the other route, which will conclude in the same fashion. So if I take this route, I'm going to have Planck's constant multiplied with the frequency. Planck's constant 6.63 times 10 to the minus 34, multiplied by the frequency that is shown. What is the frequency that is shown? 2.8 times 10 to the 16 hertz. So let me put that in my calculator. 6.63 times 10 to the minus 34 multiplied by 2.8 times 10 to the power 16. This is 1.86 times 10 to the minus 17 joules. Okay, clearly it is easy to see that 1.86 times 10 to the minus 17 joules is greater than 6.63 times 10 to the minus 19 joules. Okay, minus 17 is greater than minus 19. We know that for sure. Okay, so the energy of the light that is being shown on the metal is greater than the threshold frequency. So obviously electrons are going to be emitted. They're going to be ejected from the metal surface. So this is one way you can show that indeed the electrons are going to be emitted. Okay, 10.1.2. Let's take a look at 10.1.3, the interesting question. Okay, it was the first time I'm coming across a question like this. It's really interesting, right? But it's not difficult. I don't know why the mark allocation is 6 marks. It's not difficult at all, but it is interesting. Okay, so sphere A carries a charge of minus 5.4 times 10 to the minus 6 coulombs and requires a minimum force of 0.027 newtons to move from rest. So we have the force. Okay, the force is equals to 0.027 newtons. The charge on A is 5.4 times 10 to the minus 6. I'm forgetting about the sign. I'm just focusing on the magnitude. Okay, the question is saying, let's calculate the minimum number of photons of ultraviolet light that must strike sphere B, which will cause sphere A to move from its rest position. Okay, we have to go back to the basics. You need to understand that one photon can emit only one electron. Okay, so if we calculate the number of electrons that are being emitted on the sphere, then we can use that to calculate the number of photons. Basically, the number of electrons is equal to the number of photons. So we are actually supposed to just find the number of electrons. The number of electrons will be the number of photons. So let's go ahead and do that. Okay, so we will use F is equals to K Q1 Q2 divided by R squared. Okay, we have the electrostatic force. We have two charges that are attracting each other or repelling. I don't know in which direction they're moving. Okay, if electrons are being emitted from the sphere, then it will become positively charged. Okay, so they are attracting each other with a force of 0.027 newtons. I have Q1 or QA, which is 5.4 times 10 to the minus 6. I can go ahead and find Q2 because K is a constant and I have R. After finding Q2, then I'm going to calculate the number of electrons on Q2. Okay, let me go ahead and do that. The electrostatic force 0.027, K 9 times 10 to the 9, Q1 5.4 times 10 to the minus 6 multiplied by Q2. Everything divided by R squared. So R squared will be 0.1 squared. If we cross multiply, we're going to get, so 0.027 multiplied by 0.1 squared, I'm getting 2.7 times 10 to the minus 4, being equals to 9 times 10 to the power 9 multiplied by 5.4 times 10 to the minus 6. I'm getting 4.86 times 10 to the minus 4 multiplied by Q2. So it's obvious what I need to do. I need to divide both sides by the coefficient of, this is to the power 4 and not to the power minus 4. This is to the power 4. So let me just go ahead and change that. So we have to the power 4. Okay, so now I just need to divide both sides by 4.86 times 10 to the power 4. So what is 2.7 times 10 to the power minus 4 divided by 4.86 times 10 to the power 4? Okay, I'm getting Q2 is equals to 5.5556 times 10 to the minus 19 coulombs. So now I have the charge of Q2. I can go ahead and calculate the number of electrons that were emitted, okay? Of which the number of electrons that are emitted will give me the number of photons. So the number of electrons is equals to the charge divided by the charge of an electron. So we're going to have 5.5556 times 10 to the minus 9 divided by 1.6. Okay, 1.6 times 10 to the minus 19. That is the charge of an electron. Okay, so let me put this in my calculator. Divided by 1.6 times 10 to the minus 19, I'm getting 3.4723. Okay, 2 decimal places because this is my final answer. 3.47 times 10 to the power 10 electrons, which is the number of photons. Okay, so I think you would also need to conclude that the number of photons is equals to the number of electrons, which is 3.4723 times 10 to the power 10.
I think definitions like static friction is one of those things that people overlook, right? People usually concentrate on Newton's first law, second law, third law, so on and so on. But these kind of definitions are definitions that people oftenly overlook. They don't really give themselves some time to actually go through and memorize these kind of definitions. So I'm expecting that a lot of people actually got 2.1 wrong. But anyway, stories. Let's take a look at 2.2. Draw a labeled free body diagram showing all the horizontal forces acting on the crate just before it starts moving. Right. 2.2. Just like 2.1. People are not paying attention to the details. So I think that this is another question where people got it wrong. But most people think they got it right, but they actually got it wrong. Let me show you why. So 2.2, the key word here is horizontal, right? We want to draw a free body diagram showing all the horizontal forces. So if you include the vertical forces, I'm assuming you'll probably get it wrong, right? You'll probably lose 1 mark for every vertical force that you include. I think that's probably what's going to happen. So if you include the normal force and the weight, I think you're going to get nothing, or at most 1. But I'm quite sure there's no way you get all the marks if you include the vertical forces. So free body diagram for this object. Let's read through the question statement and see what is happening. In an experiment, a crate of mass 8.5 kg lying stationary on a rough horizontal table. So already we know that we are supposed to have friction, right? Because it acts horizontal. It is connected to a mass hanger by means of a light inextensible string passing over a frictionless pulley, as shown in the diagram below. Mass pieces are added to the mass hanger and the acceleration of the crate is measured. The experiment is repeated several times by adding different masses to increase the hanging mass each time. Ignore the effects of air friction. So right, that is the information we have. And then we're supposed to draw a label free body diagram acting on the crate just before it starts moving. Okay, so obviously we have the tension, right, as a consequence of the light inextensible string that connects the crate and the mass hanger. And then we also have frictional force, right, acting on the object. So there we go. These are the only 2 forces that we're supposed to have: frictional force and the tension force. Right, no normal force, no horizontal force. Not because they are not there, not because they do not exist. They still do exist, but the question is saying only the horizontal forces. So we have to respect that. And then 2.3.1. We're supposed to calculate the coefficient of static friction. So we are looking for this coefficient of static friction. So we already know fully well that the static frictional force is equals to the coefficient of the static friction multiplied by the normal force. The coefficient of static is usually greater than the coefficient of kinetic. Right. You will see why I'm mentioning that in this question as we do 2.3.2. So what information do we have? Do we have the frictional force? Maybe. Let's take a look and see what we have here.
we are actually not given the frictional force, right? The static frictional force. So how the hell are we supposed to calculate it? But do we have the coefficient? The coefficient is what we're interested in. So obviously we don't have that. What about the normal force? Well, the normal force, we can calculate it, right? Because there's no Fy, the normal force is just going to be equals to the weight. So the normal force, 8.5 multiplied by 9.8. So let me just put this in my calculator and see what happens. My calculator is in scientific, so let me put it back to normal. So we have 83.3 Newton. This is the normal force. And then the coefficient is what we're interested in. So how can we calculate the static frictional force? How can we possibly calculate that? Okay, let's take a look at our scenario here. In 2.2, we have a free body diagram, right, of the crate just before it starts moving. Just before it starts moving, the frictional or the static frictional, it is supposed to be, because it's just before it starts moving, should be equals to the tension, right? But how can we calculate the tension? We are given this diagram here, right? You can see that when the hanging mass is 4.2, our crate starts moving, because that's where we start having a bit of acceleration, right? Right here at 4.2. So the static frictional force is equals to the tension, right? But the tension here on the mass hanger with the mass pieces is just equals to the weight, right, of that object. So that is, what is the mass of that thing? Let's take a look. The mass is 4.2 when we start having an acceleration, and acceleration due to gravity is 9.8. So we have 4.2 multiplied by 9.8, which is equals to 41.16. So we have the static frictional force. So now we can see 41.16 is equals to the coefficient multiplied by 83.3. So the coefficient is going to be equals to 41.16 divided by 83.3, which is equals to 0.49. So that is 2.3.1. Let's take a look at 2.3.2. We are looking for the magnitude of the acceleration represented by y on the graph if the coefficient of kinetic friction between the crate and the table is 0.4. So take a look at this. The coefficient of kinetic friction is 0.4, and we calculated the coefficient of static friction to be 0.49. So we are quite convinced that the answer we have in 2.3.1 is correct, because if the coefficient of kinetic friction was greater than this one for static friction, we should be worried, because we know fully well that that should not be the case. So there we go. We have the coefficient of kinetic friction, and then what else do we have? We are looking for the acceleration at y. So we do have the mass, we have the hanging mass, right? So the hanging mass is equals to 7.4. Let's concentrate on the crate. If we concentrate on the crate, F net is equals to ma. We know that fully well. And then the force that is pulling the crate is the tension minus the frictional force that opposes. And this is equals to ma, right? So what is the tension? We don't have the tension at this point. What about the frictional force? We have the coefficient, right? So this is 0.4 multiplied by the normal force, which is 8.5 multiplied by 9.8, 83.3. So we have 83.3, and then this is equals to 8.5a. So tension minus, so 0.4 multiplied by 83.3, and this is equals to 33.32, and this is equals to 8.5a. Okay, so it seems like we are we are stuck here. We have the tension, we have the acceleration, and we have two variables, right? So we need another equation. So let's concentrate on the mass hanger. The mass hanger, the free body diagram, it should be the weight and the tension, right? So why is it going down? It is going down because of the weight. So weight minus tension is equals to 8.5, not 8.5a, but the mass of the hanger, which is 7.4a. So the weight 7.4 multiplied by 9.8 minus the tension is equals to 7.4 A. Okay. Obviously, in place of tension, we can substitute. We can make the tension the subject of the formula in this equation. So it is going to give us 8.5 acceleration plus 33.32. So instead of having tension there, we can say 7.4 multiplied by 9.8, which is 72.52 minus 8.5A minus 33.32 is equals to 7.4A. So minus 8.5 minus 7.4, and that is minus 15.9A. This is equals to 72.52 minus 33.32. It is equals to 39.2. But when you take it to the other side, it is going to be minus 39.2. So the acceleration is equals to minus 39.2 divided by 15. Is this 15.9 or 15.19? I forgot what that it is, what I wrote there, because it's not clear. So minus 39.2 divided by minus 8.5 minus 7.4. I can just do that because I'm not sure what I wrote there anymore. So the acceleration that I'm getting is 2.47 meters per second squared. That is the answer to 2.3.2. And here's the question for you, 2.4. A 5 kg block is now placed inside the crate and the experiment is repeated. How will this affect the maximum static frictional force now experienced by the crate? Okay, choose from increases, decreases, or remain the same. Give a reason for your answer. So what is your answer to 2.4 and why are you saying so? Apart from that, let me know which question you want me to do next. Here we go. So I gotta say, I'm quite disappointed because this year there's no free fall or projectile that we need to define. You know, just like we expect in the previous years, we always had one between free fall and projectile. But anyway, stories, let's take a look. So ball A is thrown vertically upwards at 12 meters per second from the top of the building. 2 seconds after ball A was thrown upwards, ball B is thrown vertically downwards at 5.4 meters per second from the top of the same building. Both balls A and B strike the ground at the same time, T seconds. Ignore the effects of F friction like we always do, and then we're given the position time graph for the two balls. Right, so the first question, 3.1.1, we are supposed to, using equations of motion only, calculate the value of each of the following as shown in the diagrams. And then 3.1.1, we are looking for the time t. So t is the time at which the two balls strike the ground, right? So let me just see the mark allocation. It's 5, so it seems like we might need to do a bit of work there. So if I concentrate on ball A, we have an initial velocity. I always take up as positive, so the initial velocity is going to be 12, which is positive. The acceleration is minus 9.8. And then I'm looking for time t, right? It seems like that is all I have as far as ball A is concerned. That is all I have. So with two variables, I'm not going to be able to calculate the time. I need 3 so that I can pick an equation, and then the unknown will be the fourth. Okay, let me try the second ball, ball B. It is thrown downwards at a velocity of 5.4 meters per second. The acceleration minus 9.8. We are looking for time t. So there we go again. We don't have enough variables, but we have two balls. Can we work simultaneously? Can we use ball A and ball B in order to find our time t? Let's give it a try. So if we focus on ball A first, so which equation do we want to use? We want to use an equation that involves delta y. Why am I using delta y? Why am I choosing to take delta y as the fourth variable? Because they are thrown from the same height. So at time t, when they strike the ground, they have the same displacement, right? So for ball A, delta y is equals to vi delta t plus a half acceleration delta t squared. So vi is 12. Time is what we're interested in. Plus a half minus 9.8, let's say t squared. So delta y will be equals to 12t minus 4.9 t squared. This is as far as ball A is concerned. What about ball B? When we go to ball B, delta y is going to be equals to minus 5.4 t, right? And then plus a half minus 9.8. I know that he's going to give me minus 4.9, but I'm just choosing to write it as it is because I don't want to go to the answer without substituting because I'll lose marks. Well, I'm not going to lose marks, but if you do it, you lose marks in the exam. But anyway, stories. So ball B was thrown 2 seconds after ball B was thrown. So actually, the time t for ball B should not be t. So if you made that mistake, you don't get the answer, right? The time t for ball B is actually t minus 2 because it was thrown 2 seconds later and then it strikes the ground at the same time with ball A. So don't make that mistake. If you make that mistake, then you don't get the answer. I'm sure somebody did make that mistake. And then plus a half acceleration minus 9.8, right? So here we're also going to have t minus 2 squared. This is because it was thrown 2 seconds after ball A was thrown. So delta y is going to be minus 5.5 t plus 10.8. Let me just verify, because in the exam you will substitute 2 multiplied by 2 in the calculator because you don't want to make any mistake. So this is 10.8 and then minus 4.9 and then we have t minus 2 squared, right? So that is going to be t squared minus 4t plus 4. Yeah. If you don't see why that is the way it is, you probably got the question wrong either way. Okay, delta y will be equals to minus 5.4t plus 10.8 minus 4.9 t squared. So 4.9 multiplied by 4. So this is plus 19.6 t, right? And then what? Minus 4.9 multiplied by 4 again. So plus 19.6 t. Is it plus? No, it is minus because we have minus multiplied by plus. So we have minus. So let's just verify here because it seems like there's a lot going on. This is fine. This is fine. T squared minus 4t plus 4. This is fine. Minus 4t squared is fine. Plus 16t is fine. And then here we're supposed to have minus 19.6, not minus 19.6t. So, okay, that was another mistake. Yeah, it's always important to verify. So, delta y, so let's add the like terms. So, minus 5.4 plus 19.6, right? That gives me 14.2. So, we have 14.2t. And then 10.8 minus 19.6 minus 8.8. So minus 8.8 and then minus 4.9 t squared. It does not have a like term, so minus 4.9 t squared. So we can equate these two things, these and these. We can equate those because they are both equals to delta y. So 12t minus 4.9 t squared is equals to minus 4.9 t squared plus 14.2 t minus 8.8. Okay, let me just verify. Yeah, this is fine. 12t minus 4.9 t squared. Okay, that is fine. So obviously we have minus 4.9 t squared plus 4.9 t squared, right? So we can just drop that. So we're left with 12t is equals to 14.2 t minus 8.8. Okay, so 12 minus 14.2, I'm getting 12 minus 14.2, I'm getting minus 2.2. So minus 2.2 t is equals to minus 8.8. So t is equals to, so 8.8 divided by 2.2, I'm getting, what do I get? 8.8 divided by 2.2, I'm getting 4. So time t is 4 seconds. So this takes 4 seconds. Okay, there we go. That is 3.1.1. It's a lot of work, to be honest. Yeah, 3.1.1. It's a lot of work. What about 3.1.2? we are looking for the value of z. So z is the height from which the two balls were projected, right? So we, how many marks? 3. Not sure it's worth 3 marks. Okay, but either way, delta y is equals to, we can take one between the two equations. Let's take 12t minus 4.9t squared, right? And then we know that t is equals to 4 when the two balls strike the ground. So when we substitute here, we shall get delta y, which is z. So 12 multiplied by 4 minus 4.9 multiplied by 4 squared is equals to, so 12 multiplied by 4 minus 4.9 multiplied by 4 squared. This is minus 30.4. So z is equals to 30.4, right? It is in meters, right? But z is just going to be 30.4. Yeah, because the meters is here in position, right, on the brackets there. But yeah, the two balls are projected 30.4 meters above the ground. Okay, what about 3.1.3? We are looking for the value of y. So y is the maximum height reached by a, right? So if I still remember a, the initial velocity is 12, the acceleration is minus 9.8. Maximum height, we know that vf is equals to 0, right? And then we are looking for delta y, right? So let's do that. Vf squared is equals to vi squared plus 2a delta y. So we have 0 squared being equals to 12 squared plus 2 minus 9.8 delta y. So delta y is equals to minus 12 squared divided by minus, well, 2 multiplied by minus 9.8, right? So delta y is equals to, so 12 squared divided by 19.6. This is 7.35 meters, right? But y is not going to be 7.35 meters, right? Y is going to be equals to 30.4 plus 7.35. I know we just lost some people there. I know somebody didn't add the two numbers. So y is equals to 37.75 meters. So there we go. That is the value of y. And then 3.2, we are supposed to, on the same set of axes, sketch the velocity time graphs for ball A and B while they're in free fall. Okay, so let's do that. Well, let's have our axis first, right? That's v, that's t. So t in seconds, v in meters per second. So the initial velocity of ball B is 12. So 12, I'm taking up as positive. And that of B is minus 5.4, right? We know that the time t here, we can just put it as t, but we know fully well that it is 4 seconds. Okay. And then the second ball is projected 2 seconds after, right? B is projected 2 seconds after. So here we have ball A. Ball A starts there. And then ball B will start somewhere here, which is 2 seconds after. So what happens to ball A? Ball A reaches maximum height after some time. And then it goes on to strike the ground at time t. Yeah, which is somewhere there. And then what? Let me just draw a straight line here. On the same set of axes. Okay, the question says sketch, so I wanted to ask if you had a graph paper, but I don't think you had. Okay, so I'm putting those dotted lines there so that I can be as accurate as I can be, right? So that is for ball B, and then for ball A rather. Ball B is projected downwards, so it starts here and then stops at time t. So you're supposed to have something like this as far as the velocity time graph is concerned. So there we go. Write down the principle of conservation of mechanical energy in words. That is 4.1. So usually, if in 4.1 I'm defining the principle of conservation of mechanical energy, I'm assuming that in 4.2 I'm going to have to use that principle. Usually it is the principle of conservation of linear momentum, and then we would use it in the equation that follows, right? But here we have the conservation of mechanical energy. So I'm expecting that that's what we're going to use in 4.2. But let's go ahead and see if that is actually the case. So we have two trolleys A and B of masses 1.5 kgs and 2 kgs, and then they're stationary, and then between the two of them there's a compressed spring, right? The trolleys are released and the spring takes t seconds to return it to its natural length, right? The spring then falls to the ground. Trolley A moves to the left while trolley B moves to the right. We can clearly see here after the spring is released. Trolley A then moves to the left while trolley B moves to the right, and then trolley B goes up a frictionless inclined plane, rising to a maximum height of 1.5 meters as shown in the diagram below. So 4.2, calculate the speed of trolley B at the bottom of the inclined plane. Okay, so let's see what we can do here. So obviously the first thing that we're going to try out is the conservation of mechanical energy. If it doesn't work out, then we can try other things. But the most organic step should be the conservation of linear momentum, of mechanical energy, not linear momentum. So let's take a look at the cart B. Is it a cart? No, it's a trolley. So let's take a look at B at the bottom of the incline, and then also take a look at it at the top of the incline. So at the bottom of the incline, that is where we are interested in its velocity, right? Let me just say V and then to VF. So we are interested in this velocity at the bottom of the incline. But what else do we have? We just have the mass. That's all we have, right? The mass is 2 kgs. And then at the top of the incline, so the question says that does it reach a maximum height? That's what I want to see, because if it reaches a maximum height, I know that the velocity is 0 there. So it rises to a maximum vertical height. So okay, V is equals to 0 at the top, because that is the maximum height. The mass is still the same, but we have the height, which is 1.5 meters. Here we can say that the height is equals to 0. So this information looks like it is enough for us to use the conservation of linear momentum. We know that the mechanical energy, the total mechanical energy at the bottom should be equals to the total mechanical energy at the top. This is because our track does not have any friction, right? It is frictionless. So we can use the conservation of mechanical energy. So at the bottom, we're going to have EP plus EK, right? Potential energy plus kinetic energy. At the top, we're also going to have EP plus EK. So what is the potential energy at the bottom? We know that the potential energy is mgh, right? So the mass is 2, gravitational acceleration is 9.8, the height is 0. What about the kinetic energy? Half, mass is 2, v squared. That's what we're interested in, right? And then at the top, mechanical energy is 2, 9.8, the height is 1.5. But the kinetic energy at the top is actually equals to 0, because we know that at the maximum height, the velocity is 0. So we have 0 squared there. So this gives us 0, 2 divided by 2 is 1. So we have v squared being equals to. This gives us 0. So let me just put that in my calculator. 2 multiplied by 9.8 multiplied by 1.5. 2 multiplied by 9.8 multiplied by 1.5. That is 29.4. So we have 29.4. So v is equals to 5.42 meters per second. The question says speed, so we don't have to give any direction. We can just leave it like that. Okay, and then 4.3.1. For the t seconds that the spring takes to return to its natural length, calculate the change in momentum of trolley B. Change in momentum of trolley B. So change in momentum delta P, which is m multiplied by Vf minus Vi. We can use this to find the change in momentum, right? So let's see. Before the spring is released, the initial velocity of both trolleys A and B is 0, right? And then after the spring is released and then it is at its full length, B is climbing up the incline with a velocity of 5.42 meters per second to the minus 1, right? Up the incline to the right. Okay, so we are looking for the change in momentum. Well, momentum is a vector, so we need to decide on a direction. Let's take direction to the right, it's positive, right? So we're going to have delta P being equals to the mass 2. Vf is 5.42. Vf is 5.42, right? Minus Vi. VI is 0, right? VF is not 0. VF is 0 there at the top. Here we have 5.42, and here we have 0 once more, right? So don't confuse, don't take, well, 5.42, it's our VF when the spring is lengthening, and it is our VI when we are going up the incline, right? So most people, they sort of confuse the two, right? So 2 multiplied by 5.42, this is equals to 10.84. So kg meters per second to the right. To the right. This is the change in momentum of trolley B. While trolley A, write down the change in momentum of trolley A, that is 3.2, right? So it is going to be the same. It is going to be the same, but in the opposite direction, right? It's easy to prove because we know that F net is equals to delta P over delta T, right? So these A and B will experience the same force. We cancel time and time, we end up with delta P being equals to delta P, but in the opposite direction because of Newton's third law. So the change in momentum of ball A, or trolley A, not ball A, will be 10.84 kg meters per second. Where? To the left. All right. Maybe what we can talk about is the SI unit here. The question is saying change in momentum. It is not saying impulse. So should the SI unit be kg meters per second, or should it be newtons multiplied by second? Which one between the two? Kg meters per second or newtons multiplied by second? Right. I think the impulse, right, will be kg meters per second, but the change in momentum will actually be newtons multiplied by second. So let me know in the comments, which SI unit did you use? Did you use kg meters per second, or did you use newtons multiplied by second? I think that is another thing that we need to figure out here. So I'm interested in your answer for this question. Is it in kg meters per second, or is it newtons multiplied by second? And why are you saying so? Right. Again, I think this is one of the things that probably there's going to be a lot of disagreement on. Do we use both? Do we have the freedom of choice? Are we supposed to use one? Let me know in the comments. All right. And then 4.4, calculate the speed of trolley A after t seconds. So now we can use, because we know here we have 0, 0, here we have 5.42, and here we have an unknown speed. So that is the speed that we are looking for. We can obviously use the conservation of linear momentum. So the conservation before should be equal to the total momentum before, right, should be equal to the total momentum after, right? So before we have 1.5 plus 2, because, well, we can even separate them if you want that. We have 1.5 multiplied by 0 plus 2 multiplied by 0, right? And after we have 1.5 multiplied by V plus 2 multiplied by 5.42. Okay, so 0 is equals to 1.5 V, and then 5.42 multiplied by 2, not 1 point something. So 0 is equals to 1 point, I've already written it there. So here I'm supposed to have plus 10.84. V is equals to 10.84 divided by minus 1.5. This is equals to minus 7.23 meters per second. So we're looking for the speed. So let me just say 7.23 meters per second and not worry about the direction. There we go. Define the term work done by Air Force. Well, I have to agree. In this exam, the definitions are quite brutal. In question 2, we are defining static friction. In question 3, we don't have a definition. In question 4, we are defining the conservation of mechanical energy. And in question 5, we are defining work done by a force. What? I can't even remember the last time I came across a question and we had to actually define work. But here we go. That's what we're supposed to do. That is 5.1. Let's take a look at 5.2. Draw a label free body diagram showing all the forces acting on the crate as it moves. At least in 5.2, we're supposed to draw a free body diagram showing all the forces. Because in question 2, we're supposed to draw a free body diagram showing only the horizontal forces, not vertical forces. Right? You include the vertical forces and you probably lose some marks. Okay, so let's read the questions. Let's go through the question statement and see what is happening. A constant force F is applied at an angle of 30 degrees to the horizontal on a crate of mass 6 kg that is initially addressed as shown in the diagram below. Easy to see. A constant frictional force of 10 Newton acts on the crate as it moves from rest at point A along a horizontal surface to point B. The distance between point A and point B is 1.5 meters. The speed of the crate at point B is 2 meters. So we have 2 meters per second there. Okay, so we need a free body diagram for the crate. And the mark allocation is 4 marks. So first things first, we need the weight, right? We put the weight first and then we think after, right? Because we know that the weight is going to be there. So that arrow there, we're going to put the weight. And then we have the normal force, obviously, because it is resting on a surface. And then we have the applied force, which is at an angle. Do we have a frictional force? Yes, we have a constant frictional force. So I think that is all the forces that we need. Okay, so we have the force applied. We have the weight, normal force, and the frictional force. So 4 marks, 4 forces, seems like we're good to go. Let's take a look at 5.3. Use energy principles, using only energy principles, calculate the magnitude of force F, that is for 4 marks. Okay, so let's see. We have a free body diagram. We have the velocity at A, which is 0, and then we have a velocity at B, which is 2 meters per second. So because we are given the velocity at A and the velocity at B, it seems like we should be able to use the work energy theorem, right? Which says that work net is equals to the change in the object's kinetic energy. Right, but this can work, and work non-conservative should also work. Yeah, I can see that it is also going to work. But if we use work net is equals to the change in the object's kinetic energy, right? But it is also equals to the work, right? The summation of all the works done by the individual forces. So the frictional force does some work on the object, and the horizontal component of the applied force also does work on the object. So we're going to have the work done by the frictional force plus the work done by the horizontal component of the applied force being equals to the object's change in kinetic energy. So the work done by frictional force is going to be Fr multiplied by delta x multiplied by cos of 180 plus the work done by the horizontal component of the force applied. So that is Fx delta x cos of 0. It's cos of 0 because the object is going from A to B, right, which is the same direction as the horizontal component of the force applied. And this should be equals to half mvf squared minus a half mvi squared. So let's go ahead and substitute. Frictional force is constant at 10 newtons. So we have 10 multiplied by the displacement 1.5 cos of 180. Now let's come to the horizontal component of the force applied. Obviously, because it is a flat surface, it is going to be F cos of theta, right? So we have F is what we are looking for, and then cos of 30 degrees, right? This is the horizontal component of the applied force, and then multiply by delta x, which is 1.5, and then cos of 0 because they're in the same direction. This is equals to a half. The mass of the object is 6 kg, so we have 6 vf squared. Oh, we have all these velocities. So vf is 2, right? So 2 squared minus a half. The mass is 6. The initial velocity is 0 squared. Okay, so 10 multiplied by 1.5 multiplied by cos of 180. This is minus 15. So we have minus 15, and then cos 30 multiplied by 1.5 multiplied by cos of 0. This is plus 1.299 f being equals to, so right hand side 1 over 2 multiplied by 6, 2 squared, minus 1 over 2 multiplied by 6, 0 squared. This is 12. So 1.299f is equals to 12 plus 15, which is 27. So this is 27. So f is equals to 27 divided by 1.299. So f is 20.79 newtons. Right, we only need the magnitude, we don't need the direction. So that's it. So let's just verify and see if what we did is correct. This is the constant frictional force. This is the right displacement, cos of 180 minus 15. Seems good. Cos of cos 30, maybe I can just substitute that in my calculator. Cos 30 multiplied by 1.5, that is 1.299. So I'm happy with this, right? And then 6 divided by 2, that is 3, 4, that is 12. 12 plus 15, yeah, seems good, seems good. So that is the applied force. Okay, and then 5.4, I want you to tell me the answer to this question. What did you write? A 2 kg block is placed in the crate. What effect will this have on the work done by the same force when the crate is again moved from point A to point B? Right, only increases, decreases, or remain the same. So is the work done by the applied force going to increase or decrease when we add the 2 kg block on the crate? Or is it going to remain the same? Let me know in the comments. Here we go. Name the phenomenon that explain why the wavelengths shown in the graph differ. I think all the time in question 6, when we come across something like this, we know what the answer is already. Doppler effect. And then question 6.2 is the car moving towards or away from the listener. Give a reason for the answer. Now we have to go through the question statement. A stationary listener standing on the roadside records the wavelength of the sound emitted by a siren of a police car traveling at a constant velocity. In the wavelength time graph below, not drawn to scale, wavelength of the listener is the, well, wavelength with the subscript of L, right, is the wavelength of the sound recorded by the listener, while the one with a bit of an S here is the wavelength recorded by, well, the wavelength of the sound emitted by the siren. And then we're supposed to take the speed of sound in air as 343 meters per second. So is the car moving away or towards the listener? The listener is stationary. So what is influencing the wavelength that the listener observes is the motion of the car, whether it is moving away or towards. So take a look at this. The frequency of the listener, or not the frequency, but the wavelength observed by the listener is greater than the wavelength observed by or emitted by the sound source. But wavelength and frequency is inversely proportional to the wavelength, right? So this simply implies that the frequency emitted by the source is greater than the frequency observed by the listener. So if the frequency observed by the source is, so if the frequency emitted by the source is greater than the frequency observed by the listener, what does that imply? It implies that the listener has to be moving away, given that the sound source is stationary. So that is the answer to 6.2. And then 6.3.1, calculate the frequency of the sound emitted by the siren. Well, we have the wavelength of the sound emitted by the siren, so it should be quite easy to calculate the frequency. F is equals to V divided by the wavelength. We are told that we are supposed to take the speed of sound in air as 343 meters per second. So we have 343 divided by 0.38. It's already in meters, so we don't have to change anything there. So 343 divided by 0.38, this gives us 902.63 hertz. This is the frequency emitted by the source. 6.3.2, magnitude of the velocity of the car. That is actually the last question in question 6. So we are looking for the velocity of, well, the car. Is the listener the one who is stationary, or the car is the one that is stationary, our sound source? Let's go through our question statement again. A stationary listener. Okay, so the listener is stationary. So the listener is stationary. It is the car that is moving away, right? So the answer here is still away, but it is actually the sound source that is moving and not the listener. The listener is stationary. It's the sound source that is moving away. Okay, so magnitude of the velocity of the car. So this is the velocity of the sound source that you are looking for. We have the frequency of the sound source because you've calculated it. We have the velocity of, well, the speed of sound in air. It is given to us. Velocity of the speed of sound in air, it is just v, it is given to us, right? Magnitude of the velocity of the car, so we are looking for vs. We have vl because the listener is stationary, which is 0. And then what about the frequency observed by the listener? We can calculate that because we are given the wavelength, right? Not the we are given the wavelength, but we can calculate the frequency. It is going to be equals to 340. Well, okay, let's leave that for now, but we can calculate it, right, as we move forward. So with these variables, we can say FL is equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. So FL, the frequency observed by the listener. So we're going to say 343 divided by the wavelength, right, which is 0.4. So this is the frequency observed by the listener. And then we have V, which is 343. The listener is stationary, so plus or minus 0. And then we have 343. The sound source is moving away, so we're going to have plus Vs multiplied by the frequency emitted by the sound source, which is 902.63. So 343 divided by 0.4, this is 857.5, and it is equals to 343 divided by 343 plus Vs multiplied by 902.63. Let's divide both sides by 902.63. If we do that, we're going to get 0.95 being equals to 343 divided by 343 plus Vs. Let's cross multiply. So 0.95 multiplied by 343, this is 325.8506, right? And then plus 0.95 Vs. This is equals to 343. So Vs is going to be equals to 343 minus 325, 32, not 3, 32.5. 325.8506, everything divided by 0.95, the coefficient of Vs, right? So let me just put that in my calculator and see what I get here. I'm getting 18.05. So Vs is 18.05 meters per second. There we go. That is question 6. So we have done question 2, 3, 4, 5. If you haven't watched that, click on the channel and you'll find those videos. Which question do we go to next? Let me know in the comments. Here we go. Calculate the magnitude of the electric field at X. Let's go ahead and take a look at that. So 7.1, P is a 2 nanocoulombs point charge, as we can clearly see, right? X is a 0.6 centimeters away from charge P, as shown in the diagram below. We just want the magnitude of the electric field at X. Should be an easy question to answer. So 7.1 E is equals to KQ divided by R squared. So K is 9 times 10 to the power 9, right? It's a constant. But because I'm writing the final exam and I don't want to make any mistake, I will actually verify on the formula sheet, right? Because what if it's minus 9? Well, it is still plus 9. 9 times 10 to the power 9 multiplied by the charge of P. It is 2 times 10 to the minus 9, not minus 6, right? And then divided by R squared, which is in centimeters. So we need to convert to meters. So in 1 meter, we have 100 centimeters. So we divide by 100 and we square that. Now I just need to press my calculator. So 9 times 10 to the power 9 multiplied by 2 times 10 to the minus 9, 6 over 100, and we square that. I get 5,000. So we have 5,000. What is the SI unit? We know that E is equals to F over Q, right? So the SI unit is newtons per coulomb. That is 7.1. Let's take a look at 7.2. Point S with a charge of minus 2 nanocoulomb is placed 4 centimeters away or to the right of charge P, as shown in the diagram below. Draw a resultant electric field pattern due to charges P and S. Okay, so P is positive, S is negative. Okay, so they will attract. So what are we expecting? Let me just do that again. We are expecting the charges, well, not the charges, but the field lines to be pointing away from charge P and pointing towards charge S, as S is negative, right? And then let's just go ahead and have some more field lines, right? So they're pointing towards the positive sphere and they point away at the negative sphere, right? So we have something like this. Yeah, actually, P is positive and S is negative. We expect the field lines to point away from P, right? Because it is positive, and point towards S because it is negative. Okay, so let me just write that nicely. So these charges are supposed to point away from P. Let me just add all the field lines that I'm going to use here, and then I'll worry about the direction after, right? So the field lines are pointing away from the positive sphere. So this is what away looks like, the point away from the positive sphere. And then the negative sphere, the point towards the center, right? The point towards the negative sphere. So the positive sphere away, and then from the negative sphere's point of view, it is towards. So this is what we're supposed to have for 7.2, right? 7.3.1, we're supposed to define Coulomb's law. So I'm gonna leave that to you, right? The square distance between the charges, not between them, not between their centers. When it comes to Coulomb's law, we don't say between the centers. That is gravitational law. So if you did say between the centers here, when you at the end of the definition, that is wrong. It's not between the centers. It's just between the charges. Right? We don't talk about the center of a charge here. So that is 7.3.2 or 7.3.1, I mean. And then 7.3.2, what is the polarity of charge T? Choose from positive or negative. Let's go through the question statement and see what is happening. A third point charge T is placed 2 centimeters to the right of S as shown in the diagram below. Point charge T experiences a net electric field force of 2.5 times 10 to the minus 4 newtons to the left. Okay, to the left. And then we're supposed to figure out whether it is positive or negative. So let's take a look at the two cases where it is positive, right, and where it is negative. Okay, so if it is positive, S and T will be attracting, right? So this will be the force as a consequence of S, because S and T will be attracting. But what about the force as a consequence of P? P and S have the same magnitude, but because P is so far away, we expect the vector to be smaller. We expect the magnitude of the force as a result of P to be smaller. This is if T is positive, right? Let's take a look at when T is negative. If T is negative, this will be the force as a result of S, because they will be repelling each other. But because P has the same magnitude as S and is far away, this makes sense to be the force as a result of P, right? So in this case, when we look at our situation, what do we have? We know that the net electric force is to the left, right? So it means that at T, we have a positive charge because the resultant is to the left when T is positive. As you can clearly see here that Fs would be greater than, here Fs would be greater than Ft, P. So it is easy to see that at point T we should have a positive charge, right? Because if it is positive, then the net electric will be to the left. And then 7.3.3, we are supposed to actually calculate the magnitude of charge T. Let's go ahead and do that. So F net will be equals to, this is our scenario, right? We are basing everything on this scenario. So Fs will be equals to Fs minus Fp. I'm taking direction to the left is positive here, right? So what is F net? F net is 2.5 times 10 to the minus 4. What is Fs? Fs is going to be, we'll know fully well that F is equals to K, Q1, Q2 over R squared, right? And we want the charge at T. So Fs is going to be 9 times 10 to the power 9. The magnitude of the charge S, 2 times 10 to the minus 9, multiplied by Qt. Everything divided by the distance between S and T. It is 2 centimeters. So 2 over 100, converting it to meters squared, right? And then minus 9 times 10 to the power 9, 2 times 10 to the minus 9. That is the charge of P, right? Magnitude of the charge, rather. And then we have Qt divided by the distance between the two spheres. So it is 4 plus 2, which is 6. So we have 6 divided by 100 squared, right? So if we take a Qt as a common factor on the right hand side, we're going to have 2.5 times 10 to the minus 4 being equals to, let me just make this a little bit bigger, right? Being equals to, so I'm taking Qt as a common factor, right? So we are going to be left with 9 times 10 to the power 9 multiplied by 2 times 10 to the minus 9 divided by 2 over 100 squared minus 9 times 10 to the power 9 multiplied by 2 times 10 to the minus 9. Everything divided by 6 over 100. 6 over 100 squared. If we divide both sides by this coefficient of Qt, we get Qt being equals to 6.25 times 10 to the minus 9 coulombs. There we go. 8.1, define the term power. Finally, a definition that you're familiar with, right? It is the rate at which work is done. That is power. P is equals to W over delta T, the rate at which work is done. That is 8.1. Let's take a look at 8.2. So 8.2, if both light bulbs operate as rated, calculate the reading on ammeter A2. So let's go ahead and take a look at our question statement. L1 and L2 are two light bulbs that have the following ratings. We have the power and the voltage of L1, the power and the voltage of L2. The two bulbs are connected as shown in the diagram below. The battery has an internal resistance of 0.6 ohms, while the conducting wires and the ammeters have negligible resistance. R1 and R2 are resistors. Back to the equation 8.2.1, we want the reading on A2. So the bulbs are operating as rated. That is very important. That is information that basically unlocks the equation. What does that mean? It means that the power dissipated by L2 is that which is rated, right? It is that which is given to us, 48 watts. So that is what's going to allow us to find the reading on A2, right? Because we know that the current that passes through A2 is the current that passes through L2, because they are on that same parallel path. So what is the power of L2? It is 48 watts. And then what is the voltage of L2? Voltage dissipated by L2, that is 32 volts. And then what we're looking for, the reading on A2, so that is the current, right? So with these three variables, how do we calculate the current? We know that P is equals to V multiplied by I. The power is 48 watts, right? The voltage is 32, and then the current, well, 32, not 3V, 32, and the current is what we're interested in. So I will be equals to, so 48 divided by 32, that is 1.5. So we have 1.5 ampere as the reading on A2. 8.2.2, we want the reading on A1, right? The reading on A1. The reading on A1. Right. So we need to understand the current that A1 reads. The current that A1 reads is the total current, right? So A1, essentially, we are looking for IT. But take a look at this. When the current divides at this point, a proportion of the current is going to go on this path, while the other proportion of the current goes to this path. So if we calculate the current that passes through L2 and the current that passes through L1 and add those two, we have the current that is read by A1, the total current. So the current that is read by L2, let's call that I2. We calculated it to be 1.5 ampere. Let's calculate the current that is read by, not that is read by, but that passes through L1, because there is some current that passes through L1. If we can find a way to calculate the current that passes through L1, we will have the total current, because L1 is also operating as rated. So what information do we have as far as L1 is concerned? Well, we have the power, which is 36 watts. We have the voltage, which is the potential difference, which is 20 volts. So P is still equals to V multiplied by I. The power is 36. The voltage is 20. We are interested in the current. So the current is going to be equals to 36 divided by 20, which is 1.8 ampere. So this is I1, right? I2 is 1.5. So the reading on E1 will be equals to 1.5 plus 1.8. So this is 1.5 plus 1.8. Let's see, supposed to be 3.3, right? That is what we're getting, 3.3 ampere. But we're in the final exam. We don't want to make any mistake. We will literally punch in the calculator 2 multiplied by 2, even though we know that it is 4. So that is 8.2.2. Let's take a look at 8.2.3. So 8.2.2 said, let's find the reading on A1, right? And A1 reads the total current. I was just making sure that I didn't miss anything. 8.2.3, the resistance of R1. We are looking for the resistance of R1. Okay, so how can you find the resistance of R1? We have the resistance of R2, which is 4 ohms, right? And then what else do we have? We have the, we don't have the EMF, but we have the internal resistance, and we have the total current. So the total current, we know that it is equals to 3.3 ampere. So can we use the total current to find the resistance of R1? Yes, we can. How? I'm glad you asked. We know fully well that VP is equals to IT multiplied by RP, right? So do we have VP? Because if we have VP, we can easily then calculate the resistance on R1. Okay, so let's see. Let's take a look and see if we can do that. We know the voltage that is dissipated by R2, right? But do we know the voltage that is dissipated along the two parallel paths? Well, we can calculate VP using we can calculate VP using the voltage across this path, right? Because think about it, we say that in series there's different potential differences, right? That's in series. But in parallel, the potential difference is the same and the current differs. So VP can also be equals to the voltage that is dissipated by L2. VP is equals to the voltage that is dissipated by L2. It is equals to 32 volts, right? So the voltage across this path, right? Let's call this path X, and the voltage dissipated across the path Y, they should be the same, right? But we already know that So we're saying that V of R1 plus V dissipated by L1 should be equals to VP, right? Because R1 and L1, that's the only two spots where there's voltage being, there's a potential difference, right? So V of R1, we can calculate that because we know V of L1. V of L1 is 20. So we have 20 being equals to 32. So V of R1 is equals to 12, right? 32 minus 20. So there we go. So V of R1 is equals to 12. But we know the current that passes through R1. So V of R1 can also be equals to I multiplied by R. So V of R1 is 12. We know the current that passes through R1. We calculated it in 8.2.2. It is, so let me see, 8.2.2. It is, so let me check, 36, that is for R1, for L1, and then 20 volts. The current is 1.8. So 1.8 passes through R1. So the current is 1.8 and then multiplied by R. So R is equals to 12 divided by 1.8. This is 6.67 ohm, right? So the resistance across the path at the top, oh, okay, we don't have the resistance of L2, but we don't need to calculate it. So this is one way you can use to calculate the resistance of R1. But already you can see that when I'm trying to solve this problem, there's a couple of ways that are presenting themselves. So if you use a different method and you still got 6.67 ohms, you're still good, because clearly there's a couple of ways we can use to actually answer this question. And then 8.2.4, we are looking for the EMF. So 8.2.4, we are looking for the EMF. So we should be able to calculate the EMF directly because we have everything else but the EMF. EMF is what we're interested in. Internal resistance, we have that. Total current, we have that. External resistance, do we have that? That's what we need to calculate, right? So RS is equals to 4 ohm. We only have one resistor which is in series, which is R2. And then RP, okay, so RP is equals to, I don't like using this one actually, I like using 1 over RP for some reason. It's equals to 1 over R1 plus 1 over R2. So 1 over RP is equals to 1 over the total resistance on one path. The total resistance on one path. Okay, so it seems like we actually do have to calculate the resistance on L2 and L1. We don't have a choice anymore. Okay, that is one approach. One approach can be calculating the resistance of L2 and L2, of L2 and L1, and then calculate EMF using EMF is equals to IT multiplied by R external plus R internal. But another way that is becoming apparent to me and seems easier is if we say EMF is actually equals to V internal plus V external, right? So V internal is equals to current multiplied by the small r, right? Current multiplied by the small r. We have the current 3.3, right? So is it 3.3 or 3.2? 3.3. Okay, so we have 3.3 multiplied by 0.6, right? So 3.3 multiplied by 0.6, that is 1.98 volts. Okay, and then V external, there's two places where there's a potential difference across VP and across this R2, right? So V external will be equals to VP plus the voltage that is dissipated by R2. So VP, we already know that it is 32. VP is 32. Now let's calculate the voltage dissipated by R2. So R2, the current that passes through R2 is 3.3 because that resistor is in series. And the resistance of R2 is 4. So let's add these. 32 plus 3.3 multiplied by 4. This is 45.2. So EMF will be equals to V internal 1.98 plus V external 45.2. So let me just add this 45.2 plus 1.98. Okay, 45.2 plus 1.98. Yeah, this is equals to 47.18 volts. Right, that is the EMF of the battery. Yeah, obviously there's other ways of doing it, as it is quite clear. 8.3, bulb L1 burns out after a while. Assume that the resistance of bulb L2 remains constant. Will bulb L2 continue to glow after bulb L1 burns out? Choose from yes or no. Support your answer with a suitable calculation. So I'm thinking that it will continue to glow. So L1 burns out. First of all, we need to understand the consequence of L1 burning out. If L1 burns out, there's no current that is going to pass through here, right? There's no current that is going to pass down that path. So that path is essentially out of play. That is the consequence of L1 burning out, right? It's not gonna short circuit the circuit. Usually when bulbs burn out, they just act as a voltmeter of some sort, right? There's no current that passes anymore. It does not short circuit the circuit, right? So this path is gone. This path is gone. That path is gone. We can forget about that path. Okay, so even if that path is gone, there are some things that are still true. The internal resistance is still 0.6. The EMF is still 47.18. This is still true. What will change is IT, right? But R external, we can still calculate. R external will be L2 and R2, right? Because these two resistors are still in play. So R external is equals to, the resistance of R2 is 4. We don't have the resistance of L2, but we can use the information that is given there to calculate the resistance of L2, because the resistance remains the same, right? So we can still use that information. It's still relevant. So we have the power, we have the voltage. How do we calculate the resistance? P is equals to V squared over R. So R should be equals to V squared over P, right? So V is 32. So 32 squared over 48. This is equals to, so 32 squared, okay, 32. My calculator is in stats, so I cannot write divide, but I just fixed that. So 32 squared divided by 48, that is 21.3333 ohms. So this is the resistance of L2. So R external is going to be 4 plus 21.3333, right? What I'm about to conclude, we can conclude it without actually doing this calculation, but the question says let's calculate, so I'm just respecting that. So 25.3333 ohm is the new resistance. So what will happen to the total current? The total current will be close to the EMF, right, divided by R external 21.3333 plus R internal 0.6. This is coming from EMF is equals to IT R external. I'm actually doing this for myself to see if I'm doing it in the correct way. So IT, clearly it is equals to EMF divided by these two things. Okay, now I'm convinced that I'm doing it the correct way. So IT is equals to EMF 47.18 divided by the total resistance, which is 21.3333 plus 0.6. This is equals to 2.15. So the current, initially it was 3.3 ampere. Now the current is equals to 2.15. So the current is decreased. So even though the bulb will still glow, it will glow dim. Right, there we go. Question 8. Let's go to 9. Name the type of generator. Choose from AC or DC. Should be an easy question to answer, right? 9.1. This is DC. Why are we saying that? You can see that the induced current does not change direction. It stays in the same direction. If it goes down like this and forms a cos or sine graph, that would be an AC, alternating current. But in our case, we have a DC generator. That is 9.1. Let's take a look at 9.2. Say the energy conversion that takes place in this generator while it is in operation. So all generators, right? We have mechanical energy to electrical energy, right? That is what generators do. So if it was a motor, it will be electrical energy to mechanical. But because it is a generator, we have mechanical to electrical. We are generating electrical energy through mechanical and sometimes chemical. 9.2. What about 9.3? Give a reason why this generator is not suitable for the transmission of electricity over long distances, right? That is because there's a lot of energy loss in a DC generator over long distances. That's one of the advantages that AC has over DC, in that you can use AC to transport the electricity over a long distance, right? But with DC, there's a lot of energy loss, right? 9.3. 9.4. Calculate the frequency at which the coil rotates in this generator. So frequency is equals to 1 over period, right? So what is period? The amount of time it takes to complete one cycle, one wavelength. So you can see here that we have a half, and then this is another half. So from 0 to 0.02, that is a period, right? We have completed one cycle. So the frequency is going to be equal to 1 divided by 0.02. So 1 divided by 0.02, this is 50 hertz. So there we go. That is the period. 60. Oh, that is the frequency, not the period. 50 hertz. And then 9.5, define the term root mean square current. Well, I'm going to leave that to you. And then 9.6, calculate the root mean square current delivered by the generator. Well, let's go. We know that IRMS is equals to I max divided by square root of 2. Okay, so we can see here there that we have 1.2 divided by square root of 2. So let me just put that in my calculator. I'm getting 0.85 ampere. 9.6. What about 9.7? The graph below shows how the induced current varies with time after a change was made to the operation of the generator. Okay, so first things first, the Imax is no longer 1.2, but it is now 0.6, right? And then the period is no longer 0.02, it is now 0.04, right? So fully describe the change that was made. Okay, so let's do it like this. I'm going to comment on the period. I want you guys on the comments, on the comment section, to comment on the current that is induced. What do I say about the period? I'm going to say that the time taken to rotate the, what are we rotating? I'm seeing if we're given a specific word here, right? Well, the time taken to complete one cycle has been halved, right? That is why it takes twice as much time to complete one cycle, right? That's what we can see as far as the period is concerned. The rotation of the coil has been halved. That's why it takes twice as much time to complete one cycle. And what are you guys saying about the current induced? It was 1.2, now it is 0.6. Let's go. Which color of light is responsible for ejecting electrons that have a maximum kinetic energy equal to 2.65 times 10 to the minus 20 joules. There we go. Let's take a look at the equation statement. Red light, blue light, and green light are shown simultaneously on a sheet of potassium, as shown in the diagram below. Each color of light consists of a single frequency. Two maximum kinetic energies of the ejected electrons are possible. Two maximum kinetic energies of the ejected electrons are possible, namely 6.96 and 2.65 times 10 to the minus 20 joules. Each ejected electron has only one of these maximum kinetic energies. Okay, let's go back to our question. Which color of light is responsible for ejecting electrons that have a maximum kinetic energy equal to 2.65 times 10 to the minus 20 joules? So we need to understand what is going on. We need to think about what is going on before we can answer this question. So we have two maximum kinetic energies of the ejected electrons, right? But we have three lights that are being shown on the potassium sheet. So what does that mean when we have two maximum kinetic energies? It means that one of the lights is actually not ejecting electrons. Which one can it be between red, blue, and green? We need to go to our spectrum, right? Red, orange, yellow, ROIG, BIV. So red has the lowest frequency, right? So it's the one that is least likely to eject electrons compared to blue and green, as you can clearly see. So if we have only two maximum kinetic energies, it means that green and blue are ejecting electrons, but the red light is actually not ejecting electrons. So which color of the light is responsible for ejecting electrons that have a maximum kinetic energy of 2.65? So we then need to compare these kinetic energies to the lights that we have. Blue should be the one ejecting electrons with the most amount of energy. Okay, so between 2.65 and 6.96, 6.96 is greater, right? So it should be blue, it should be green that emits electrons with an energy of 2.65, and then blue will emit electrons with a kinetic energy which is greater than that of green, 6.96 in our case. So the answer to 10.2.1 is green, right? Green should emit electrons with less kinetic energy compared to blue. So that is 10.2.1. But in saying that, I've answered 10.2.2 as I'm explaining 10.2.1, right? Because that's what the question says. Explain the answer to question 10.2.1. So 10.2.3, the electrons with the maximum kinetic energy of 2.65 times 10 to the minus 20 joules are ejected by light that is a frequency of 5.85 times 10 to the power 14 hertz. Calculate the frequency of the light that ejected electrons with a maximum kinetic energy of 6.96 times 10 to the minus 20 joules. Okay, so what are we looking for? We are looking for the frequency of the light that emits electrons with a maximum kinetic energy. So EK max, that is equals to 6.96 times 10 to the minus 20 joules. So how can we solve this question? Well, we can just say that the energy is equals to the work function plus EK max. And then energy plus constant multiplied by the frequency, right? Planck's constant, as the name suggests, is a constant. So this will allow us to find the frequency. And then this will be equals to the work function plus the EK max, which is 6.96 times 10 to the minus 20. So there we go. This is the EK max. But you can see that we have a problem that is arising here. We don't have the frequency, but we also don't have the work function. But with the information that we're given, we can be able to calculate the work function for ourselves, right? Because we are given EK max and frequency of light, right, for one of the lights that are emitting electrons. So if we use that information, we can say the energy is equals to the work function plus EK max. We want to use this information so that we can find the work function, right? Which will be equals to the energy minus EK max. So how are we going to find the energy? Planck's constant, 6.63 times 10 to the minus 34, multiplied by the frequency that is given, 5.85 times 10 to the power 14, minus the kinetic energy, 2.65 times 10 to the minus 20 joules. So the work function is going to be equals to, so let me put that in my calculator, 6.63 times 10 to the minus 34 multiplied by 5.85 times 10 to the power 14 minus 2.65 times 10 to the minus 20. This is giving me a work function of 3.6136 times 10 to the minus 19. What is the SI unit of work function? It is joules, right? So this is the work function. We can then substitute it back into this equation. So if we do that, we're going to have Planck's constant 6.63 times 10 to the minus 34 multiplied by the frequency. That's what we're interested in. So multiplied by F is equals to the work function 3.6136 times 10 to the minus 19 plus the EK max, not minus. So the EK max here is 6.96, right? So 6.96 times 10 to the minus 20. So 6.63 times 10 to the minus 34 multiplied by the frequency is going to be equals to 3.6136 times 10 to the minus 19 plus 6.96 times 10 to the minus 20. Right, let me put brackets here so that I can be 100% sure that my calculator is interpreting what I want to say the way I want to say it. 6.96 times 10 to the minus 20, 3.6136 times 10 to the minus 19. Okay, looks good. So here I'm getting 4.3096 times 10 to the minus 19. So let's divide both sides by the coefficient of F, right? So 4.3096 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34. I'm getting a frequency of 6.5 times 10 to the power 14. So there we go. That is the answer to 10.2.3. Let's take a look at 10.2.4. So 10.2.4, the question is saying the intensity of the light is increased while the intensity of the red light is increased while the intensities of the blue and green light remain the same. What effect will this change have on the rate of electrons that are ejected? Choose from increase, decrease, or remain the same. So we have already deduced that the red light is not emitting any electrons. So what does that tell us? Even if we increase the intensity, it's not going to matter. If we increase the intensity of the red light, it's not going to matter. It's not going to affect the number of electrons that are being ejected because red light is not emitting electrons, right? The energy that it carries is less than the work function. So even if we increase the intensity, it does not increase the number of electrons that are being ejected and therefore increase the rate, right? So the answer yes remains the same. 10.2.4 remains the same. So 10.3, some of the atoms of a hot gas made up of a single element are in an excited state. The spectrum formed by the hot gas is observed on a screen in a darkened room. The spectrum consists of specific colored lines on a dark background. Specific colored lines on a dark background. 10.3.1, name the type of spectrum formed. So I'm asking you this question. Is this an emission spectrum or is it an absorption spectrum? Why do you say so? 10.3.2, explain the presence of the colored lines in the spectrum. Alright, so your answer to 10.3.1 is being explained by 10.3.2 essentially. So tell me, why are you saying it is an absorption spectrum? If you're saying it is emission, why are you saying so? There we go.
This question is saying, let's calculate the maximum height above the ground reached by block A. It sounds like a typical vertical projectile motion, but it is way more than that. You're gonna see what I'm talking about when I answer the question. Can I even answer the question? That's the question on its own. Let's do 2.1 so that I can show you what I'm talking about. So 2.1, the question is saying that let's show by means of a calculation that the magnitude of the acceleration of block B was 3.88 meters per second squared while the block was moving vertically downwards. So let's go ahead and read our question statement so that we can see what is going on. So when block B is released, so now we know fully well that this block B is released at some point. It moves vertically downwards and strikes the ground with a velocity of 3.41 meters per second. So if it is released, then we know that VI is equals to 0 meters per second. And we're given VF, the velocity at which it strikes the ground. It is said to be 3.41 meters per second. What else do we have? We have the distance or the displacement of our object B, right? From the time it is released to the time it strikes the ground. So we have delta Y being equals to 1.5 meters. And what are we looking for? We're looking for the acceleration, right? So based on the vertical projectile motion, you can see what we have to use here. VF squared is equals to VI squared plus 2a delta Y. We have VF squared, we have VI, we have delta Y. So we can use this formula for sure, right? It's gonna work because we're looking for the acceleration. So let's take direction towards the ground as positive. If we do that, then our VF is 3.41 squared, which is equals to our VI, which is 0, we square that, plus 2a, and then if we take in direction towards the ground is positive, then our delta Y will be positive 1.5. We're gonna have 11.6281 being equals to 0 squared is just 0, right? And then here we have 2 multiplied by a multiplied by 1.5. That is equals to 3a. So if we divide both sides by 3 in order to find our acceleration is equals to 3.88 meters per second squared, right? And that's exactly what we are asked to prove. So our answer for 2.1, we're quite confident we're doing the right thing. And then now 2.2, let's draw a free body diagram showing all forces acting on block B immediately after it was released. Right, so let's just go ahead and do that. So for block B, we're gonna have the weight pointing downwards, right? And then now we can start thinking about everything else. You know the weight is gonna be there, so you put the weight first, and then after that you have to start thinking about everything else, right? It is connected to a light inextensible rope, so we're supposed to have tension force going up, right? So we have tension and weight. We have two forces acting on the object, and the question also has 2 marks, right? So we're quite confident we were able to identify all the forces. If the question was out of 3 marks and we had only 2 forces, we were most likely going to be doing something wrong, right? You should be aware of that. And then 2.3, this is the one I want you guys to do. State Newton's second law of motion in words, right? We know that the acceleration is directly proportional to the F net, and so on and so on. Let's just do 2.4, right? Before doing 2.5. So 2.4 is quite an interesting one also. It's saying that let's calculate the value of M by applying Newton's second law to each block while they are in motion. People are getting this question wrong so often, such that they're telling you to apply Newton's second law in each block, right? They usually just say calculate the value of M, and you have to figure it out yourself that you have to use Newton's second law on both blocks. But then now they're actually telling you, let's go ahead and apply it on block B and see what's going to happen. So for block B, we have the free body diagram, right? So when I say F net is equals to
ma. And then we're gonna say the force that is pulling the object minus the force that is opposing. The object is going down, right? So it means that we have the weight pulling our object, and then the tension is opposing. So we're gonna say that the weight minus the tension is equals to ma. So what is the weight? The weight is 7.5 multiplied by 9,8 minus tension is equals to the mass, which is 7.5 multiplied by our acceleration, which is 3.88. So what is 7.5 multiplied by 9.8? That is 73.5. And then minus tension is equals to 7.5 multiplied by 3.88. Which is equals to 29.1. So minus tension will be equals to, so now we take in this term here to the right hand side, so that it will be 29.1 minus 73.5, which is equals to minus 44.4, right? So if we divide both sides by minus 1, we're gonna get the tension being equals to 44.4 newtons. Right, we have the tension, but that's not what we're looking for. We're looking for the value of m, right? So now we have to go to that object. So for object A, still F net is equals to ma, right? There's no other way. So let's have a free body diagram for object A so that we can see what is going on. So for object A, the tension is pulling the object upwards, right? And the weight is opposing. So here we must have tension minus the weight, because now it is the tension that is pulling and the weight that is opposing, unlike in object A. Right, so the tension, we know that it is 44.4 minus the weight. The weight should be m multiplied by 9.8 is equals to the mass multiplied by the acceleration, which is 3.88. Right, so we're gonna have 44.4 minus 9.8 m is equals to 3.88 m. It's easy to see that we're gonna have 44.4 and then is equals to, so we take in this term to the right hand side, so that is 3.88 plus 9.8, which is equals to 13.68 m. If we divide both sides by 13.68, we're gonna have 44.4 divided by 13.68, and then the size of our mass is 3.25 kgs. Right, so we have our mass, the value of m, that is 2.4. and now 2.5, let's just do 2.5 real quick. So let me show you something. Let's calculate the maximum height above the ground reached by m. So initially I was thinking, why does this question have 5 marks? It should have 1, because from this point here to the ground it's 1.5, and then while B is moving from that height to the ground, then A will move from the ground to that height, which is 1.5. So the maximum height for A should be 1.5. Why does it have 5 marks? I don't understand. But then I realized that when it reaches this height, which is 1.5, it has a velocity which is not equals to 0, right? So it's still going to go up for some time, because its velocity there is not 0, so it's not stopping. It's still going up until it ultimately gets stopped by gravity. Right, so what is the velocity at this point? That is the question we are interested in. The velocity at that point is equal to the velocity that the object B strikes the ground with. Right, and then what is the value of that velocity? That is 3.41. It is given to us here. So at this point here, at this height, ball A has a velocity of 3.41 meters per second.
I was not so sure about the velocity of A at that point. I actually calculated it. And then I realized that, okay, fine. The velocity at which ball B strikes the ground with is the velocity of ball A at that height, because the acceleration is the same, and then VF is not dependent on the mass. When we're using VF squared is equals to VI squared plus 2A delta Y. So we have the velocity at that point. We want the maximum height above the ground, right? But then another thing we have is VF, right? Which is at the maximum height we're interested in. That VF is equals to 0. Because at that point, your object will no longer be going up. So if we find this height here, and then we add it to the 1.5 we have, then we have the height of object A above the ground. So let's go ahead and do that. We say that VI will be close to 3.41 meters per second, and VF will be equals to 0. Right. Our acceleration, how much will our acceleration be? If we take upwards is positive, our acceleration will be minus 9.8 meters per second. That is because when ball B strikes the ground, object A will now be in free fall. The tension force on that rope is going to be equals to 0. Right. So we have VI, we have VF, we have the acceleration, we want delta Y. Right. So it's easy to see now that we can say that VF squared is equals to VI squared plus 2A delta Y. So VF is 0, maximum height. And then VI, if we take it up as positive, that is 3.41 squared plus 2 acceleration minus 9.8 because we're taking upward as positive, and then multiply by delta Y. So we have to take this term to the left hand side. So 3.41 squared is equals to, so 3.41 squared is equals to 11.6281, right? If we take it to the other side, we're going to have minus 11.6281 being equals to 2 multiplied by minus 9.8, that is minus 19.6 delta Y. If we divide both sides by minus 19.6, we're going to get 0.59. So 0.59 meters is equals to delta Y. So here we have 1.5, and then here we have 0.59. So our height above ground, is 1.5 plus 0.59. Right, that will be our height. That is equals to 2.09 meters. Free fall is the motion of an object where the only force acting is gravity. Right, so that is 3.1. Let's go ahead and do 3.2.1. So the question is saying that let's calculate the time taken for ball A to strike the ground. So let's look at ball A here. It is released from a height of 15.2 meters above the ground. When it is released, we know fully well that VI is equals to 0 meters per second. Right, and we have delta Y. So let's take up as positive. If we take up as positive, then delta Y should be equals to minus 15.2 meters when our object strikes the ground. Another information we have is the acceleration, as we always do, minus 9.8 meters per second squared. And what are we looking for? We're looking for the time it takes the ball to strike the ground. Right, so based on the variables we have, VI, acceleration, delta Y, and the time that we're looking for, it's easy to see now that we're going to say delta Y is equals to VI delta T plus a half A delta T squared. Right, initially I didn't want to use this formula because what about delta T squared and delta T? I'm going to have to solve this by factorizing, right? But then I realized that VI is equals to 0. So this term here is going to give me 0. I'm not going to have so many issues, right? So if we go ahead and substitute
we're going to get minus 15.82 is equals to VI, which is 0, right? Multiplied by the time. So that term falls away. Plus a half. The acceleration is minus 9.8 and the time is what we're looking for. So we're going to have minus 15.82 being equals to, this term falls away. We just have minus 4.9 delta t squared. So it's easy to see now that delta t will be equals to the square root of 15.2 divided by 4.9. Right, so now it's just a matter of putting that in your calculator, and what am I getting? I'm getting 1.76126 seconds. So that is the time it takes ball A to strike the ground. Right, it makes sense because it's gonna take about 1 second to cover 9.8 meters, right? And then the rest of the height can take less than a second, right? Let's do 3.2.2. So in 3.2.2, quite demanding one, right? 5 marks. We're looking for the magnitude of the velocity with which ball B was projected from the ground. So let's look at the information we have. We don't have VI. If you take the motion from the time it was projected to the maximum height, you can say you have a VF, which is equals to 0, right? But we don't know the maximum height also, because at this point, what we have is the initial velocity, which is unknown, and the acceleration, which is minus 9.8 meters per second squared. And then another thing we can calculate is the time for the motion of ball B, right? Because we are told that ball A and ball B, they strike the ground at the same time. But then when ball A was at this point, that is only when ball B was projected upwards. So we can say that the total time of ball A minus the time taken by ball A to go from maximum height to 3.2 meters below the maximum height will give us the time for ball B. Right, so let's go ahead and do that. So for ball B, not ball B but ball A, we can say that delta y is equals to VI delta t plus a half a delta t squared. Right, so now our delta y, we can say that is minus 3.2 meters because we're looking for the time taken for only this journey. That is the time we're interested in, right? We're going to subtract it from the total time, and that will be the time for ball B. Right, so if we substitute minus 3.2, then our VI 0 delta t plus a half minus 9.8 delta t squared. Right, so we're gonna have minus 3.2 being equals to minus 4.9 delta t squared. If we make delta t the subject of the formula, we're going to get 3.2 divided by 4.9. We know that minus and minus, they're going to cancel out, right? And our time will be 0.8. So we have 0.8081. So right, the time for this part of the motion from this point to this point is 0.8081. Right, so to find the time for the entire motion of ball B, we can say that so the time for ball B, we're going to say that it is equals to the total time for ball A, which is 1.76126 minus 0.8081. Right, so let me just put that in my calculator real quick so that I can see what I get. I'm getting 0.95316 seconds. Right, so that is the total time for ball B. Let's revisit the information we have for ball B and see if we can manage to find that VI. We have the time for the total motion. Right, we can put that in mind. And then VI is still our unknown. We have the acceleration, which is minus 9.8 meters per second squared. But if we take the motion from the ground to the maximum height, we can say that we have VF, right? We have a VF which is equals to 0. And then to find the change in time from ground to 0, we're going to say total time divided by 2, because the time taken from ground to the maximum height shall be the same time from maximum height to the ground. It is actually wrong for me to put this dot here. We don't know how high ball B is above the ground at maximum height, right? So if we divide that total time by 2, so we have 0.95316 divided by 2. Let me just put that in my calculator real quick. I'm getting 0.4765. So now I have delta T. I have delta T. I have VI is what I'm looking for. I have acceleration. I have VF. So it's easy to see now that I can say VF is equals to VI plus A delta T. VF is 0. VI is what we're interested in, plus our acceleration, which is minus 9.8 multiplied by the time, which is 0.47658. So minus VI is going to be equals to, so I have minus 9.8 multiplied by 0.47658. Right, so I get minus VI being equals to minus 4.6705. And then VI is equals to 4.6705 meters per second. Right, that is the initial velocity for which ball B is projected upwards. Now the last question, 3.3. So on the same system of axis, let's draw the position time graphs to show the motions of both ball A and B from the instant ball A is dropped until the time it reaches the ground. Let's take the ground as the 0 position, right? Because usually they will say let's take the ground as our reference point, and that will lead to a lot of ambiguity. What do they mean? You know, reference point. Are we taking it as 0? Are we? What is happening? But then when they say we must take it as the 0 position, that is clear. There is no ambiguity. You know exactly what is expected of you. Right. So the x-axis, there we go. And then obviously on the x-axis, we're going to have the time in seconds. And on the y-axis, we're going to have delta y in meters. Maximum height 15.2. So let's start with ball A, right? So ball A is starting from 15.2 and then it goes down until it strikes the ground, right? It takes 1.76 seconds for that motion. So we have 1.76 seconds, right? And then now we have to go to ball B. So ball B is only projected 0.8 seconds later. So we have 0.8 here, right? Yeah, that is the time at which is projected. And then it goes up to its maximum height, which is less than that of ball A. That's, yeah, it's easy to see. But then they strike the ground at the same time. So I think we should have something like this. I wonder what you guys did. Can you please let me know in the comments if we have the same position time graph? The total linear momentum in an isolated system is conserved. That is the principle of conservation of linear momentum in what? 4.1, right? So let's go ahead and do 4.2 and see what is happening here. So the first question, 4.2.1, calculate the magnitude of the velocity of the trolleys immediately after the collision. So based on the principle of conservation of linear momentum, we know that the sum of the momentum before should be equal to the sum of the momentum after, right, if that system is isolated. So for our case here, we have trolley A, which is moving to the right, and we have trolley B, which is stationary. And after they collide, they move together as one unit, right? So if we set up our equation here, we'll get m1 multiplied by the velocity plus m2 multiplied by its velocity being equals to m1 plus m2 multiplied by Vf. If you're confused and you can't see what is happening, that is because the momentum is equal to the mass multiplied by the velocity. So this right here is the momentum for trolley A, the momentum of trolley B, and the momentum as they move together as one unit. Right. So if we go ahead and substitute, we're going to get 7.2 multiplied by 0.4. We take in direction to the right is positive, right? Plus the mass of trolley B, which is 5.3 multiplied by 0, right? It was stationary, and then this will be equals to 7.2 plus 5.3 multiplied by the final velocity, right? So if I put 7.2 multiplied by 0.4 on my calculator, I'm getting 2.88, and 5.3 multiplied by 0, that will just be 0, right? And that will all be equals to, so now I have 7.2 plus 5.3, which is 12.5. So I have 12.5 multiplied by Vf, right? It's easy to see now that I just need to divide both sides by 12.5. So if I divide both sides by 12.5, let me see what I get. I'm getting 0.2304 meters per second being equals to Vf. So there we go. I have the final velocity of the trolleys immediately after the collision. Right. And 4.2.2, let's calculate the magnitude of the average net force exerted by trolley A on trolley B during the collision if the collision time is 0.02 seconds. So there's two ways of doing this one. You can say that F net is equals to the change in momentum divided by the change in time, or you can say that F net is equals to the mass multiplied by acceleration. They're all going to work, but let's just use the first one, right? If we use this first one, we know that the change is equals to the mass multiplied by Vf minus Vi, right? We're on the same page now. We can go ahead and substitute. So F net will be equals to the mass. So let's use trolley B, right? You can use trolley A. You're going to get the same thing. If we use trolley B, we're going to get the mass being equals to, what is the mass again? 5.3. And then Vf is 0.2304. And then it's coming from rest. So its Vi must be 0. And we're dividing all that by 0.02. That is the amount of time the collision took, right? And then putting that in my calculator real quick, I'm getting 61.056 newtons. It is a force in which the work done in moving an object between 2 points is dependent on the path taken. So that is 5.1, a non-conservative force.
Right, and then 5.2. Let's use energy principles to calculate the speed of the crate when it reaches point C. Right, so let's see what's going on here. We have an electric motor that pulls a 20 kg crate from rest at point A, right, up the incline by means of a light inextensible rope. And then we can see that the incline makes an angle of 18 degrees with the horizontal B, C, and D are points in the incline plane. And then we can see clearly that the distance between A and B is 15.6 meters. Right, we are told that the motor exerts a constant force of 96.8 newtons parallel to the incline. And then there's a constant frictional force of 13.5 newtons. Right, so we're supposed to use energy principle. If the question says use energy principles, you can use work net is equals to the change in EK. Right, you can also use the work done by non-conservative forces equals to the change in EK plus the change in EP. Right, you can do that. So let's just go ahead and solve it using the first formula, right? I've actually solved it using both. So if you try this formula, it should also work. Right, so if we use that formula, we're going to get F net multiplied by delta x multiplied by cos of theta when it goes to a half mvf squared minus a half mvi squared. Right, so now we can find F net so that we can find VF ultimately, right? So how can we find F net? Let's draw a free body diagram of the 20 kg block as it moves up the incline, right? So we have FG parallel, which is pushing the object down the incline. We have the frictional force, right? And then the force applied by the electric motor. We have the normal force, obviously, and we have the weight perpendicular, right? The normal force and the weight perpendicular are not going to do any work on the object. So we are interested on the force applied by the electric motor, frictional force, and FG parallel. So if we find the net force there, we're going to get the net force being equals to the force applied, which is 96.8, right? So we're going to have 96.8 minus the forces that are opposing, frictional force, that is 13.5, minus FG parallel. So FG parallel is mg sine of theta, right? So that is FG parallel. And then if we substitute that in our equation, the mass is 20 kgs, the acceleration is 9.8, and then multiply by sine of 18 degrees. So if we put that in our calculator, then F net should be whatever we get there, right? So let me just do that real quick so that we can see what we get. And then I think our F net should be equals to 22.7327 newtons. Right, so now we have F net. We can put it in our equation. So in place of F net, we now put in 22.7327, right? And then in place of delta x, we have 15.6. And then the object is moving up the incline, and the F net is also pointing up the incline. So the angle in between those two should be 0, right? So we're gonna have cos of 0 being equals to a half. The mass is 20 kgs multiplied by VF squared minus a half 20 velocity initial. Our object is coming from rest, right? So multiply by 0 squared. Right, so let me just solve the left hand side. And 22.7327 multiplied by 15.6 multiplied by 1. What am I getting? I'm getting 354.6301 is equals to, so I have multiplied by 20, that will be 10, right? And then we have VF squared, right? So if we apply a bit of algebra here and make VF the subject of the formula,
we're going to get the square root of 354.6301 divided by 10. Right, so now what is left, I just need to put that in my calculator, and our VF is 5.96 meters per second. Right, that is 5.2. Right, let's move to 5.3. So 5.3 is saying that let's calculate the minimum average power dissipated by the electric motor to pull the crate from point A to point C. So if we want to find the power, it's either we can use the work divided by the time, or we can use the force multiplied by the average velocity. Right, we don't have the time as it is, right? Maybe we can try calculate the work, but we don't have the time. But then if you look at the other formula, we have the force, right, that is exerted by our electric motor, right? And then we have VI, which is equals to 0, and we have VF, which is equals to 5.96. So we can add those two and divide by 2 to find velocity average. Right, so what am I saying? I'm saying that the power will be equals to, so the force that is exerted by our motor, that is 96.8 multiplied by velocity average. So I'm saying to find velocity average, I'm going to say VF plus VI divided by 2. So what is VF? VF is 5.96 and then plus 0 divided by 2. Right, so that is 96.8 multiplied by 5.96 plus 0 divided by 2. And then the answer I'm getting here is 288.46 for, what is the SI unit of power again? I think it's watt. Right, so we're gonna have that there. I'm so much interested in how other people solved this problem, so please just let me know in the comments what you did for 5.3. Then 5.4 is saying that when the crate reaches point C, the rope breaks. So our rope is breaking at this point, at C. And then what happens next? The crate continues moving up the inclined plane, as you would expect. It comes to a stop at point D, and then slides down the plane past point B. Right. Draw a labeled free body diagram for the crate as it slides down the plane past point B. Right, so it's sliding down, and we need to draw a free body diagram for that motion. So when it is sliding down, FG parallel is still down the incline. FG parallel is down the incline. And then the frictional force is now up the incline. Right, and then we have our normal force there, and we have our weight perpendicular, or FG perpendicular, right? So I'm expecting 1, 2, 3. I'm expecting this question to be out of 3 marks because we have identified 3 forces, right? And indeed it is, right? So now I'm convinced that I have the correct free body diagram because my number of forces correlates with the marks for the question. Right, and then 5.5, let's look at what 5.5 says. So in 5.5, let's do a velocity time graph for the entire motion of the crate, starting from point A until it passes point B, and again on its motion down the inclined plane. Right, well, so we studied that V is equals to 0. And then at point B, we have, not at point B, but at point C, we have a velocity of 5.95 meters. So let's write 5.95 here. And then, right, let's have our VT graph. Yeah, so there we go.
to 5.95. And then what happens after we reach a velocity of 5.95? So the rope breaks. And then when the rope breaks, we no longer have that force that is pulling our object. But then our object will go up for some time before it reaches a VF of 0, right? As it is going up, its velocity is decreasing until it reaches 0, right? So let's see if we can indicate that in our graph. So it decreases until it reaches V is equals to 0, right? That is, now we add point D. We have reached V is equals to 0, because it's going to be increasing bit by bit until we reach V is equals to 0. And then after that point, now it is going down, right? Our object is going down and its velocity is starting to increase, right? So I'm thinking that we're going to have, something like this. Its velocity is starting to increase now. Alright, so I'm thinking we're gonna have something like that until we reach point A again. We don't know the velocity of point A. I don't think we need to indicate the value anyway. Right, I'm quite interested on how yours look like. Can you please just let me know in the comments if we have anything similar? One of the most interesting equations under Doppler effect I've came across, that is 6.1.2, right? So let's look at 6.1.1. You just need to state the definition of Doppler effect in once, right? I'm sure you can do that. Let's look at 6.1.2, the interesting equation. So the question is saying a car moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits sound waves with a frequency of 24,000 Hz. Alright. And then these sound waves are reflected off the car, and the reflected sound waves are then detected by the device as shown in the diagram below. We can see what is happening there. And then if the speed of sound in air is 340 meters per second, let's calculate the frequency of the reflected sound waves detected by the device. So let's do a bit of conceptualization here. So let's put X as our vehicle and put our device somewhere here. So the first thing that is going to happen, our device is emitting a sound wave, right? So let's just denote that. So we have some frequency of source, and then when it strikes the car, it's no longer Fs. We now have FL, right? It's going to is going to detect a totally different frequency. And then from that frequency it detects, it's now going to reflect it and send it back to the device. So now we have this frequency being reflected back to the device. And then now we have FL2. So you can use this Fs here to find FL, and then when you find that FL, it now becomes your Fs that the device is going to detect. Am I making any sense? Let me show you what's going on. So for the first part, we have the frequency of the listener being equals to V plus or minus the velocity of the listener divided by V plus or minus the velocity of the source multiplied by the frequency emitted by the sound source, right? So the frequency observed by the listener, or the frequency that strikes our vehicle, it will be equals to 340, and then our listener or our vehicle is moving towards the device, right? So we're supposed to have plus the velocity of our listener, which is 22 meters per second, and then we can divide everything by 340 plus or minus the velocity of the device, which is 0, right? It is stationary, and then we can multiply that by the frequency emitted by our device, which is 24,000, Right, so let me just compute that real quick. So I have 340 plus 22 divided by 340, essentially multiplied by 24,000, and I'm getting 25,552.94 hertz. So this is the frequency that strikes our car. This is the frequency that strikes our car. And now this frequency is reflected back to the device as Fs, right? This frequency now becomes our Fs, is reflected back to our device. So what am I saying? We're saying that now we're going to have FL being equals to V plus or minus VL divided by V plus or minus Vs multiplied by the frequency emitted by the source. So what is FL? FL is what we're looking for, the frequency that is detected by the device, right, after it has been reflected. Right, that will be equals to 340, and then now our listener is the device. We know that it is stationary, so we're gonna have plus or minus 0 divided by 340, and then now our sound source is moving towards, it is the car, right? So we're gonna have 340 minus 22 multiplied by the frequency of the source, which is what we calculated here, 25,552.94 hertz. That is the frequency that is being reflected by the car. This is the trick of the question. As soon as you can wrap your head around the concept, then you're essentially done. So multiplied by 25,552.94 hertz. I'm getting 27,320.75 hertz. Right, so that is the frequency of the reflected sound waves detected by the device. Right, and the last question, 6.2, the spectral lines observed for a distant star show that the star is moving away from Earth. Explain by referring to frequency how one can deduce that the star is moving away from the Earth. So here, I'm much interested in how you guys answered this question. So can you please just let me know in the comment section. What happens when you have a positive and a negative charge? Right, we have two unlike charges. They're definitely going to attract. Right, so the answer to 7.2 will be something like the following. We're supposed to draw the net electric field pattern due to the 2-point charges. And now 7.3, we need to calculate the magnitude of the electrostatic force that Y exerts on X. Right, so we have Y and X right there. So F is equals to K Q1 Q2 divided by R squared. So what is the value of K? K is a constant, right? So we have 9 times 10 to the power of 9. And then Q1, we can take X as Q1. But when you substitute, you don't put the negative sign, you just put the magnitude, which is 7.2 times 10 to the minus 9 multiplied by Q2, which is also 7.2 times 10 to the minus 9. So we can just say 7.2 times 10 to the minus 9 squared, right? And then divided by the distance between the two charges. So we have 0.03, and then we can square that. 5.18 times 10 to the power minus 4 newtons. Right, so yeah, there we go. Let's move to the next question and see what we can do. So 7.4, let's draw a labeled vector diagram to show the directions of the electric fields at the point where X is positioned. Right, so in our question statement, we are told that a third point charge Z of unknown positive charge. So we have a positive right here, and then it is placed
0.01 meters to the left of point charge X on the line joining point charges X and Y, as we can clearly see. Right, so we need to draw a labeled vector diagram to show the directions of the electric field at the point where X is positioned, right? So let's say X is positioned somewhere here. We're gonna have an electric field as a consequence of our charge Z, right? So let's call it E1 pointing to the right. And then the electric field due to Y is gonna be to the left, right? So we have something like that for 7.4. 7.5, it says that the magnitude of the resultant electric field at the point where X is positioned is 4.91 times 10 to the 5 newtons per coulomb. Let's calculate the magnitude of charge Z. So the resultant electric field will be equals to E1 minus E2, right? As we can see that they are pointing in opposite directions. So E net is 4.91 times 10 to the power 5. And then E1, we don't have E1, right? That is what we're going to use to find the charge of Z. So we have E1 minus E2. So we're going to have K. Let's not forget that E is equals to K, Q divided by R squared, right? So we're going to have 9 times 10 to the power 9 multiplied by 7.2 times 10 to the minus 9 divided by the distance, right? From here to here is 0.03 squared. So we have is 0.03, right? So we're gonna have 0.03 squared, right? So we're gonna have 4.91 times 10 to the power 5 plus 9 times 10 to the power 9 multiplied by 7.2 times 10 to the minus 9, everything divided by 0.03 squared, and this will be equals to E1, right? So instead of writing E1, let's go ahead and substitute, right? So we're gonna have 4.91 times 10 to the power 5 plus 9 times 10 to the power 9 multiplied by 7.2 times 10 to the minus 9, everything divided by 0.03 squared, and then this will be equals to 9 times 10 to the power 9 multiplied by the charge of Z divided by the distance. So the distance from Z to X is 0.01 meters, right? So we're gonna have 0.01 meters, and we can square that. On the left hand side I have 5.63 times 10 to the power 5. This is equals to 9 times 10 to the power 9 multiplied by the charge of Z divided by 0.01 squared, right? So the charge on Z will be equals to 5.63 times 10 to the power 5, everything divided by 9 times 10 to the power 9 divided by 0.01 squared, right? And then ultimately we're going to get 6.26 times 10 to the.
Have you ever calculated the EMF using simultaneous equations? That's what we're going to do for this question, right? Look at 8.3. We have to calculate the EMF, but we don't have the internal resistance, right? But before we do that, let's do 8.2. So 8.2.1, we're looking for the reading on the voltmeter. So our voltmeter is connected across this 3 ohm resistor, right, as you can clearly see. So what you have to realize here is that the current splits at this point. So we have two parallel paths. These two resistors, the 2 and the 5, are parallel to the 3 ohm resistor. And then what do we know about resistors in parallel? We know that the voltage is the same, but the current is different, right? So to find the reading on the voltmeter, we can actually use this current we are given in A1 and multiply it by the resistance of these two resistors. We can find the VP by doing that, right? We know that if we do that, it's going to be the same value that is in the voltmeter, because the 3 ohm resistor is in parallel with the 2 and the 5 ohm resistor, right? So what are we saying? We're saying that we can have VP is equals to I multiplied by R. So VP will be equals to 1.5 multiplied by 7, right? Pretty much straightforward, no complications whatsoever. And then if you put that in a calculator, you should get 10.5. So the answer here for 8.2.1, we have 10.5 volts. That will be the reading on the voltmeter. Right, let's move forward and do 8.2.2. What are we looking for? We're looking for the reading on ammeter A2. So right, if we go to our sketch, you're gonna realize that ammeter A2 is here, right? So basically what we're looking for is the total current, because ammeter A2 experiences total current. So we're looking for IT. What do we have up to so far? We have VP, which is equals to 10.5 volts. What we're looking for is IT, right? But then we have a formula that says that VP is equals to IT multiplied by RP. So since we have VP, we can find RP, and then by doing that, we're going to ultimately find IT. So let's go ahead and find the resistance in parallel. We can say that 1 divided by RP is equals to 1 divided by R1 plus 1 divided by R2. So RP is equals to 1 divided by the total resistance on this path, which is 3 ohms, right? Plus 1 divided by the total resistance on this path, which is 2 plus 5. So we're supposed to have 2 plus 5 here to the power minus 1. And then if you put that in your calculator, you're going to get 2.1 ohms, right? So now we have RP. We can then say that VP is equals to IT multiplied by RP. So VP is 10.5, and then IT is what we're looking for. But what is RP? RP is 2.1. It's easy to see now that IT will be equals to 10.5 divided by 2.1, which is equals to 5 amperes. Right, so the value of IT is 5 amperes. Right, let's move to the following question. We're looking for the power dissipated in the 3 ohm resistor. So to determine power, there's quite a few formulas we can use. We can say that P is equals to V squared divided by R. It is equals to V multiplied by R by I, or it is equals to I squared multiplied by R. So let's see if we can use the first formula. We have the voltage, it is 10.5 volts, and then we have the resistance, which is 3. So we can use this formula. We don't have to try use any other thing. So we're gonna have P being equals to, what is the voltage? 10.5, and then we square that divided by the resistance, which is 3 ohms. Right, so now it's just a matter of putting that in your calculator. And then when I do that, what I'm getting 36.75. So I have 36.75 watts.
Right, that is 8.2.3. The question we're really interested in is 8.3. So in 8.3, we're told that switch S1 is now open while switch S2 remains closed. The reading on the ammeter E2 is now 3.64 amperes. So when S1 is open, now we have an IT which is equals to 3.64 ampere. We have a total current which is equals to 3.64. So let's go to our sketch and see what happens when switch S1 is open. So when switch S1 is open, the current is no longer passing this point, right? So basically, all the current is gonna flow like this. All the current is gonna pass through the 3 ohm resistor, right? So now our total resistance is 3 ohm. So to calculate the EMF, we can say that EMF is equals to I multiplied by R plus the internal resistance. So our EMF will be equals to the current, which is 3.64 multiplied by the external resistance, which is 3 ohms, right, plus the internal resistance. So EMF is equals to, so we have 3.64 multiplied by 3, which will give us 10.92 plus 3.64 R. As you can see, we're looking for the EMF, but we don't have the internal resistance. So we're stuck. We have one equation and two variables. So we can call this equation 1 and go ahead and try find another equation so that we can solve simultaneously. So this is when IT is equals to 3.64 ampere. But what happens when IT is equals to 5 amperes, like we had when both switch S1 and S2 are closed, right? So now we can use this information. We know that the corresponding current is 5 ampere, right? So we're going to say that EMF is equals to I multiplied by R plus internal resistance again. So the EMF is equals to the current, which is 5 amperes when both switches are closed, multiplied by the external resistance, which is RP, right? That was 2.1, and then plus internal resistance. So the EMF is equals to 10.5 plus 5R, equation 2. So we can equate these two equations and determine the internal resistance and ultimately the EMF. So equation 2 is equals to equation 1. So what are we saying? We're saying that 10.5 plus 5R should be equals to 10.92 plus 3.64R. Right, so let's take 10.5 to the right hand side and take 3.64R to the left hand side. So if we take 3.64R to the left hand side, we're gonna get 1.36R, and then when we take 10.5 to the right hand side, we're gonna get 0.42. So R is equals to 0.42 divided by 1.36, and that is equals to 0.31. Actually not 0.31 but 0.3088 ohms. Right, so we have the internal resistance. We can substitute it into either equation 1 or 2 to find our EMF. So if we substitute it in equation 2, we're gonna get 10.5 plus 5 multiplied by 0.3088. Right, so we have 10.5 plus 5 multiplied by 0.3088. I'm getting 12.044. So 12.044 volts seems to be our EMF. Right, and now this trick equation 8.4 is actually out of 4 marks. So what is it saying? We have switch S2 is now opened while switch S1 is closed. So let's go ahead and make that adjustment. S2 is now opened. So S2 is now opened. The 3 ohm resistor is no longer taking part in our circuit. We can essentially just erase this. Yeah, we no longer have that when switch S2 is now open. How does the voltmeter reading change? Actually, let's not erase it because now we cannot see our voltmeter. So let's just erase S2 alone. Let's just erase S2 alone. Right. Yeah. There we go. How does the voltmeter reading change? Choose from increase, decrease, or remain the same. So the voltmeter is reading V external, right? So what will happen to V external when that switch is open? The first thing to realize is that R external increases. That's what's going to happen when that switch is open. R external is going to increase. But if R external increases, and we know that I is equal to V divided by R, then current decreases. If current decreases, and let me show you something, EMF is equals to I multiplied by R plus I multiplied by the internal resistance. If the current decreases and then our internal resistance stays the same, then V internal is going to decrease, right? V internal decreases. But we need the EMF to stay the same. So to combat a decrease in the internal potential difference, V external increases. So the answer that we're looking for here in 8.4 is actually increases, right? The reading on the voltmeter will increase. 1.1, which of the following best illustrates balanced forces? So let's break that down before we even attempt to answer the question. When you're thinking about balanced forces, you're thinking F net is equals to MA and F net is equals to 0. Your object is stationary or it is moving at a constant velocity. That's when we can say that forces acting on an object, they are balanced. Let's look at option A. A person lifting a heavy object from the ground. Obviously, if you're lifting the object from the ground, the forces are not balanced, right? And then B, a big rock free falling to the ground. If it is free falling, there's only gravity acting on the object. Acceleration is not equals to 0. So we cannot say that the forces are balanced. And then C, a light stationary object. The object is stationary. So obviously our acceleration is equals to 0 meters per second squared. That is exactly what we're looking for. So the answer to 1.1, we can go with C. Let's look at 1.2. An 8 kg box is placed on a rough surface as shown below. If a force of 16.5 Newton is applied to the box and it accelerates at 1.5 meters per second squared to the right, the frictional force between the 8 kg box and the surface is, so again, back to the basics, F net is equals to MA. Let's sketch a free body diagram for the object real quick. So we just have the force that is applied, which is equals to 16.5 newtons, and we have some frictional force, which is what we're looking for. So if we substitute that into F net, we're going to say force applied minus frictional force is equals to MA. The force that is pulling the object minus all the forces that are opposing the motion. So that is 16.5 minus frictional force, which is equals to the mass. The mass is 8 kgs and the acceleration is 1.5. So 16.5 minus frictional force is equals to 8 multiplied by 1.5. That's supposed to give you 12. So you can see now that the frictional force will be equals to 4.5 newtons. That is because 16.5 minus something to give you 12. So that something must be 4.5 newtons, right? So that seems like our answer to 1.2 is actually B. Let's move to 1.3. 1.3, a ball is dropped from a certain height above the ground and bounces a few times as it hits the ground. The velocity time graph below describes the motion of the ball from the time it is dropped. Ignore all the effects of air friction. In relation to the velocity time graph for the bouncing ball shown above, which statement below is correct? And then A is saying down is taken as positive direction. So let's look at that. Our ball is being dropped from a certain height and it starts going down. So if down was taken as positive, then our VT graph should immediately go up, but then it is immediately going down. So we're taking up as positive and down as negative, right? So option A that says down is taken as positive, we know that it is already not correct. Let's look at B. B says down is taken as positive. Again, we know that B cannot be correct because we can easily see that down is not taken as positive. Let's look at C. Down is taken as negative. Right. Now there's something to think about. Down is taken as negative and the ball is at its highest point of its bounce at C. So let's go and look at C. C is right here. C is right here. And we know fully well that at the highest point, V equals to 0 meters per second. So C cannot be our highest point because velocity is not equals to 0 at that point. Now, by elimination, our only answer remaining is D. Let's look at it and see why it makes sense. Down is taken as negative, true, and the ball is at its highest position of its bounce at D. Yes, D can be our highest point because velocity at that instance, it is equals to 0 meters per second. Right, let's move to 1.4. So we have 1.4. Two identical solid spheres, each with a mass m and traveling at a speed v, move towards each other in an isolated system. The spheres have a head-on elastic collision. Which statement is correct for the collision as described above? So if collision is elastic, then the momentum EP before shall be equals to EP after, right? And then another thing that is true about an elastic collision, EK before should be equals to EK after, right? So the momentum before, because we have m multiplied by v plus m multiplied by minus v, because the other sphere, the other solid sphere has the same mass but in the opposite direction. The momentum before is equals to 0, right? So the momentum after should also be equals to 0. Let's look at the kinetic energy. The kinetic energy before is a half m v squared plus a half m minus v squared, which is just going to give us, this will give us a half mv squared plus a half mv squared. So this is just mv squared. This is the kinetic energy before and the kinetic energy after. This is the momentum before and the momentum after. Let's look at our options. Option A is saying the spheres stick together on impact. We're not really sure. And then B says, let me not say A here because it seems like I'm saying A is the answer. And B says the total kinetic energy after impact is mv squared. Yes, that's what we have. The total kinetic energy before and after is mv squared. So 1.4, we don't even have to go through the other options. Our answer is B. We have proved that beyond reasonable doubt. 1.5, the mechanical energy of a moving object will remain constant if its free body diagram looks like this. If this is the free body diagram of the object, then the mechanical energy will remain constant. It will be conserved, so to say. So A, there are frictional forces present. If there are frictional forces, your free body diagram will not look like this. And then there is only gravitational force acting on it. We don't have to go any further. The answer is B. Mechanical energy is conserved when your free body diagram looks like this. Right. 1.6. A train is moving at a constant velocity of 10 meters per second while sounding its whistle, which has a frequency of 500 Hz. Take the speed of sound in air as 340 meters per second. What frequency will be heard by a man sitting in the train? So when the man is sitting on the train, the man and the train have the same velocity, right? So let me just do the math real quick. So we know that FL is equals to V plus or minus VL divided by V plus or minus VS multiplied by FS. So V is the same for the man and the train. And then VL and VS, they are the same for the man and the train. So basically we have FL being equals to FS. So the man is going to experience the same frequency that the train is emitting because he and the train are moving at the same velocity. So 1.6, we have the answer being A. He will experience a frequency of 500 Hz, the same frequency that is being emitted by our train. 1.7, the diagram below shows a point P at a distance r from a charged sphere Q. Right, the electric field strength at point P is, let's look at A, directly proportional to R. No. It's supposed to be inversely proportional to R squared, right? Because E is equals to Q1 divided by R squared. So it's supposed to be inversely proportional to R squared, not directly proportional to R. So A is definitely not correct. Let's look at B, directly proportional to the square. So if it says directly proportional to the distance between the two, then it is incorrect. It's supposed to be inversely. And then C, inversely proportional to the square of R and to the right. And then D, inversely proportional to the square of R and to the left. Right, so now we just need to look at whether it is to the right or to the left. It is indeed inversely proportional to the square of R, as we can see from our formula. So now we have to be asking ourselves, Q is negatively charged. Where do the field lines point on a negative charged sphere? They point towards itself. The field line will point towards the charge itself. So you can see here that at P, the field lines will be pointing to the left. They will be pointing towards Q, right? So the answer here to 1.7 is supposed to be the field lines at P will be pointing to the left. They will be pointing towards Q, as you can see from the field lines that surrounds Q as a negatively charged sphere. So inversely proportional to the square of R and to the left. That is option D. 1.8. 1.8 is saying which of the following statements about the AC generator is true. The minimum potential difference produced is not 0 volts. It is 0 volts. So that cannot be our answer. B, the EMF produced decreases as the number of windings increases. That is not true. That is not true. We know from grade 11 that if you want to increase the EMF induced, you can increase the number of turns, you can increase the number of windings. So B cannot be correct. The maximum value of the AC can be increased by increasing the period of rotation. Well, I was initially conflicted between C and D. And then I realized that increasing the period of rotation is decreasing the time it takes for one cycle to be completed, because period is the time it takes to complete one cycle. So if you increase the period, it means that you are now rotating very slowly, and that cannot increase the EMF. So by elimination, it seems like our answer is D. It also makes sense. The maximum value of the AC produced can be increased by increasing the speed of rotation of the coil. So 1.8 is our correct answer. Let's look at 1.9. 1.9 says that a battery with internal resistance is connected to a fixed resistor R. A voltmeter is connected across the battery as in diagram A. The battery is replaced by one with the same EMF but with a larger internal resistance as shown in the diagram. In diagram B, how will the voltmeter reading and current through the fixed resistor change compared to diagram A when switch S is closed? So EMF is equals to V external plus the current multiplied by the internal resistance. The EMF is staying the same. Our batteries still have the same EMF,
but then now it has more internal resistance. So let's look at what is going to happen. If you increase the internal resistance, the total resistance of the circuit is going to increase, and then the current is going to decrease. If the current is going to decrease and the external resistance of the circuit is still the same, then V external will also decrease, because R is remaining the same, the external resistance of the circuit. So let's look at what we have. With regards to the voltmeter reading, is saying that the voltmeter reading is going to decrease. Yes, the voltmeter reading is going to decrease, even though the EMF is the same. They're saying that switch S is closed. When switch S is closed, current is flowing in our circuit. So the voltmeter connected across the ends of our battery will be reading V external and no longer EMF. You need to realize that. So we're looking for answers with a voltmeter reading that is saying decreases and decreases. So now our answer can only be A or B. Let's look at the current through resistor. We have already deduced that the current will decrease, the current of the entire circuit, because it's all the same everywhere. In this instance, we don't have any resistors in parallel. So the current is also going to decrease. So that is option A. So our answer to 1.9 is A. And 1.10, this question actually doesn't make sense. The diagram below shows the kinetic energy versus frequency of a photocell that has a sodium metal cathode. The work function of sodium is 4.41 times 10 to the minus 19 joules. Let's just stay there. And then the question is saying the threshold frequency of sodium is, so we are given the work function, which is equal to Planck constant multiplied by threshold frequency. We have work function with Planck's constant. So the threshold frequency should just be work function divided by threshold, not threshold, but Planck's constant, right? And then I think, let me just look at that answer again. When you put that in your calculator, you're going to get 6.61 times 10 to the power 14 hertz. That is your answer when you use this information. And then we are given a graph. In our graph, the frequency where you start seeing some kinetic energy is given as the threshold frequency is equal to 3 multiplied by 10 to the power 14 hertz, right? So on the same question, we have two possible answers. 3 times 10 to the power 14 hertz and 6.61 times 10 to the power 14. Well, if you look at our option, we have 3 times 10 to the power 14 hertz as option B, right? Option C is in joules, so it cannot be correct. And option D is also in joules, so it cannot be correct. And then option A is also not correct, because our answer when we use the work function is 6.61 times 10 to the power 14 and not 4.41. Unless I'm missing something. I think we actually cannot answer this question. There is two possible answers. Only one is in the options provided. So if push comes to shove, you would have to choose the option that is there on your, or on one of your options. Please just let me know what you think about this question. Yeah, because I think it is very problematic. This question looks interesting, right? Let's take a look at it and see where we end up. A group of learners design a device that consists of a line to ball on a string hanging from the roof of a cargo truck. This device is used to determine the acceleration of the truck. When the truck is stationary or moving at a constant speed, the ball will hang straight down. But when it is undergoing a constant acceleration, the ball hangs down at an angle theta, as shown in the diagram below. And the first question, 2.1, draw a free body diagram of all the forces acting on the ball for 2 marks. So if this question was for 3 marks, you would expect 3 forces on your free body diagram. If it was for 4 marks, you would expect 4 forces acting on your object. And then now that it is for 2 marks, we are only expecting 2 forces to be acting on the ball, right? So let's go ahead and identify those forces. The first force, obviously, it's always weight. Before you start thinking about any other force, you put weight first, and then you go through your situation. Here we also have the tension.
the reason why our ball is hanging from the cargo, right? From the roof of the cargo. So to show the tension at an angle, there we have it. We have the tension and the weight. Why am I choosing to show the tension at an angle? Because in the diagram given, the ball is at an angle 2.2, 2.2.1. In this case, the mass of the ball is 50 grams and the angle theta is 18 degrees. Calculate the horizontal force on the ball. So horizontal force on the ball, the force along the x-axis is what we're looking for, right? Let's resolve that free body diagram first. We have the weight and we have Ty, the y component of the tension, and we have Tx. In this equation, we are looking for Tx, but we don't have the tension. Although we have the angle, we don't have the tension, right? So we cannot calculate Tx directly. What we can do, we can calculate the weight and equate it to Ty. And then after finding Ty, we can then find Tx. So we're going to say that the y component of our tension is equals to the weight. Our object is not moving upwards or downwards, so this equation should be true. So to find the y component of the tension, we're going to say tension, this angle here is 18 degrees. If this angle is 18 degrees, this angle here should be 72 degrees because this angle here is 90 degrees. So we're going to say tension sine of 72 degrees is equals to the weight. Our object weighs 50 grams. So that will be 50 divided by 1000 multiplied by gravity, right? Gravitational acceleration, which is 9.8. It's easy to see now that we're going to divide both sides by sine of 72. So divided by sine of 72, and then we do the same thing on the right hand side. We have to divide by sine of 72. And if you do that, you should get the tension being equals to 0.5152 newtons. So that is the entire tension. We are only interested on the x component. So now we're going to see that Tx is equals to the tension cos of theta. So what is our tension? We know that it is 0.5152 cos of 72 degrees. And if you put that in your calculator, you should get 0.1592 newtons. So there we go. We have the horizontal force acting on the pole. 2.2 magnitude of the acceleration of the track. As soon as I start hearing about acceleration, I'm thinking F net is equals to ma. We want the horizontal acceleration. There's only one force acting on the horizontal, which is Tx. So we're going to have Tx being equals to the mass multiplied by the acceleration. Tx is 0.1592. The mass is 50 divided by 1000 multiplied by the acceleration. So you can see here that we're just dividing both sides by 50 divided by 1000, and then we do the same thing on the left hand side, 50 divided by 1000. And if you put that in your calculator, you shall get an acceleration of 3.1842 meters per second squared. 2.3. A and B below are two identical blocks, each with a mass of 5 kgs, joined together by a light inextensible string. The blocks are being pulled with a force of 65 newtons at an angle of 40 degrees to the horizontal, as we can see. The two blocks accelerate to the right at an acceleration of 2.17 meters per second squared, and the tension in the rope is 26 newtons. Right, and then 2.3.1. Let's look at what the question says. Calculate the friction on each block. Let's start with block A. Right, so we don't have the coefficient of friction, so we cannot use FR is equals to the coefficient multiplied by the normal force. That is not going to work because we don't have the coefficient. What we can do instead is say that F net is equals to MA. So now we put in our tension on block A. So which forces are acting on block A? We have the tension, which is pulling it to the right. And then we have the frictional force, which is opposing. The normal and the weight, which we're not interested in, but anyway, yeah, they are acting on our object. So we're gonna have the tension minus the frictional force being equals to the mass multiplied by the acceleration. The force that is pulling the object minus all the forces that are opposing is equals to MA. So what is the tension? The tension is 26 and then minus frictional force. The mass of the object is 5 kgs and the acceleration is said to be 2.17. So minus frictional force is equals to 5 multiplied by 2.17 minus 26. So the frictional force acting on object A will be equals to 15.15 newtons. Right, that is the frictional force acting on block A. And moving to block B, let's use the same approach. Let's start with the free body diagram. We can never go wrong with the free body diagram. So we have the weight, we have the normal force, we have the tension and the frictional force opposing, and then the force that is pulling, we have Fx, right, the x component of F, and then we have Fy, the y component of F, but we are only interested on the x component of F, right? Again, F net is still equals to MA. What do you do at this step? You say that the force that is pulling the object minus all the force that are opposing. Which force is pulling the object? That is Fx minus all the forces that are opposing. The tension and the frictional force being equals to MA. So to find the Fx, we're going to say 65 multiplied by cos of 40. That is how we find the x component of that force. Minus the tension, which is 26, minus frictional force, which we're interested in, is equals to MA. Our mass is 5 kgs and our acceleration is 2.17. So we're gonna say minus frictional force is equals to 5 multiplied by 2.17 plus 26 minus 65 multiplied by cos of 40. Right, you just put that in your calculator and it is easy to see that the frictional force acting on object B is 12.94 newtons. An object that moves under the influence of the gravitational force only. That is the definition of projectile. If you omit the word object in your definition, you lose a mark. And after gravitational force, if you omit the word only, you lose another mark. So we have to be very precise with our definitions. That is the answer to 3.1. Let's look at our question statement and try answering 3.2. So a 50 grams ball is dropped from a certain height. The velocity time graph below represents the motion of the ball as it bounces vertically on a concrete floor. The time of contact during the bounce is 0.02 seconds. Ignore all effects of air friction. And then 3.2, the question says that let's write down the magnitude of the velocity with which the ball leaves the ground after bouncing. So let's look at our graph. Our ball is dropped from a certain height with this velocity right here, which is equals to 0. And then when it strikes the ground, it is striking the ground at 3.92 meters per second. And then it spends 0.02 seconds in contact with the ground, and leaves the ground with a velocity of 3.43 meters per second upwards. So the answer to 3.2, we're looking for the magnitude of the velocity with which the ball leaves the ground after bouncing. That should be 3.43 meters per second. And 3.3, draw a labeled free body diagram showing all the forces acting on the ball at 0.77 seconds. So let's go to 0.7 seconds and see what is happening. So at 0.77 seconds, our velocity is equals to 0. We know that we are at a maximum height. But apart from the velocity being equals to 0, there is nothing special about maximum height. Gravitational force is still acting on the object. It is still 9.8 meters per second squared downwards. So our free body diagram should look something like this. We have FG, right? And that is all that we are required to do for 3.3. Now let's move to 3.4 and look at 3.4.1. Use the information given on the graph and calculate the acceleration of the ball. So 3.4.1, we're looking for the acceleration of the ball. There's two ways we can use to answer this question. We can use equations of motion because we have VI, we have VF, and we have delta T. Another way we can find the gradient of our graph. The gradient of the VT graph will give you acceleration, and then the area will give you the displacement. So if we use equations of motion, our VI is equals to 0 meters per second because our ball was dropped, and VF is equals to 3.92 meters per second, the velocity at which we strike the ground. Then the acceleration is what we're interested in, and the time for that motion is 0.4. So if we use equations of motion, we're going to have VF being equals to VI plus A delta T. We're saying that VF is 3.92 and VI is 0 because it is dropped, right? Plus A multiplied by 0.4. It's easy to see now that A is just equals to 3.92 divided by 0.4, of which if you put in your calculator, you're gonna get 9.8 meters per second squared. So that is our acceleration using equations of motion. If we decide to use the gradient, we can take this first point here, we can take this point and this point and find the gradient between the 2 points, of which we're gonna get y2 minus y1 divided by x2 minus x1. y2, that is 3.92, and y1 is 0. x2, that is 0.4, and x1 is 0. Again, you can see that we're going to get 9.8 meters per second squared, regardless of which technique we decide to use. 3.4.2, the question is saying that let's calculate the height from which the ball was dropped. Again, two ways of answering the question: equations of motion or the area under the graph. For the position or for the displacement, we need the area under the graph. So also to find the height, we're going to use the area under the graph. For the acceleration, we use the gradient of the VT. So you need to know which to use when. We don't just calculate the gradient all the time, right? So if we use the area under the graph, we're going to have area being equals to half base multiplied by height. So the area which we're interested in, let me just erase this. The area which we're interested in is this very area here, is this area we have here. So if we decide to use that area, our base is 0.4. So we have a base of 0.4. And our height is 3.92. Our height is 3.92. The height of our triangle is 3.92. And then if you punch that in your calculator, you should get an area of 0.784. So our answer here will be 0.784 meters. That is the height from which our ball was dropped. Light work. Obviously, you can use equations of motions again to answer these questions. There's multiple ways of solving this one. I think there's probably 5 ways you can use to answer this question. The next question, 3.5. On the same set of axes, draw a position time graph for the motion of the ball from 0 second to 1.12 second. Use the ground as 0 reference, indicate the height from which the ball was dropped, and all the relevant times on the t-axis of your graph. So let's go ahead and try that. What do we need? We need our set of axes. We need a set of axes. So our y and our x. We are good to go now. We can say that this is y in meters and this is time in seconds. So our maximum height where our ball was dropped, that is 0.784. And we strike the ground after 0.4 second. We're in contact with the ground for 0.02. So we leave the ground at 0.042 seconds. So let's just plot that first before we carry on. So if we connect those two, we should have something like this. And then our ball will leave the ground, obviously. It reaches another maximum height. We can see that from our velocity time graph, right? It reaches another maximum height and then it goes down to strike the ground again. So there at the maximum height, we have a time which is 0.77 seconds. Here it is right here. And then the entire time for the motion is 1.12 seconds. And I think we get to go. I think we've indicated all that we needed to indicate. Let's look at 3.6. Give one term for the rate of change of momentum. One term for the rate of change of momentum. What's happening here? So the rate of change of momentum, delta P divided by delta T. We know fully well that this is equals to F net. So the one term which we should give is net force, right? If not net force, then at least resultant force. Yeah, there isn't anything else we can say there. 3.7. Calculate the magnitude of the force exerted by the floor on the ball for the time of contact. So let's go to a graph and look at that. Yeah, let's just erase this. So we're interested on only this part of our motion. We're looking for the force that the floor exerts on the ball. But let's just sketch or draw the free body diagram of the ball while it is in contact with the floor, so that we can have a bit of clarity. So if we do that, we're gonna have FG, obviously, as always, and then the floor is gonna be pushing the ball upwards. So this will be the force exerted by the floor. So that's what we have there. That is our free body diagram. So we can say that F net is equals to F exerted by the floor minus FG, because they're in the opposite direction. So if we calculate F net and we find another way of calculating FG, then we essentially have the force that is exerted by the floor. How can we find F net? We know that F net is equals to the change in P divided by the change in T. So at 0.4, we start with a velocity of 3.92. And at 0.42, when we leave the ground, we have a velocity of 3.43. Now it is important to note that it is 3.92 downwards, and then it is 3.43 upwards. So that will be essential when we choose which direction we take in as positive and which direction we take in as negative. And obviously our change in time is 0.02 seconds. So that seems like we have F net covered. We know that the mass is equals to 50 grams. So we have F net covered. FG, we also have it covered because we know that FG is our outermost simple case, right? So FG, the mass is 50 grams, and the gravitational acceleration due to the Earth is 9.8 meters per second squared downwards, right? That direction is going to come in handy when we substitute. So which direction do we want to take as positive? Let's take up as positive. So take up as positive. Take up as positive. It is just common sense. So in place of F net, let me just write our equation down again. So F net is equals to the force applied by the flow minus Fg. So in place of F net, we can put the rate of change in momentum, right? So the mass will be 50 divided by 1000 multiplied by Vf, which is 3.43 upwards, minus Vi, which is 3.92 downwards. So if it is downwards, we should substitute it with the minus sign if we take it up as positive. So we're going to have minus 3.92. We close that bracket and we divide everything by 0.02. And then this will be equals to the force that is exerted by the flow minus Fg. So what is our mass? Our mass, again, we have 50 divided by 1000 multiplied by 9.8. So that is 9.8 downwards. So it will actually be minus 9.8. Well, we have already indicated that Fg is going downwards by this minus sign right here. So our 9.8, it actually doesn't need that negative sign, because if it has that negative sign, then we have the force exerted by the flow plus the force exerted by gravity, because that minus and that minus will give you a positive. So that 9.8 is actually supposed to be positive. So we have 9.8 here. And now what you are left with is taking this term to the left hand side. And if we do that, we're going to get the force exerted by the flow being equals to. So now let's just drag and drop for the sake of time. So we duplicate that, and then we're going to have plus 50 divided by 1000 multiplied by 9.8. And that should give us 18.865 newtons. Right, 3.8. In 3.8, the question is saying, if a softer ball is used and the time of contact with the floor is increased while the change in momentum remains constant, how will it influence the force on the ball? Right, only increase, decrease, or remain the same? It is going to decrease, so the answer here is decreases. Why am I saying that? We have already deduced that F net is equals to the change in momentum divided by the change in time. So we're keeping the change in momentum constant. We're saying that it is the same. If we increase the change in time, F net would decrease. Why are we saying so? F net is inversely proportional to the time of contact. Conservative force, it is a force in which the work done in moving an object between 2 points is independent of the path taken. So that is 4.1, right? If we move to 4.2, the question is saying that let's name the conservative force in the diagram above, right? Without even looking at the diagram, I know that in our context, in our scope, we have only one conservative force, which is force of gravity or gravitational force. So the answer for 4.2
is force of gravity. That's the only conservative force we talk about in our scope. Moving to 4.3 is saying that let's take the work energy theorem in words. So we have work net being equals to the change in EK, and that in words goes as follows: the net work done on an object is equals to the object's change in kinetic energy. So the net work done on an object is equals to the object's change in kinetic energy. Basically, you just explaining the formula, right? Because it's easy to see from the formula that the net work done on an object is equals to the object's change in kinetic energy. 4.4. So 4.4 is in that the velocity of the block at point B is 6.92 meters per second. So at this point we have 6.92 meters per second, right, at point B. And then the question goes on to say that use energy principles only to calculate the frictional force that the block experiences and it moves from point A to point B. So when the question says let's use energy principles, there's two equations we can use. Work net is equals to the change in EK, and then work done by non-conservative forces is equals to the change in EK plus the change in EP, the potential energy, right? So I'm gonna go ahead and use the second equation to answer our problem, and then you guys can use the first one so that we can see if we end up at the same answer. So let me go ahead and do that, right? But then before I answer any question, I have to draw a free body diagram, right? So that I can see clearly what is going on. So if I go ahead and do that, so the block is going down. As it is going down, we know that there is the weight, which we can resolve to weight parallel and weight perpendicular, right? And then we have the normal force and we have the frictional force, right? So if you look at the forces acting parallel the surface, we have the frictional force and weight parallel, right? But then we know that force of gravity is conservative, right? So if I'm using the second equation, which says that the work done by non-conservative forces, then the only force I will consider is friction, right? So if I go ahead and do that, I'm gonna have frictional force multiplied by delta x multiplied by cos of theta, right? So that is supposed to be equals to the change in EK plus the change in EP, right? So if we go ahead and compute that, we're gonna get a half mvf squared minus a half mvi squared, and then plus mgh final minus mgh initial, right? And if we go ahead and substitute, friction is what we're looking for, so we're just going to have fr then, and then multiply by delta x, which is equals to 8 meters, right? The displacement of the object, and then multiply by cos of 180. When you're calculating the work done by friction, it will always be cos of 180 because it always acts in the opposite direction. And then that will be equals to a half. The mass of the object is 2 kgs. And then velocity final, it's here, right? We've talked about it, 6.92. So we have 6.92 squared minus a half the mass of the object, which is 2, and then velocity initial, which is 2 meters per second, right? We square that, and then we have plus mgh final. So the mass is 2 kgs, and then G, gravity, is 9.8, and then the height final. So now we have a problem. We need the height in order to use that equation, and we don't have it, right? So let's look here. We need that side. Yeah, we need the height. So what we have an angle and the hypotenuse, right? So it's easy to see that we can go ahead and say that, let me just do it here real quick. Sine of theta is equals to the opposite, which is our height, right, divided by the hypotenuse. So we're gonna have sine of 30 being equals to the height divided by 8. So the height is equals to 8 multiplied by sine of 30, which is equals to 4. So our height is equals to 4, right? So let's go ahead and solve our problem. So here we're gonna have so the height final. So we're coming from a height of 4, right? And then we go in here at B where the height is 0. So the height final is 0. And then height initial is the one that is equals to 4, right? So we're gonna get minus 8 frictional force is equals to, and then if you compute the right hand side, you're gonna get minus 34.5136. And then if we divide both sides by minus 8, so let's just go ahead and do that. Dividing both sides by minus 8, we're gonna get the frictional force being equals to 4.31 newtons. So that is 4.4, right? Let's do 4.5 real quick. So 4.5, the question is saying that the coefficient of friction for the last horizontal stretch after point B is 0.35. So here we have a coefficient of 0.35, right? And then the question says that let's calculate the distance the block will travel before coming to a complete stop without using equations of motions. So if it is coming to a complete stop, then we know fully well that we have VF is equals to 0, right? But then that's not all we have. We also know that VI is equals to 6.92 meters per second for that part of the motion. Yeah, it was VF from point A to B, but then from point B to a complete stop, it is now VI, right? And then what else do we have? We have the coefficient, which is equals to 0.35. So let's go ahead and set up our equations and see what we can do here. So we can use work net is equals to the change in EK, and we are governed by the variables you have, right? If you have VF and VI, you're most likely going to use this equation or that other one. So we're not just choosing it in randomly, we are guided by the variables we have. So now all we have to do is draw a free body diagram for the object. You're gonna see real quick that the only force acting is frictional force, right? Because even though the weight is acting on a flat surface, it does 0 work. We have the normal, it always do 0 work. So we're gonna have the work net being the force done by friction multiplied by delta x multiplied by cos of theta being equals to a half mvf squared minus a half mvi squared. So frictional force, the frictional force will be the coefficient multiplied by the normal force. We know that fully well, right? So the coefficient is 0.35 and the normal force is mass multiplied by gravity, so that will be 2 multiplied by 9.8, and then we have delta x, and then the angle that we have there is obviously cos of 180, right, for frictional force, and that should be all equals to, so I'm running out of space, so I'm just gonna write it here. So that should all be equals to a half the mass is 2 kgs, and velocity final, we know that it is 0 if we go into a complete stop, right? And then minus half 2 kgs, and then the initial velocity is 6.92 squared, right? So now all we need to do is just solve the right hand side and look for delta x, right? So if you do that, you're gonna get minus 6.86 multiplied by delta x is equals to the right hand side. So let me just put that in my calculator real quick and see what I get here. So I'm getting minus 47.8864, and then it is easy to see that we're going to divide both sides by minus 6.86, right? And then if we do that, we're gonna get delta x being equals to 6.98 meters. I don't think it was necessary to make the car look so animated, but it doesn't affect us with anything. Let's look at 5.1. For this investigation, write down the following: a dependent variable, one control variable, and a suitable investigative question for this experiment. So what is going on here? We have graded 12 learners that conduct an investigation to verify the speed of a race car using the Doppler effect. So they are verifying the speed of a race car using the Doppler effect. So that's a giveaway. We have our dependent variable in that very statement, because your dependent variable is what you're measuring. You're changing something, and then when you make a measurement, that is your dependent variable. Here we're investigating to verify the speed of a race car. So our dependent variable is the speed of the race car. So that is the answer to 5.1.1. Speed of the race car. So let's continue reading and see if we can extract the control variable and a suitable investigative question for this experiment. A race car driving around a race course at a constant speed emits a single frequency of 200 Hz. A learner records the sound using a cell phone as the car approaches him and after passing him. So what will we say is our control variable in this experiment? So the answer to 5.1.2, our control variable is our speed of sound in air. Right? We need the speed of sound in air to remain constant. It's going to have an effect on our results. So we need to ensure that the speed of sound in air is controlled. How can you possibly control the speed of sound in air? It will be wise to do your experiment in a very short period of time, because if you prolong it, then the humidity will most likely change as the day progresses and your results are going to be affected. 5.1.3, a suitable investigative question for this experiment. What is the relationship between the change in the frequency that will be observed relative to the speed of the vehicle? What is the relationship between the change in the frequency that will be observed relative to the speed of the vehicle? That is 5.1. And moving to 5.2. So when playing back the sound recorded on the cell phone in the presence of an oscilloscope, a difference in frequency of 67.15 Hz was registered. Use the information above to calculate the speed of the race car. Take the speed of sound in air as 340 meters per second. So there's actually 3 ways you can use to answer this question, because it is a bit open-ended, right? You're only told that there's a difference in frequency of 67.15 Hz. Is this difference when the car is moving towards or when the car is moving away? You're not told. So you can make a calculation and solve your equation as if the car was moving towards and as if the car was moving away. And then by doing that, you're going to get different answers, which are all correct. So let's just make calculation for when the car is moving towards, right? So we're going to have FL being equals to V plus or minus VL divided by V plus or minus VS multiplied by the frequency of the source. So there's a difference in frequency of 67.15 that was registered, right? So the frequency emitted by the source, that is 200 hertz. If we're saying that we're considering the case where the car is moving towards, then we can see FL will be equals to 200 plus the difference that was observed. And then for a person who's taking the case where the car is moving away, then it's going to be 200 minus 67,15, because you would expect the frequency observed to decrease, right? And then in our case, the frequency observed, we're expecting it to increase. So we have Fs, we have Fl, and we have V. It is given to us as 340 meters per second. So if we go ahead and substitute, we're going to have 267.15 being equals to 340. The velocity of the listener is stationary, right? So we can just leave that, divided by 340, and then the velocity of the source. For our case, the car is moving toward, so we're going to have minus Vs multiplied by the frequency of the source, which is 200. So we can divide both sides by 200 to get 267.15 divided by 200 is equals to 340 divided by 340 minus 4s, right? And then if you cross multiply, we're gonna get 200 multiplied by 340 being equals to 267.15 multiplied by 340 minus 267.15 Vs. Obviously, we're going to take this term to the left hand side. If we do that, we're going to get 200 multiplied by 340 minus 267.15 multiplied by 340 being equals to minus 267.15 Vs. And then I can divide both sides by the coefficient of Vs, which is minus 267.15 divided by minus 267.15, right? So we're gonna get Vs being equals to 85.46 meters per second, right? If you take the case where the car is moving towards, you're gonna get something around 170 meters per second, right? So that is what is so weird about this question. Moving to 5.3, the spectrum of light from most stars contains lines corresponding to helium gas. Diagram A shows the helium spectrum as observed in a laboratory. So let's look at diagram A right there, as you can see. And then for diagram B, shows the helium spectrum of light from a distant star. And then the obvious question is the distant star moving away from or towards the Earth? Explain your answer. It is moving away. It is moving away, right? So the difficult thing about this question is that you don't know where the red end is and you don't know where the blue end is, right? But you're given the wavelength instead. So you can deduce where the red end is and the blue end is from the wavelength, because we know that in the red end we have longer wavelengths. So right here we have the red end, longer wavelength. And then here we have the blue end, a shorter wavelength, right? We have 400 here, and here we have 700, right? And then again here we have blue, and then we have red. So here on Earth, that's our spectrum. And then here in our distant star, you can see that the spectral lines have shifted towards the red end. So it is moving away because of that. Define electric field strength at a point. This definition is actually different from electric field. So what does electric field strength at a point say? It says that the electric field at a point is the electrostatic force experienced per unit positive charge placed at that point. The electrostatic force experienced per unit positive charge placed at that point. That is electric field strength at a point. Totally different from just electric field. The answer to 6.1. Now let's look at 6.2. 6.2 is saying that let's sketch the electric field pattern around spheres B and C if A was removed. So let's look at B and C only. B is negatively charged, as you can see, and C is also negatively charged. So what is going to happen to those two spheres? They are going to repel, like charges repel. So we're going to have an electric field that looks like the following. There we go. I want you to realize something. Sphere B has a magnitude of 2.64 nanocoulombs, and sphere C has a magnitude of 7.46 nanocoulombs. That is why I'm deciding to put a lot of electric field lines on sphere C compared to sphere B. Usually, examiners don't care about that, but you never know. The greater the magnitude, the more field lines you should allocate to that sphere. 6.2. Let's look at 6.3. 6.3 is saying that charge B experiences a net force of 0.004078 newtons due to charges A and C. Find the distance R between the charges B and C. Let's go ahead and do some conceptualization here. So our charge of interest is B. We have the net electrostatic force that B is experiencing due to A and C. So let's draw a free body diagram for all the forces that B is experiencing along the X, that is. So B is negatively charged, C is negatively charged. That tells us that they're going to repel, like we have deduced in 6.2. So C will be pushing B to the left. So this is F of C on B. Now let's look at B and A. B is negatively charged, A is positively charged. So A will be attracting B to the left. So again, we have F of A on B. So all our forces are pointing to the left. That is to say that the F net on B will be equals to F A on B plus F C on B. Just a friendly reminder, F is equals to K, Q1, Q2 divided by R squared. So F net is equals to, actually let me not say F net anymore, because we know what F net is. F net is 0.004078, and that should be equals to F of A on B. So we're going to substitute in this formula. That will be K. K is a constant, 9 times 10 to the power 9 multiplied by Q1. So we can take Q1 as A, which is 5.6 times 10 to the minus 9 multiplied by Q2, which is B in this instance, 2.34 times 10 to the minus 9. We're only interested on the magnitude. We don't have to put a sign in electrostatics. And then the distance between them is 6 millimeters. So we're going to have 6 divided by 1,000 squared. You divide by 1,000 when you want to convert millimeters to meters. And then plus F C on B. Right. So we're going to have 0.004078 being equals to. When you put that in your calculator, you should get 0.003276 plus FC on B. So now it's just a matter of taking this term to the left hand side, and we have F of C on B, right? If you do that, you get 0.000802 being equals to F of C on B. Instead of F of C on B, now let's go ahead and substitute. So we're going to have K again, which is 9 times 10 to the power 9 multiplied by B, the magnitude of B, which is 2.34 times 10 to the minus 9 multiplied by the magnitude of C, which is 7.46 times 10 to the minus 9. Everything divided by R squared. If we do a bit of a mathematical manipulation at this point, we're going to get R squared is equals to 9 times 10 to the power 9 multiplied by 2.34 times 10 to the minus 9 multiplied by 7.46 times 10 to the minus 9. Everything divided by 0.00802. We take square roots on both sides. R is equals to 0.014 meters. And just like that, we have solved 6.3. Let's look at 6.4. So 6.4, charges A and B are allowed to touch and then moved back to the original distance between them. Calculate the new charge on each sphere. So when charges are allowed to touch and then separated, we say that Q nu is equals to Q1 plus Q2 divided by 2. But then in this formula, we actually have to account for whether a sphere is positively charged or negatively charged. For A, we can say that 5,6 times 10 to the minus 9 plus Q2, which is B, minus 2.34 times 10 to the minus 9 times 10 to the minus 9, right, divided by 2. The answer here should be equals to 1.63 times 10 to the minus 9 columns. 6.4.2. Explain the change, if any, to the fold pattern between B and C. So initially they were all negative, and now B, our sphere B is now positive. Our sphere B is now positive and C is still negative. So they're now going to attract. So what happens to the electric field lines when two spheres are attracting? What do they look like? The variable resistor R is set at a resistance of 3.5 ohms. So instead of having that R there, let's put 3.5 ohms. And then the first equation, 7.1.1. Let's calculate the total resistance of the circuit, including the battery. Right. So we're going to have RT being equals to RS plus RP. But we are required to include the resistance of the battery. So let's have plus the small r, which is our internal resistance, by the way. The resistance in series is just going to be the resistance of this variable resistor. It's the only resistor that is in series, right? R1 plus RQ and so on. This is sort of the formula we use. But then in this instance, we only have one resistor in series. So we're just going to have 3.5 ohms. And then now, let's go ahead and find the resistance in parallel. We're going to have 1 divided by RP being equals to 1 divided by R1 plus 1 divided by R2 plus 1 divided by R3 and so on. So we're going to have 1 divided by RP being equals to 1 divided by R1. So the resistors in parallel, this 10 ohm resistor is in parallel with this 30 ohm resistor. Why am I saying so? I'm saying so because the current flows from the positive terminal to the negative terminal. So when the current is flowing at this point, it divides. A proportion of the current comes to this path and another proportion of the current comes to this path. So that is why we're saying that those two resistors are in parallel with each other. So we're going to have 1 divided by 10 plus 1 divided by 30. So RP is equals to 1 divided by 10 plus 1 divided by 30 to the minus 1. If you put that in your calculator, you should get 7.5 ohms. So there we go. We have RP. The internal resistance is given to us right here is 0.6 ohm. So that is to say that RT, the total resistance, will be equal to the resistance in series, which is 3.5, plus the resistance in parallel, which is 7.5. And then lastly, the internal resistance, which is 0.6. You add all that and you'll get 11.6 ohms. And that is the total resistance of our circuit, including the battery. Let's move to 7.1.2. 7.1.2. Let's find the current measured by ammeter A2. Let me just remove these lines so that we can have a bit of clarity. We're looking for the current in this ammeter A2. We're looking for the current in this ammeter A2. So what are we looking for? We're looking for the current. It will be quite easy to find the current if we had the voltage and the resistance, right? But it seems like we have the resistance. There's a heater there with a resistance of 10 ohms. So our resistance is covered. We know that it is equal to 10 ohms. What we can actually do here, we have VT. We have the total voltage, right? And then we have the total resistance. We can find the total current. And then by finding the total current, we can then find VP. So let's go ahead and say that VT is equals to IT multiplied by RT. The total voltage is equals to the total current multiplied by the total resistance. The total voltage, that is 24 volts. And then the total current is what we are interested in, right? And then the total resistance, we calculated it to be 11.6. So IT will just be, so now it's just a matter of saying 24 divided by 11.6, which is equals to 2.069 ampere. So right, there we go. We have IT. Now that we have IT is just taking us a step closer to our answer. We're not looking for IT. We're looking for the reading on A2, and A2 doesn't read IT. So we can say that VP is equals to IT multiplied by RP. If you use this formula, you're going to be able to find the voltage that the heater experiences, or the total voltage on that path, that is. So VP will be equals to 2.069 multiplied by RP. I think RP is supposed to be 7.5. RP is supposed to be 7.5. And if you put that in your calculator, you shall get 15.53 volts. So now we have VP. Let's go back to our initial information. Now we have VP. We can say that this V here is equals to 15.53 volts. So now we can go ahead and find our current, because we have VP. We're going to say that the current on that path will be equals to VP divided by the resistance on that path. So VP, that is 15.53, and then the total resistance on that path, it is 10 ohm. So it's easy to see now that the current there on that path should be 1.55 amperes. And now we have answered 7.1.2. 7.2, the variable resistor is now adjusted to have an even higher resistance value. So the resistance of the variable resistor is increased. So we no longer have 3.5 here. We probably have 10 or something. Whatever number is greater than 3.5. The question is saying, how will this affect the power dissipated by the heater? Right? Only increase, decrease, or remain the same. So what is the equation for power again? Power is equals to I squared multiplied by R. So what is going to happen when the resistance increases for the entire circuit? When the resistance increases, the current is going to go down. If the current goes down and P is directly proportional to I squared, then the power should also go down. It should decrease. So the answer to 7.2 should be decreases, as we can clearly see from our equations. Let's perform an experiment to determine the internal resistance R of a battery. They use a variable resistor as the external resistance, as shown in the diagram below. Yeah, you can see the setup there. And these are the results of the experiment. We have experiment 1, 2, 3, 4, and 5. And the first question, 8.1, is saying, let's use the information in the table above to plot a graph of potential difference versus current. Use the graph paper supplied at the end of the question paper. We need V external versus current. As you can see, we have the potential difference on the y-axis and we have the current on the x-axis. The collaboration on both axes will earn you a mark. If you include all 5 points, you get another mark. If you have a baseline of fit, you have another mark. And the last mark is for a negative gradient. Your graph needs to be sloping down. As you can see here, that when the current is increasing, the potential difference is decreasing. The question that really interests me here is 8.2.1. Let's look at 8.2.1. Use the graph to determine the following: the EMF of the battery. So the graph is coming from this information in our table, right? But before we can determine the EMF of the battery in 8.2.1 or the internal resistance in 8.2.2, we actually need an equation for that graph. It is V external versus current, right? But we know fully well that EMF is equals to V external plus V internal. We need V external to be the subject of our formula, right? So we can say that V external is equals to EMF minus V internal. So V external will be equals to minus V internal plus EMF. But we know fully well, beyond reasonable doubt, right, that V internal is equals to I multiplied by the internal resistance. So if we substitute that in place of V internal, then we're going to have minus the current multiplied by the resistance plus EMF. So now you can see the equation we have for graph. It will be easy to determine the EMF and to determine the internal resistance. So let's start with the EMF. Obviously, you can see here from the equation that when the current is equals to 0, V external is equals to EMF. So if you come here to your graph, when the current is equals to 0, V external will be your EMF. So we can go ahead and say that EMF is equals to 1.5 volts. And 8.2.2, saying let's find the internal resistance of the battery. Use an equation to justify the method used. So which equation are we supposed to use? We have already deduced that V external is equals to I multiplied by R plus EMF. It's easy to see that V external is our Y, and then our current is X. So our gradient should be R, right? Plus EMF, which is C. To find the gradient, we actually have to calculate the gradient of the graph using the 5 experiments we have. So the gradient is equals to Y2 minus Y1 divided by X2 minus X1. So let's go and pick 2 points from the 5 data points we have. So we can take this point and this point. So this will be our second point and this will be our first point. Potential difference is our Y. So we're going to have 1,15 minus 1.5 divided by the current corresponding to 1.15 volts. That is 229. But it's not just 229. Look, we have this M here. We need to be aware of that. So it's 229 multiplied by 10 to the minus 3. And then minus the current that corresponds to 1.5 volts, which is equals to 0. Right. And then if you put that in your calculator, you're going to get minus 1.53. So our internal resistance is just equals to 1.53 ohms. And that is the answer to 8.2.2. Let's look at 8.3 real quick. A conducting wire of negligible resistance is connected between the points X and Y. Before we even continue reading, let's just go ahead and connect those 2 points so that we can see with clarity what is gonna happen to our circuit. So there we go. What does the question say? How does this affect the temperature of the battery? Write down only increase, decrease, or remain the same. Explain your answer. It is going to increase. It's going to increase. Let's talk about why that is the case. So when you connect X and Y, you no longer have external resistance. Right? Because the current is just gonna take this path. It's not gonna go to that rheostat there. It's not gonna go to our variable resistor. It's just gonna take this path. So what are we saying? We're saying that the resistance is gonna decrease. The external resistance is gonna decrease. It's actually gonna go to 0. And then when the external resistance decreases, what is gonna happen to the current? The current is going to increase. And then we know that R, our internal resistance, is constant. So if our internal resistance is constant and the current is increased, then V internal increases. And then V internal increasing is the reason why the temperature of our battery is actually going to increase. Describe the energy change that occurs in a DC motor. So for all motors, we have electrical energy to mechanical energy as our energy convention. And then for all generators, it is the other way around. We have mechanical energy to electrical energy. So since here we have a DC motor, our answer is just supposed to be electrical energy to mechanical energy. 9.2. Let's explain the term DC. DC standing for direct current is that current that keeps flowing in one direction. So current that keeps flowing in one direction. And then if the question was based on an AC motor and we would need to explain what AC means, we would say is the current that alternates, it changes direction. 9.3. In which direction will the conventional current in the coil flow? Alright, only from P to Q or from Q to P. We have a motor. For all motors, we use the left-hand rule. And then for all generators, we use the right-hand rule. For the left-hand rule to work, you need to put your thumb, your index finger, and your middle finger 90 degrees to each other. And then with your index finger, your pointing finger, you point from north to south, right? And then if you do that, your thumb is going to be pointing up if they are indeed at right angle with each other. And then your middle finger will be pointing from Q to P. And then this middle finger that is pointing from Q to P is the direction of the current. So the answer to 9.3 is Q2P. If it was a DC generator, we would be using the right hand rule. We will do the same thing, but now using the right hand. On motors, we use the left hand. Right. 9.4. Explain the change that needs to be made for this motor to be an AC motor. So without being told that this is a DC motor, we can tell by the presence of this split ring. We have these split rings right here. So if you want to change this DC motor to an AC motor, we have to replace that split ring. We have to replace the split ring with slip rings. Don't confuse the two. For DC, we have split ring, and for AC, we have slip rings, right? And 9.5. Let's look at 9.5 and do some calculation. A heater level 2000 watts, 220 volts and 50 hertz is connected to an AC circuit. Calculate the maximum current that flows through the heater. Right. So we have the power average given to us as 2000 watts. and then we have VRMS, which is 220 volts. And in order to find the maximum current, we will need IRMS first. Why am I deciding that this voltage that is given is VRMS and not Vmax? How do I know that it is VRMS and not Vmax? It is because this heater is connected to an AC. When an appliance is connected to AC, the current is IRMS and the voltage is VRMS. You should put that in mind so that you know what to do the next time you get a question like this. So now we can say that the P average will be equals to VRMS multiplied by IRMS. Nothing new, because we know from electricities that the power can be equal to the voltage multiplied by the current. Nothing surprising there. So the power average, that is 2000 watts, VRMS just 220 multiplied by IRMS. We just divide both sides by 220 and get that IRMS is equals to 9.09 ampere. Another way of finding IRMS is by saying that IRMS is equals to Imax divided by square root of 2. So you can see here what we have to do now. We're going to say that Imax is equals to IRMS multiplied by square root of 2. So we have 9.09 multiplied by the square root of 2. If you put that in your calculator, you should get 12.86 ampere. The minimum frequency of light needed to emit electrons from a certain metal surface. That's what we call threshold frequency. The answer to 10.1. Let's look at 10.2.1. Let's calculate the work function of cesium. Let's calculate the work function of cesium. Let's go through our information and see what we have. How can we potentially calculate the work function of cesium? So we have a photoelectric cell which is connected in a circuit. The lowest frequency of light that will emit electrons from its cesium surface is 5.1 times 10 to the 14 Hertz. So we have the threshold frequency, which is equals to 5.1 times 10 to the power 14 Hertz. Right. And then we can calculate the work function using the threshold frequency, because the work function is equals to Planck's constant multiplied by the threshold frequency. So this will be equals to H. Planck's constant obviously is a constant, as the name says. It is 6.63 times 10 to the minus 34 multiplied by the threshold frequency, which is 5.1 times 10 to the 14, and this is equals to 3.38 times 10 to the minus 19 joules. We have our work function. This is the minimum amount of energy required for an electron to be emitted. 10.2.2, we're calculating the amount of energy carried by the incident photons of violet light. So we have violet light of wavelength 400 nanometers that is incident on our cesium surface. So the amount of energy, if you are given a wavelength, will be equals to Planck's constant multiplied by the speed of light divided by the wavelength. If you're given the frequency, then it's just Planck's constant multiplied by the frequency. But I'm sure you know that. Again, Planck's constant, that is 6.63 times 10 to the minus 34 multiplied by C, which is speed of light, 3 times 10 to the power 8 divided by the wavelength of the incident light of the violet light, which is 400 times 10 to the minus 9. Now it's just a matter of putting that in your calculator to get 4.97 times 10 to the minus 19 joules, Let me just write that again. to the power minus 19 joules. So let me show you something. This is the amount of energy from the light that is incident on our surface, and then this is the amount of energy that is required. So you can see that the amount of energy that is incident is greater than the amount of energy that is required. So when those photons are ejected from the surface, they're going to have a kinetic energy. They're going to have some form of kinetic energy, right? 10.2.3, the maximum kinetic energy of the photoelectrons emitted from the cesium surface when violet light shines on it. So now we actually need that kinetic energy, which I was talking about in 10.2.2. Well, our energy is equals to H multiplied by the frequency, of which the frequency can be C divided by wavelength. But then at the same time, our energy is equals to the work function plus EK max, So what I've realized is that some examiners, if you omit these max here on your EK, you actually lose a mark. So yeah, be aware of that and not lose mark unnecessarily. So in our equation, we have the energy of the incident light, and then we have the work function of our metal surface. Now we need EK max. It's just a matter of direct substitution and making EK max the subject of the formula, solving for X, basically easy max. So EK, not EK max, but then the energy is equals to 4.97 times 10 to the minus 19. This will be equals to the work function, which is 3.38 times 10 to the minus 19 plus EK max. For the faint-hearted ones, we just take in this term to the left-hand side and we are done with our equations, right? And then if you subtract 3.38 times 10 to the minus 19 from 4.97 times 10 to the minus 19, you're going to get EK max. So we have EK max being equals to 1.59 times 10 to the minus 19 joules. So that is the maximum kinetic energy of the electrons that have been emitted from the cesium metal surface when violet light is incident.